Welcome to the University of Colorado Boulder's Power Electronics Specialization. In this course, you will learn how switching power converters change electrical power from one form to another with very high efficiency and accurate control. A popular example today is the electric vehicle such as the Tesla Model S. The heart of its power system is a power converter that changes the DC battery voltage to variable frequency and variable voltage AC to control the electric motor that drives the wheels. Power electronics on the vehicle also performs the function of battery charging, converting the 60 Hz AC from the utility into the DC required to charge the battery, with control of the current so that battery life is maximized. The Toyota Prius, a hybrid electric vehicle, also contains a power electronics module under the hood. It similarly controls an electric motor and battery charging.
Another example of power electronics is the connection of a variable speed wind turbine to the AC utility. The frequency and voltage of the AC produced by the electric generator vary with wind speed. In this application, power electronics can be used to convert the variable AC to the fixed frequency and voltage required by the utility.
Some other examples of applications include solar power systems, the power systems of mobile electronics, computer server systems, and spacecraft power systems. In general, we require high-efficiency power conversion with accurate and sophisticated control to optimize energy use.
This specialization is an introduction to the electronic circuits used to convert electric power with high efficiency. You will learn how these circuits work and how to model their losses and design their control systems. Welcome to the course Introduction to Power Electronics. I'm Professor Robert Erickson from the University of Colorado at Boulder and the Department of Electrical, Computer, and Energy Engineering. This course is available in both non-credit and for-credit versions. It's the first course within the specialization on power electronics. It's also the first course of our graduate certificate in power electronics, and it serves also as the first course in a pathway specialization that can allow you to gain admission into our Master of Science degree program. In this short video, I'm going to discuss how the credit and non-credit courses work, including enrollment and grading. It's very important, so I hope you'll watch the video all the way through. This course uses our textbook Fundamentals of Power Electronics. However, you don't have to buy the book to take the course. All of the material that you need is available in the videos and in the PDF files containing the lecture slides. While we are not able to formally enforce prerequisites, this course is taught at a graduate level, and the basic assumption is that you are fluent in the material of circuits and electronics at the level that it's taught in a typical undergraduate electrical engineering degree. So as I mentioned, this course is the first course in a specialization called Introduction to Power Electronics. If you sign up for the for-credit version of this course, it carries the University of Colorado course number ECEA 5700, and you can receive transcripted credit for this course. The three other courses that follow this course in the specialization are listed here. The second course is on converter circuits, the third is on control of converters, and the fourth is on design of magnetics for converters. And the intent is to give you the basic technical foundation to actually build power converters in the lab. For your information, the specialization covers the same technical material that we teach in our regular on-campus course that's called Introduction to Power Electronics, and it's numbered ECEN 5797. We have both for-credit and non-credit versions, and here's the difference between them. So you can sign up either way. If you sign up for the non-credit version, you pay Coursera the fee for the non-credit course, and if you complete the assignments of the non-credit version, then you can earn a Coursera certificate of completion. If you sign up for the 4-credit version, then you pay university tuition, and if you complete the assignments and the examination in that course, then you can earn transcripted university credit that you can apply towards our campus graduate certificate in power electronics and to our Master of Science degree in electrical engineering. Both the non-credit and the 4-credit versions give access to the same lectures, homework assignments, supplementary materials, and discussion forums. To get access to the exams, you need to sign up for the 4-credit version. The 4-credit version also additionally gives you access to course facilitators, also known as teaching assistants, and they will hold office hours, regular office hours, where you can dial in remotely and talk to the course facilitators. The non-credit version is continuously available, so you can start and stop at any time. The 4-credit version is scheduled into 8-week sessions. So once you sign up for the 4-credit version, you need to finish before the 8-week session concludes. If you sign up for the non-credit version, you can transfer, if you want, into the 4-credit version. You'll have to pay the university tuition for that 4-credit version to do that, but when you do it, then any work that you've done on the homework will be automatically transferred into the 4-credit version of the course. We have a performance-based admission process to our MSEE degree program. This involves completion of the 4-credit versions of the power electronics courses, the 4 courses of this specialization, with a grade point average of at least B or better throughout those 4 courses. If you complete the 4-credit version, then it can be applied towards that performance-based admissions process. The 4-credit version can also be applied, as I mentioned, to the university graduate certificates and towards the MSEE degree. A little bit about changing your enrollment status. So first of all, as I mentioned, you can switch from non-credit to 4-credit at any time. One strategy might be to sign up for the non-credit version, try the homeworks and see how they go, and if you feel like you can handle the work, then you can at that point upgrade to the 4-credit version. So to do that, you will have to pay the university tuition for the 4-credit version, but any work that you've done in the non-credit version is automatically transferred. In the 4-credit version of the course, you can drop the course within 14 days of enrolling and receive a full tuition refund. When you do this, the course then does not appear at all on your university transcript. After the 14 days, you can still withdraw from the course. At that point, you won't receive a tuition refund, and the course will appear on your transcript, but with a grade of W, which stands for withdraw. The W grade does not impact your grade point average and really doesn't mean anything except that we're not going to issue you a grade. You can withdraw at any time up until the point when you access the exam of the course. Once you access the exam, then you're committed and you'll be issued a grade on your transcript. At the end of the 8-week session for a 4-credit course, your course grade is computed if you haven't dropped or withdrawn. So your course grade is computed on whatever work you've entered, and you will be issued a grade. I hope that if you don't complete the class that you would withdraw or drop and not just let a grade turn in automatically into an F. That's not the goal here. So please be diligent in dropping or withdrawing if needed. For this course, ECEA 5700, there are 3 homework assignments, and basically it's 1 per week or whatever pace you want to go at. You're allowed unlimited attempts to these assignments. They are auto-graded, and you can find out what your score is immediately and try again if you like. There are also in-video quizzes. These are just for your own edification, and they're not graded. At the end of the 4-credit course, there are some examination preparation materials These are not in the non-credit version, including a practice exam. This practice exam is not graded, but it has the similar conditions to the real exam, and I suggest you try it and see how it goes. You can withdraw from the course at any point, including after you've done the practice exam. And then finally, we have a proctored examination, which is the one that counts. Again, this is only in the 4-credit version of the course. The proctored exam is similar to the homework assignments, and it has a similar format. The main difference is that it's a closed book exam, that it uses a proctoring service, and it's a timed 2-hour exam. So what you will be able to do is have unlimited submissions to the problems within the 2-hour time period and get feedback on which ones are right and wrong according to the autograder. But when the 2 hours are up, then the exam is over, and it will use your last submission as the final grade. So we have 3 homework assignments. Here's how they are weighted. So 15%, 20%, and 15%. And then the exam is weighted 50%. This weighted average then determines the final course letter grade for this course. And it is all really automatic, or it's machine graded. The non-credit course has the same materials as the 4-credit course, except for the exam module. So it has the 3 homework assignments, it has all of the lectures and supplementary materials. To earn a Coursera Certificate of Completion, you have to successfully pass all 3 homework assignments, and the typical passing threshold on the assignments is 70%. So what's on the course site? There are recorded lectures for the entire course. There are the slides used in each lecture, which you can download as PDF files and follow along. There are the homework assignments, and there's some solved sample problems for additional help. There are discussion forums for each homework assignment. The first assignment relates to simulation of a switching converter, and so there are some simulation files. You will need to be able to run LT-SPICE, which is a circuit simulation program that you can download for free. The 4-credit version of the course has exam preparation materials, and it has a link to the actual exam. So for the first week of class, what you should do is view the lectures for Module 1, and then do homework assignment number 1, which is simulation of a boost converter. I look forward to your participation in the class, and I hope that you find it a useful and high-quality course. In this brief lecture, I'm going to summarize the technical content of the power electronics courses and specializations that we will offer for credit. So the area of power electronics is quite broad, and it incorporates elements from a number of different subfields of electrical engineering. Certainly it's based on analog circuits and electronic devices. Control systems and feedback systems are very important. We have applications in power systems. The design of the magnetics is very important, and an important part of the design of a power converter. Often we interface electric machines, and often we will use numerical simulation. So in this course, Introduction to Power Electronics, ECEA 5700, I'm going to assume that you have some undergraduate prerequisite knowledge in analog circuits and electronics. I'm not going to assume anything else. And this first course will cover power converters really from the standpoint of analog circuits and electronic devices. So this course 1, that is 4 weeks long plus a proctored exam at the end, really is summarized by this slide. In the first week, we're going to do simulation of a switching converter. So you will use LT-SPICE to look at the waveforms of an actual switching converter. We'll learn techniques of steady-state converter analysis. So if you have a switching converter that has switched waveforms like these, how to analyze them to find things like the output voltage or the inductor currents of the converter circuit. We'll then develop equivalent circuit models, such as this one, that model the basic conversion properties of a switching converter, as well as modeling losses in the circuit. And this kind of equivalent circuit then can be used to analyze a converter to predict things like its efficiency curves. The follow-on course 2, called Converter Circuits, ECEA 5701, goes into more detail in how these switching converters work. We'll talk about how to realize the switches using power transistors and diodes. So we'll talk some about power semiconductor devices. And one of the important things to learn here is how they switch and where switching loss comes from. So here are some typical waveforms of the diode reverse recovery process, which is one of the major sources of switching loss in a practical converter. So we'll learn how to model that. We'll learn about the different important power devices, such as the power MOSFET. We're going to analyze what's known as the discontinuous conduction mode that occurs in some switching converters. And we'll look at different converter circuits or circuit topologies, including ones with transformer isolation. Here is a well-known transformer isolated converter known as the forward converter, which is one of the isolated circuits that we'll discuss. The third course in this specialization is called Converter Control, and this is an introduction to applying feedback to a switching converter. Generally, we want to regulate an output voltage or an inductor current or some similar quantity. So here's an example of a switching converter circuit known as the buck converter with a feedback loop around it to control the output voltage of this buck converter. This is a pretty complex system, and we have switched waveforms that are fairly complicated. And so in course 3 we will learn how to model the important voltage and current components in the circuit and derive equivalent circuits that we can use to design feedback loops. Course 3 will cover an introduction then to feedback in the context of switching converters. The last course, ECEA 5704, is an introduction to magnetics for switching converters. So we'll talk there about just how basic inductors and transformers work, talk about their AC and DC loss mechanisms in both the core and the winding. And we'll talk about how to design basic inductors and transformers for switching converters. Simulation is a recurring theme in this specialization and in the following ones as well. Here we're going to use LT-SPICE in this course, and in fact in the first homework this week you will use LT-SPICE to simulate the basic waveforms of a switching converter. Here is actually an example from the follow-on specialization, which gets into more detail and more advanced topics in converter control. But this is an averaged model of a switching converter and its feedback loop that can predict things like small signal transfer functions, and which can be used to design the feedback loops. That follow-on specialization goes into more advanced control techniques such as current mode control, power factor correction, input filter design, digital control, and related topics. We have a graduate certificate that we offer through this program. The graduate certificate is comprised of this specialization, the follow-on control specialization, and then a capstone design project. And in this project you will design the power conversion system for a USB Type-C interface, which interfaces a computer and its battery to a USB cable. So this involves selection of the converter circuits, design of the power stage, design of the magnetics, design of the analog controller, and then simulation and verification that your design meets requirements. Here is the prerequisite chain for this specialization. So this course, Introduction to Power Electronics, assumes a basic undergraduate knowledge of circuits and electronics, but that's all. It is prerequisite to the second course in the specialization called Converter Circuits, which I mentioned before. That one is prerequisite to the final two courses. So the control course and the magnetics design course both assume that you've had or gotten through the second converter circuits course. So I look forward to your participation in this course. I would encourage you to take advantage of the discussion forums, and in the credit course we also have course facilitators who will hold regular office hours, and I urge you to take advantage of their help as well, and I hope that you find this course rewarding. The field of power electronics is concerned with the processing and control of electrical power using high-efficiency electronic circuits. The key functional element in power electronics is called a switching converter. This lecture describes the basic functions performed by switching converters, and it introduces how high-efficiency electronic circuits can be constructed that realize these functions. The switching converter generally includes two input terminals. One is the power input, where a source is connected. The second input is a control input that tells the converter how to process the input power to produce the output. DC to DC conversion is a common function performed by converters in which the voltage of the DC is changed and possibly regulated. So we may change, say, a high input voltage into a low DC output voltage. Rectification is the conversion of AC to DC, and in the process we may want to control the output voltage, the DC output voltage, and maybe also the AC input current waveform. The inverse of rectification is called inversion, in which we have a DC input and we produce an AC output of a controllable frequency and magnitude. AC to AC cycloconversion involves changing the frequency and the amplitude of the AC voltage. In each of these, the switching converter is the key electronic power processing element, and it is composed of electronic devices as well as reactive elements, and we attempt to build this with very high efficiency. Control is invariably required. We usually want to regulate the output voltage. Although we may want to control currents or other quantities. So we're generally also building some kind of control system that adjusts the control input to the converter, for example, to regulate the output. We can do this with either traditional analog feedback, or nowadays it's economically feasible to use quite sophisticated control using digital microcontrollers. High efficiency is essential in any application that involves very much power. We want high efficiency nowadays, of course, because we want to conserve energy, but in addition to that, it's simply not possible and not economically feasible to process large amounts of power with low efficiency, because our converter will not be able to handle the heat from the power lost. So here's the equation for efficiency. It's the ratio of output power to input power, and the loss is the difference between the input and output power, which we can express in terms of the output power and the efficiency in this way. Now, our switching converters are loss limited. They're limited by the amount of heat sinking that we have and the size of the enclosure. And so for a loss limited converter with a given efficiency, this limits the amount of output power that the converter can produce. So if we can build a converter with higher efficiency, then we can either reduce the loss and build a smaller converter with smaller heat sinks, or for the same amount of heat sinking, we can get more output power and build a converter that produces more power. So a measure of how good the converter technology is really is the ratio of the output power to the efficiency. And here it's expressed in terms of efficiency. We can solve for this quantity, and it turns out to be efficiency divided by 1 minus efficiency, and it's plotted here. And so you can see that even increasing the efficiency by a few percent can increase the amount of output power, or reduce or increase the ratio of output power to loss substantially. And so our goal is to produce efficiencies that approach 1, which makes the ratio of output power to loss approach infinity. So the higher we can get on this curve, the smaller our converter can be, and the more input and output power it can produce. This drawing here is meant to represent a very small size converter with very large input and output converters. So we have a very small converter with very high efficiency that processes a very large amount of electric power. How do we build a circuit that changes the voltage with high efficiency? Here's a diagram of, in general, the different categories of electrical circuit elements that we have. Resistors, capacitors, magnetics, including transformers and inductors, and semiconductor devices that here are generally grouped into two categories. The first is linear mode transistors, such as Class A amplifiers or op-amp circuits, and the second is switched mode, which is transistors that are operated as on-off devices, such as in a digital circuit, where they're either all the way on or all the way off. In signal processing, such as you probably learned in undergraduate electronics and circuits courses, we usually avoid magnetics. Well, we don't have to, but magnetics generally are more expensive. They're hard to integrate on integrated circuits. And most engineers don't know how to design them. And so for a variety of reasons, we usually ignore or avoid magnetics. But resistors and capacitors are fine. Linear and switched mode semiconductors are also common. In power processing, by contrast, what we want to do is avoid using elements that consume power. So for that reason, we don't want to use resistors. However, capacitors and magnetics are fine, and in fact, it may be easier in a high power application to build a good inductor than it is to build a good capacitor. But we commonly use inductors, capacitors, transformers, and other elements because although they store energy, ideally they don't consume power. We can get that stored energy back at some later time. We avoid linear mode transistors for the same reason that we avoid resistors. That a Class A amplifier, for example, operates with a transistor having voltage across it and current through it at the same time, and so it consumes power. On the other hand, switched mode transistors, or transistors that are operated as on-off switches, are good. They don't consume power. The reason for that is if we can get them to operate close to the behavior of an ideal switch, then what happens is when the switch is closed, there's no voltage across the switch, and when the switch is open, there's no current through the switch. And in either state, the power consumed by the switch, which is the product of voltage and current, is zero. So to the extent that we can make a semiconductor device operate as an ideal switch like this, the semiconductor device will be lossless. So let's do a simple example of how to build a DC-DC converter with high efficiency and using just inductors, capacitors, and switches. Okay, so I'm going to take a simple example with some round numbers here. We have an input voltage I've labeled VG that is a power source, and it's 100 volts. And what we would like to do is change this 100 volts into 50 volts to supply a resistive load. And just for some round numbers, let's suppose the resistance is 5 ohms so that we have 10 amps flowing through our load. Okay, so how can this converter be realized? First of all, let's ask how, in a beginning circuits class, what circuits do you know that could change 100 volts into 50 volts? Okay, well, the resistive voltage divider is one of the first circuits taught, usually in a beginning circuits class, and we learned that the output voltage of the divider is equal to this voltage divider ratio of the load resistance over the sum of the two resistances times the input voltage. So if we adjust this added resistor to be the same value as our load resistor, we'll get a divider ratio of 1/2, and the output voltage will be half of the input. Okay, the problem with this is that the same current flowing to the load also flows through this resistor, and the same power in the load then is equal to the power in this resistor. And so we will have our 10 amps flowing through the resistor that has 50 volts across it. So there'll be 500 watts of loss in this resistor. There's 500 watts going to the load, and we draw 1,000 watts out of VG. So the efficiency is only 50%. At low power levels, it's common to build a series pass regulator circuit that operates almost in the same way as the resistive voltage divider. Except instead of a resistor, we put a transistor that operates in the active region, and it has the same voltage across it that the resistor on the previous slide had, so it dissipates the same 500 watts. With the series pass regulator, what the transistor allows us to do is to build a feedback loop that adjusts the control or the drive of the transistor to regulate the output voltage. But in this example, the series pass regulator is approximately 50% efficient. So we need a very large transistor that can take 500 watts and that has enough heat sinking to dissipate that 500 watts, which is not an easy thing to do. Let's consider instead how to do this function with switches. So instead of an active region transistor, we will use semiconductors that are operated like on-off switches. And here I'm going to draw an ideal switch, but we will realize this switch in practice with transistors and diodes that turn on and off. So let's suppose we have such a switch. We switch it quickly between positions 1 and 2 so that the voltage coming out of the switch network from here to here, Vs of t, has this waveform. So when the switch is in position 1, the voltage Vs is equal to the input voltage Vg of 100 volts. And when the switch is in position 2, the output voltage is 0. And we will operate the switch so half of the time it's in position 1, the other half it's in position 2. Okay, what do we accomplish with this? Well, the switch changes the DC voltage level. So here is this actual waveform coming out of the switch. We can use Fourier analysis to find its DC component, and you may recall from Fourier analysis that the DC component of a waveform is found by integrating the waveform over one period and then dividing by the period. So if you integrate this waveform, the integral is the area under this curve, which is this width dts times the height Vg. So we get an area of dts Vg. And if you divide by the ts, then what we find for the DC component is that it is d times Vg, where d is the duty cycle, or the fraction of time that the switch is in position 1. Okay, so if the switch is in position 1 for half of the time, then the duty cycle is a half, and the output voltage of the switch has a DC component that is half of the input. So the switch succeeds then in changing the DC component of the voltage from 100 volts down to 50 volts. Generally, we don't like to have that switched voltage appear across our load, so we will put a low-pass filter. And here's an LC low-pass filter that can be put in that if we design this filter correctly so the cutoff frequency is much lower than the switching frequency, this filter will pass the DC component, but it will reject the switching frequency and its harmonics and not let them pass through to the load, so that the output voltage is smooth and essentially is just the DC component of 50 volts. So this is a circuit that can change the DC voltage, and it does it with components that are ideally lossless, only switches, inductors, and capacitors, so it can have efficiencies that approach 100%. This is known as the buck converter. Here's one way to realize the switch using transistors and diodes. We have a power MOSFET and a power diode that switch together. And I've also shown here a feedback circuit, say a simple analog feedback circuit, that adjusts the duty cycle. It actually turns the transistor on and off and adjusts its duty cycle to regulate the output voltage. So this is a buck regulator. It's possible to build converters that will change any voltage into any other voltage. Here's an example of a boost converter that can increase the voltage. So we can build circuits that contain inductors, capacitors, and switches connected in different ways that can actually change any voltage into any other voltage as desired. Here's another example of a single-phase inverter. Here we have two single-pole double-throw switches with the load and filter connected differentially between their outputs, so that the voltage differentially between the two switch outputs looks like this. It can switch between plus VG when the switches are in position 1 or minus VG when the switches are in position 2. And by changing the duty cycle, we can change the average value, and we can actually modulate the duty cycle sinusoidally and make a sine wave of output voltage if we want to produce, say, a DC to AC inverter. Okay, so in this course you're going to learn how to build these converter circuits, how to analyze them and model them to, for example, predict their efficiencies, and also how to design and model their control systems. SPICE is a program that was originally developed at UC Berkeley in the 1960s, and since then there have been many commercial implementations of it, and one of them, LT SPICE, is freely available now and I think works very well. Here's an example, which we're going to talk about in this lecture. One enters the schematic of a circuit, in this case a buck converter, and then SPICE can numerically calculate things of interest in the converter, such as the waveforms in a transient analysis, as well as other things like frequency analysis plots. So here is a turn-on transient of a buck converter where the output starts at 0. The green waveform here is the output voltage that it computes. It goes through some turn-on transient and eventually settles down to a DC voltage that is approximately, for the buck converter, approximately equal to the input voltage multiplied by the duty cycle. Also in red here is a plot of the inductor current waveform during the same turn-on transient. To get started, what you should do is follow this link to the LT SPICE website, and from there you can download free copies of the software, either for Windows operating system or for the Macintosh operating system. From this Coursera website you can also download a zip file containing the buck converter circuit files for this example. So when you've done that, then you can double click on this file buck.asc, which will open the file in LT SPICE, and that file contains the circuit schematic. Then what you do is press the run button to start the simulation. When this simulation will take maybe 10 or 20 seconds to run. When it's done, then to display a waveform you can click on a node and it will give you the node voltage. Or you can click on an element and it will plot the current through the element. Okay, here I have opened LT SPICE and opened the buck converter schematic. What we have here, this is the buck converter power stage with the input voltage VG of 24 volts and output voltage that supplies a 5 ohm load resistor. Here is the LC filter, and the switch in the buck converter is realized with this power MOSFET and power diode. The circuit has a driver and a pulse width modulator. These are called behavioral models or mathematical models of these functions that we have developed for this Coursera course. So the pulse width modulator takes a DC input voltage, here V duty, that has a value of 0.4 volts DC, and it produces an output logic signal C that switches on and off with a duty cycle that is determined by V duty. Here the duty cycle of C will be 0.4, It has a switching frequency that is set by the pulse width modulator, and you can right-click on the pulse width modulator and enter the switching frequency. In this case, the switching frequency is set to 100 kilohertz. This signal C goes into the driver. The driver produces an output voltage to drive the gate of the MOSFET with respect to its source at the proper voltage to turn the MOSFET on and off according to the signal C. So to run the simulation, we put the cursor on the run button, the little running person there, and click it. It will take maybe 10 or 20 seconds for the simulation to run. Okay, the simulation is done. LT Spice has opened a new window here for plotting waveforms, and we can move the cursor over the schematic to different places to plot different waveforms. So first let's look at what the pulse width modulator is doing. I will move the cursor over the pulse width modulator input. The cursor changes into a little voltage probe signal, and if you click there, it will plot that voltage. Okay, so the voltage is 400 millivolts or 0.4 volts. We can look at the output voltage that the pulse width modulator makes. So I'll move the cursor over C. Okay, this is the blue signal here is switching up and down with a frequency of 100 kilohertz. Let's get the magnifying glass and zoom in on part of this, maybe over here. So the blue waveform is C, the control signal. It has a switching period of switching frequency of 100 kilohertz, corresponding to a switching period of 1 over 100 kilohertz or 10 microseconds. And the signal is high for the duty cycle times 10 microseconds, which would be 0.4 times 10 is 4 microseconds. Okay, I'm going to erase these waveforms, and now we'll look at some converter waveforms. So to erase a waveform, what you do is right-click on the name of the waveform here on the plot. So right-click on the PC, or you tap the trackpad with 2 fingers on the Mac and select delete this trace. Let's plot now the switch node voltage. So we have to click on the window of the schematic, and then when we hover over the switch node right here at the point between the transistor and diode, we can click with the oscilloscope voltage probe symbol and get a plot of the switch node voltage in green. So when the MOSFET is on for the DTS period, the switch node is equal to VG, like this. And we have 24 volts for VG. And then when the transistor is off, the diode comes on, and the switch node voltage is equal to ground, essentially, and so we have 0 volts or a low voltage. Let's plot the inductor current also. So when I hover the mouse over the inductor, the pointer turns into a little current probe to measure current in the inductor with positive current in the direction showed by the red arrow. So let's just click there. And the blue trace then is a plot of the inductor current. It goes up and down like this. It's switching or varying between about 2.6 amps and about 1.1 amp. Okay, finally we can plot the output voltage. So we'll take the mouse and hover over the output voltage and click. So the red line is the output voltage. It looks like it's between 9 and 10 volts. Now we expect the output voltage of the buck converter to be the duty cycle times the input voltage. So V should be equal to the duty cycle times VG. VG is 24 volts and the duty cycle is 0.4. So 24 times 0.4 is 10 volts. And what we find is the output voltage is a little bit less than 10 volts, but it's close. The SPICE simulation includes some of the loss mechanisms in the converter. It includes the forward voltage drops of the transistor and diode. Here I put a little resistor in series with the inductor to model the resistance of the wire used to wind the inductor. And these things all cause voltage drops that make the output voltage a little less than we would ideally expect. We'll model those things in Module 3 of this short course and develop some equivalent circuit models that predict more accurately what the output voltage is. Let's plot the input current waveform. I will select the schematic window and hover the mouse over VG. You can see that again it turns into a current probe symbol, and the arrow is pointing from top to bottom in VG, which means current is flowing from plus to minus through VG, which is backwards from the direction we actually expect the current to flow. So SPICE is going to plot this current with a negative sign, or make it negative. Here's a plot of it. When the transistor is on, the current follows the inductor current, again with a minus sign. When the transistor is off, the transistor current is 0, and so the VG current is 0 also. We also have this current spike here, and this is caused from the reverse recovery of the diode and from the transistor and diode switching times. This is another source of loss called switching loss, which we're going to study in the next short course of this course. We can measure voltages and currents using SPICE. What we do is we press the control button and click on the name of the waveform, and then a window comes up that tells us the average value and the RMS value of the waveform. So the current drawn out of VG, this I of VG, has an average value or DC component of here 707 milliamps. So we're drawing 770 milliamps on average of current out of VG. This current includes the current spike during the switching times. We can use this function to measure input currents and output currents and voltages as well, and calculate average powers and efficiencies of the converter. Likewise, we can plot the current that the gate driver draws out of its power supply. So what I do again is select the schematic window, hover over the power supply for the gate driver, and click there, and we'll get the current waveform of the gate driver, which looks like this. The gate driver must draw current out of its power supply to turn the MOSFET on, and so we see these current spikes happening. So the gate driver requires some power to operate, and we can measure the voltage and current of the gate driver and calculate its power as well. So I will control click on that waveform, and here we see that there's an average current of 14.876 milliamps drawn out of the driver. That's the average value of the waveform. It's actually coming in spikes that are considerably higher. But the average current is the DC component of current, and the average power drawn out of the gate driver supply then would be this average current multiplied by the gate driver voltage of 12 volts. Briefly, here are a few more details regarding the models that we have provided for the pulse width modulator block and the gate driver block. The functionality of this block is that it produces an output logic signal C having a duty cycle given by this formula. So it's a function of VC, the input voltage. It can have an offset, and it can also has a gain, so it's divided by some effective number V sub m. You can right click on this block to set values for those things, the offset voltage and Vm. Right now Vm is set to 1 volt, the offset is set to 0, so the output duty cycle is just equal numerically to the DC value Vc. The block also limits the duty cycle. It has to be between minimum and maximum values, which can be set as well. And you can set the switching frequency again by right-clicking on the block and typing the number in the window. The gate driver block, similarly, is a behavioral model that represents key features of gate drivers. So what you do is you apply the logic signal C to this input terminal of the driver. The driver actually measures its input voltage with respect to this input reference, which here is tied to ground. And then it produces an output voltage here with respect to the driver VDD or VSS signal here. And what we do is we apply these two terminals to the gate and source of the MOSFET to turn the MOSFET on and off. The output ground or reference of the driver need not be the same as the input reference. We also have to supply power to the driver to make the circuit work, and so here we've connected a 12-volt power supply between the input power supply VDD and its ground pin VSS. One last point, let's look again at the complete simulation for the output voltage and inductor current. So I will again plot the output voltage, and we'll plot the inductor current. And this is a plot from t equals 0 all the way to 5 milliseconds, and you can see what happens during this turn-on transient. All the signals are starting at 0 with the converter turned off, and then when we turn on, the circuit goes through some transient where the output voltage rises and there's some kind of here overshoot and ringing in both the current and the voltage, and eventually the circuit settles down into steady state. So here's a steady state output voltage and a steady state inductor current. We can measure those values as well using SPICE. So we zoom in at some point after the transient is done, and then we can control click to measure the average voltage, 9.2855 it says. So again, a little bit less than 10 volts. We can also control click on the current to measure the average inductor current. It says that is 1.8573 amps. Okay, the homework assignment for this week is to download a boost converter file. There's a zip file on the Coursera site for the homework assignment. You should download SPICE and get it to run, and then run this boost simulation file on your computer, and then use LT-SPICE to answer the questions in this homework assignment, which are things such as what is the steady state DC output voltage or average output voltage, the inductor current, calculate the system efficiency by measuring the input power and the output power and dividing, and so on. We previously introduced the buck converter, which is a converter that is capable of stepping down the voltage, ideally with very high efficiency. The key steps were first to introduce a switch network. Here is a single pole double throw switch that in practice is built using power transistors and diodes that can switch back and forth very quickly. The output voltage of the switch, Vs of t, then is a waveform that steps up and down. When the switch is in position 1, the output voltage Vs of t is equal to the input voltage Vg. Likewise, when the switch is in position 2, the output voltage is equal to 0. We repetitively switch the devices, or this switch network, with a period that is called the switching period T sub s. And the switching frequency F sub s then is equal to 1 over T sub s. So the switch is in position 1 for a fraction of time called the duty cycle d, and the d is a number between 0 and 1, so that we're in position 1 for time d times ts. Then we're in position 2 for the remainder of the switching period, so that would be for a time 1 minus d times ts. Okay, it's traditional to use the notation that 1 minus d is equal to d prime, and that's called the complement of d. So d prime is also a number that is between 0 and 1. Okay, what do we accomplish then with this switch? It reduces the DC component of the voltage so that Vs of t has a lower DC component than does Vg. We previously calculated this DC component using Fourier series. So from Fourier series, the DC component is found by integrating the waveform over one period and dividing by the period. And that's effectively finding the average value of the waveform. So to find the integral, we would integrate the waveform or find the area under the curve. That area is in fact easy to find. It's simply the area of this rectangle. So the area is equal to the base of the rectangle, which is d times ts, multiplied by the height of the rectangle, which is the voltage, input voltage Vg. So we plug that area in for the integral and then divide by the period, and what we get is that our DC component of Vs is equal to the duty cycle times Vg. And that DC component is also is the average of the waveform. So the switch network performs the function then of changing the DC component of the voltage, and it actually reduces that DC component by a factor of the duty cycle D. Now generally we don't like to apply this switched waveform to our load. We would like to produce a nice steady output voltage without this switching. But the problem is that the switch waveform, in addition to having the desired DC component, also has these high frequency AC components in the Fourier series. And these AC components are at the switching frequency and its harmonics. So how should we remove those switching components and just apply the DC component to our load? Well, we remove the switching harmonics by introducing a low-pass filter, and we can build a low-pass filter using elements that ideally are lossless with a circuit such as this one. We can insert an inductor and a capacitor that will perform as a low-pass filter with a cutoff frequency that we call frequency F0 or F0. So the low-pass filter, what the low-pass filter does is to pass components in the Fourier series that are at frequencies less than the cutoff F0 and reject the frequency components that are greater than F0. So if we choose the values of L and C to make the cutoff frequency much less than the switching frequency Fs, then our low-pass filter will reject the switching frequency and its harmonics, but it will pass the DC component, so that the output voltage V of t then will be essentially constant and equal to the DC component dVg. So then we've succeeded in building a converter that has very high efficiency and uses elements that ideally are lossless. And not only that, but this DC output voltage is adjustable. By changing simply the timing of the switching to increase or decrease the duty cycle, we can change the output voltage. So we can control the output voltage or make it follow whatever waveform we like. Okay, that is called the buck converter. In the power business, the term buck denotes a reduction of voltage. And so what we call the conversion ratio of the converter, M of D, which is defined as the ratio of the DC output voltage to the DC input voltage, that M of D is equal to D for the buck converter, and so the output voltage is reduced. Now, this is a commonly used and well-known converter, but there are many others. The boost converter is another well-known converter, and it's built by interchanging the positions of the inductor and the switch. It turns out that the boost converter can increase the voltage, so the output voltage is greater in magnitude than the input, and it is controllable by adjustment of D. Another well-known converter is the buck-boost converter, shown below here. The buck-boost converter can invert the polarity of the voltage. So with a positive input, we get a negative output. And the magnitude of the output voltage can be either increased or decreased by adjusting D. In fact, there are many converters known. We can build a converter by some circuit containing L's and C's and embedded switches, and change any voltage into any other voltage we like. So we found the output voltage of the buck converter using these arguments of Fourier analysis and low-pass filtering. But it may not be immediately obvious how to extend those arguments to find the output voltage of the boost or the buck boost. It's actually possible, but it may require some additional insight and cleverness. And so the object in Chapter 2 is to develop a systematic approach to solve for the voltages and currents of a switching converter. Okay, so we're going to introduce first the key small ripple approximation that lets us solve the waveforms of the circuit with relative ease and simple equations, and this small ripple approximation is valid in well-designed converters. With that approximation, then, we will develop the principles of inductor volt-second balance and capacitor amp-second or charge balance that let us get a system of equations that can be solved for the voltages and currents of the converter. We'll also develop some simple methods for choosing the values of inductance and capacitance in the converter, and I'll illustrate the use of all of these techniques with some examples. In this lecture, we will develop the basic analytical techniques that allow us to solve for the voltages and currents of any arbitrary switching converter. Specifically, we'll employ the small ripple approximation to simplify the equations, and we'll derive the principles of inductor volt-second balance and capacitor charge balance that give us the DC equations of the converter circuit. So if you recall from the previous lectures, we discussed the buck converter having a switch and having a low-pass filter that removes the switching harmonics but allows the DC components or the DC component of the waveform through to the output. Now, in a practical converter, we can't build a perfect low-pass filter. The low-pass filter will have attenuation, but it won't completely remove the switching harmonics of the waveform. And therefore, the output voltage of a practical converter might look like this, where there's a DC component, capital V, that, as we previously found, is equal to the duty cycle times the input voltage Vg. And then, in addition to that, we have some small ripple that is at the switching frequency and its harmonics that where a small amount of the switching ripple gets through the filter and appears in the output. And as sketched here, this ripple is actually probably a lot larger than it would be in practice. So in a practical circuit, we'll have some kind of specification on how large this switching ripple can be, and generally it's a very small number. So in an output voltage of, say, a volt or two for a computer power supply, this ripple might be 10 millivolts or some very small number. So therefore we can write the equation of the output voltage V of t as being equal to capital V, which here I'm using the capital letters to denote the DC components. So capital V is the desired DC component equal to dVg, and then plus some AC variation, that's called V ripple of T here, that is the undesired switching harmonics that make it through the filter to the output voltage. So in a well-designed converter, this LC filter will have lots of attenuation, and the ripple will be very small compared to the DC component. So we call this the small ripple approximation, where the ripple is small compared to the desired DC component, and under certain circumstances we will neglect the ripple and simply approximate the output voltage by its desired DC component. Okay, this has the effect of decoupling the equations, the differential equations of the circuit, and making them very simple to solve. Okay, so this is called the small ripple approximation, to ignore this component and simply approximate V of t by capital V. Okay, brief discussion here. As we're going to see in a minute, the small ripple approximation formally can be applied only to continuous waveforms that have small ripple. So we don't apply the small ripple approximation to switched waveforms in the circuit, such as the switch output voltage Vs of t. Instead, we apply the small ripple approximation to continuous waveforms, and specifically the inductor currents and capacitor voltages of the circuit. Okay, so let's take an example here of a buck converter, where here's our original circuit, and we would like to solve for the waveforms such as the inductor current waveform IL of t and the output voltage waveform V of t. Okay, so with the switch in each position, this circuit reduces to a linear circuit that we can solve by standard, sophomore circuit analysis. So for example, with a switch in position 1, the circuit reduces to this one, in which the left side of the inductor is connected to Vg. Okay, this is a second order RLC circuit, and we could solve it. In fact, in principle, we can simply solve the second order differential equations of the circuit. And with this being a second order circuit, in general, the kinds of waveforms that we get are sinusoidal or decaying exponential in nature. So the actual IL of t, when we solve this circuit, might have some waveform that looks like this, for example, with some initial value, IL of 0, and then some solution of the second order differential equation. Now, in a well-designed converter, this low-pass filter has a cutoff frequency that is very low in frequency relative to the switching frequency. And what that means is that the time constants, or the time that it takes this response, this ringing response, to happen, is long compared to the switching period. So one switching period might be just this long, for example. And in the small ripple approximation, what we're actually doing is approximating this solution for a short time with a straight line. And for that reason, we also often will call the small ripple approximation instead the linear ripple approximation. And any continuous waveform for a short enough time can be approximated by a straight line. And so that is what we're in fact doing. Of course, if it's a discontinuous waveform, such as a switched waveform, then we cannot, in general, approximate it with a straight line. So we apply the small ripple approximation as appropriate to inductor currents and capacitor voltages that have responses such as this one that we can approximate over the switching period or a fraction of the switching period with a straight line. Okay, we can do a similar thing with the switch in the second position as well, where the inductor, left side of the inductor, then is connected to ground instead of VG. We get another circuit to solve, and we can find the waveforms for that interval as well in a similar manner. So let's look at, for example, for the first interval, finding the inductor current waveform using this small ripple approximation. So from solving this circuit, we have a loop right here that the inductor is connected in, and the loop equation for this circuit is the inductor voltage VL is equal to the input voltage VG minus the capacitor voltage, here it's called V. So we get this equation for the loop that the inductor is connected in. Okay, now V of t is the output capacitor voltage, and as we've discussed so far, we want this capacitor voltage to have small ripple, and so V of t again can be expressed as its DC component, capital V, plus the small ripple. And here is a case where we can replace V of t by its DC component, capital V, to find the inductor voltage for this interval. And so this is a good approximation over the short time of when the switch is in this position. Okay, so this is a small ripple approximation. Knowing the inductor voltage, we can now find what the inductor current does using the well-known defining equation of an inductor, that V is L di dt in the inductor. So if we plug this expression for the approximate inductor voltage into there and solve for di dt, we get this equation, which says that the inductor current changes with a slope that is given by the voltage over the inductance, with the voltage being equal to a constant value, Vg minus capital V. Okay, so for this first interval, the inductor current will start at some initial value, IL of 0, and it will increase with this slope. And it will increase with that constant slope until this first interval is over and the switch is changed to position 2, which happens at time dts. Okay, then during the second interval, we get this circuit with the left side of the inductor connected to ground, and the loop equation now around this loop where the inductor is connected says that the inductor voltage VL is equal to minus V, like this. We can again use the small ripple approximation to replace V of t with its DC component, capital V, and ignore the ripple during this interval. And we can plug that voltage into the defining equation of the inductor again to find the slope of IL during the second interval. And what we find then is that the inductor current for this interval changes with a slope equal to minus V over L. So we started at some initial value, we went up during the first interval and ended at some point. And then during the second interval, we now change with a different slope, and the slope is negative, assuming the output voltage is positive. So we get a slope for this interval of minus V over L, and the current goes down until the switching period is over, and we end at time Ts, we end with some final value. Okay, so the small ripple approximation makes it simple to sketch what the inductor current waveform looks like. We have straight lines that have constant slopes and are easy to solve. And this greatly simplifies the equations so that we don't have to write decaying exponential type functions and have pages of algebra. So then here's a summary of what the inductor current voltage and current waveforms look like. We found the inductor voltage during each interval it was positive and equal to an approximately constant value during the first interval. And during the second interval, it was equal to an approximately constant negative value. What this did was made the inductor current go up during the first interval and then go down with a negative slope during the second interval. Okay, one thing we can do with this right away is get an equation that helps us choose the value of inductance. You can see that the actual inductor current waveform has switching ripple. The current goes up and down with a triangular waveform at the switching frequency. And on top of that, it has an average value, or DC component, which is the DC value of inductor current that we'll call capital I. To design the inductor and choose an inductor value, we generally will try to limit the amount of switching ripple in the inductor current. How much ripple we allow is a design choice, and at least for the next several weeks we will discuss converters where this ripple is limited in value to maybe 10 or 20% of capital I at full power. Okay, so the ripple, we commonly define the peak to average ripple as delta IL, and so 2 delta IL is the peak to peak ripple, which is from here to here. Okay, and from this waveform and knowing the slope, we can easily write an equation that for how large the ripple is. So for example, during the first subinterval with a switch in position 1, the inductor current changes from here to here, and the net change is 2 delta I. So we can write 2 delta IL as the change in inductor current, and this is simply equal to the slope during the first interval, Vg minus capital V over L, times the length of the first interval, which is dTs. Okay, so knowing the slope and the time, we can find the change, and we can solve then for delta IL. Just divide both sides by 2, and we get this expression. Okay, this is the equation that is commonly used to calculate the value of inductance and choose an inductor for the converter. So we can solve this equation for L, push L onto that side, and get this equation. And from this equation, we can solve for the value of L that gives a given value of delta I. Okay, there's another thing we can do besides finding the value of L. We would like to find the steady state voltage and current in the converter. So let's consider now what the inductor current does during a turn-on transient of the converter. So for example, let's suppose that we start the circuit with the inductor current equal to 0, and the output voltage is 0 also. So we'll start at 0 with the circuit turned off, and at t equals 0 we'll start switching so we'll switch between positions 1 and 2 with some fixed duty cycle. Okay, we've already found what happens. The inductor current will change with some slope during each interval. And so during the first interval, the very first switching period, the inductor current will go up with a slope that we've already found is equal to Vg minus V over L. Okay, well initially what V is the capacitor voltage Vc. In fact, let's just call this V instead of Vc. So the voltage is initially 0 at the output, and our slope during the first interval is Vg over L. Okay, so we go up until at the end of the first interval at time dts, we've reached some positive current. Okay, what happens to the output voltage? Well, this inductor current is small, but it's a little more than zero. That inductor current flows to the output, and it will slightly charge the capacitor voltage up a little. So V is still small, but it's a tiny bit more than zero. Okay, during the second interval, with a switch in position 2, we found that the inductor current changed with a slope of minus V over L. Okay, so we have a slope here of minus V over L. Well, V, the output voltage, is nearly zero, so minus V over L is pretty close to zero, and there's hardly any change in inductor current during this second interval because the slope is nearly zero. Okay, after one switching period, we end up with the inductor current at what, IL of TS, a little bit positive. It's a little greater than zero. Now we repeat the process. So for the second switching period, we'll go up with a slope of Vg minus V over L. V is a little positive now, so the slope during the second interval, this slope, is a little bit less than that slope was last time. So we don't quite increase as much. Okay, and then during the second, with the switch in position 2 for this switching period, we'll go down with a slope of minus V over L. V is a little more positive than it used to be, so this slope is a little more negative than it was during the previous period. And we end up with some net increase in current, but it's not as much as we increased in the first period. And we repeat this process, okay, with the output voltage slowly charging. And eventually, after many switching periods, we end up at some current. Let me just draw it out here, and some output voltage where the amount we go up during the first interval with this slope of Vg minus V over L is exactly equal to the amount we decrease during the second interval where the slope is minus V over L, so that we end up at the same current we started. The capacitor voltage does something also, and it ends up at the same place it started. Okay, and so at this point, this is maybe at time in TS, and here's in plus 1 TS. So after in switching periods, where in is some large number, we end up in steady state, where the waveforms become periodic. Each switching period has waveforms that are the same as the previous switching period, and the current and voltage end up at the same place they started. So you can see that will happen when the output voltage rises to a large enough value, so V is large enough so that these slopes have adjusted, and our final value, IL of in plus 1 TS, equals IL of in TS. And at that point, we say that we're in steady state. So the waveforms from then on have the correct DC values where the converter is supposed to operate. And we've gone through some transient that eventually has settled out, and we've reached steady state. Okay, it is possible to find a simple relationship that expresses that the circuit works in steady state. And it comes from this notion that we end up at the same current that we started at for the inductor. And we can derive it, in fact, from the defining relationship of the inductor, that V is L di dt. What we do is we integrate this equation to find the net change in inductor current over one switching period. So what we can do is integrate both sides of the equation. So integrate VL of t dt over one switching period. So we'll integrate, say, from 0 to Ts over one switching period, and here we'll integrate from IL of 0 to IL of Ts. And when we evaluate these integrals, the right-hand side gives us IL of Ts minus IL of 0, which is the net change in current. And if I divide both sides by L, I can write the other side of the equation as 1 over L times the integral of the voltage over one period. So in steady state, then, the net change in inductor current must be 0. And therefore, this integral of the voltage must be 0. Okay? And this is the basic relationship where we say this is volt-second balance on the inductor, that the integral of the voltage has dimensions of volt-seconds, and if you integrate the inductor voltage over one complete period, that integral, or area under the curve, must be 0 if the inductor current has no net change over that period. Another way to write this equation is simply to divide both sides by the switching period Ts, and in that case we recognize that 1 over Ts times the integral of the voltage is the DC component. So another way to say this is that the DC component of the voltage applied to the inductor is 0 when the circuit operates in steady state. We're going to use this notation of angle brackets around a variable to mean the average value. So the average value of the inductor voltage is 0 in steady state. Okay, let's try that. Try finding the applied volt-seconds to the inductor in our buck converter. We previously found this waveform was the voltage waveform applied to the inductor. The inductor saw a voltage of Vg minus V during the first interval and minus V during the second. So we have to integrate the inductor voltage, and the easy way to do that is simply to find the area under the curve. So during this first interval we have an area that is the base dTs times the height. The height is Vg minus V. During the second interval we have an area that is the base here, d prime Ts. It's the length of the second interval. Times the height, which is minus V. So if we add these two areas, they have to add up to 0. Okay, so here is that area, and if we equate it to 0 like this, we get an equation, and we can simplify this equation. D plus D prime is in fact 1. Recall D prime is 1 minus D, so the sum of D plus D prime works out to be 1, and we get dVg minus V equals 0. You can solve this for the output voltage V, and we find that the output voltage is dVg. Okay, well, we already knew that for the buck converter, but in fact this was a way to find the output voltage without using the arguments of Fourier series and low-pass filtering. Here we simply draw the inductor voltage waveform and set its average value to 0, and this is something we can do for any converter. So we could similarly use this approach to find the output voltage of, say, the boost converter or the buck-boost converter. So volt-second balance plus the small ripple approximation then gives us a way to solve for the output voltage. Okay, capacitor charge balance, or capacitor amp second balance, is the dual of inductor volt-second balance. We can apply a similar principle to a capacitor in the circuit. What we do is we start with the defining equation of the capacitor. I is C dV dt in the capacitor. We can integrate both sides of this. So integral of IC dt is the C times the integral of dVc. And if you integrate over one period, from say 0 to Ts, then this part here gives us the change in capacitor voltage over one period. The net change is Vc of Ts minus Vc of 0, and that's equal to 1 over C times the integral of the current. If we operate in steady state, then there is also no net change in capacitor voltage over one period, so the left-hand side of this equation is 0. And this says the integral of the capacitor current must be 0 when the converter operates in steady state. Again, another way to write this, we can divide by Ts, multiply by C, and find that the DC component of capacitor current must be 0 in steady state. Okay, so we can use the principle of capacitor charge balance to get a similar equation to find the conditions under which the capacitor voltage will operate in steady state. This might be more familiar than the inductor volt-second balance, or perhaps more intuitive. If you put a DC component of current into a capacitor, then the capacitor will continue to charge. And if you keep putting charge on the plates of the capacitor, just positive charge, say, then the charge will build up and the capacitor voltage will increase, and it won't operate in steady state. If for part of the time we put a positive current, say part of the period we put a positive current on the capacitor, making its voltage increase, for the other part of the period we must put a negative current to bring the charge back down, to have no net change in charge, and therefore have no net change in capacitor voltage. In this lecture, we will work a boost converter example. So we're going to apply the techniques of volt-second balance, capacitor charge balance, and the small ripple approximation to find the voltages and currents of the boost converter. So here I've shown a boost converter using an ideal switch. So the switch is in position 1 for this first interval of time dTs, and it is in position 2 for a second interval of time d prime ts. I've also labeled the inductor voltage and current, as well as the capacitor voltage and current. Incidentally, here is how we, in practice, normally realize the switch using power transistors and diodes. So there's a gate drive circuit that's just shown here as a voltage source, but when we want the switch to be in position 1, this gate driver will produce a high voltage on the gate of the MOSFET that will turn it on. And when it's on, it effectively pulls this node down to ground, just like when the switch is in position 1. For the switch in position 2, what we do is the gate driver turns off the MOSFET by making its gate voltage low. When the MOSFET is turned off, the inductor will forward bias the diode, turning it on and putting the switch effectively in position 2. Now, one thing you might wonder is, can we put a diode here, and why does it automatically come on? Well, one way to look at this is to go back to the formula for the inductor, that the inductor voltage is L di L dt, which is the voltage from plus to minus across here. So when the MOSFET is on, we build up some positive current flowing through the inductor and through the MOSFET. When we turn the MOSFET off, one way to think about it is we're effectively trying to interrupt the inductor current. So the inductor current that was positive is now trying to be forced by the MOSFET turning off to go immediately to 0. So what is DIL dt? Well, DIL dt is big and negative if we're shutting it off. You could think of it as heading towards minus infinity for slope. But maybe in practice it isn't. The IDT isn't that large, but it is negative and large in magnitude. So if the IL dt is negative, say let's call it minus infinity, what that does is it will make VL become big and negative. Well, VL is plus to minus in this direction. That's the reference direction. So if VL is a negative number, effectively it means that the negative terminal is becoming positive and the positive terminal is going down. So this node here, where the MOSFET is connected, will head to a large positive voltage from the voltage developed in the inductor. So it heads towards plus infinity, but long before it gets there, it forward biases the diode. And so in fact, when this voltage rises above the output voltage, the diode will turn on and clamp this voltage to the output. And once it does turn on, then it provides a path for the inductor current to flow. The inductor is happy and the current no longer tries to change. So we can put a MOSFET and a diode that will operate automatically with the MOSFET. Sometimes in the business, a diode that operates in this fashion is called a freewheeling diode. Okay, so what we would like to do now is apply volt-second balance to the inductor and charge balance to the capacitor to solve for the voltages and currents of the converter in steady state. So here's how we do it. First of all, on the original circuit, it's important to clearly label the reference polarities of the voltages and currents. And if you're not very careful about this, it's very easy to make minus sign errors and get the wrong answer. So to head off a lot of problems coming up soon, let's label the waveforms or the variables directly on the original converter. So I've defined the inductor voltage and arbitrarily chosen its reference direction as plus on the left and minus on the right, which means that if the variable VL of t is positive, the voltage is in the direction shown, and if VL of t is a negative number, then the actual voltage will have the other polarity. That's an arbitrary choice of the direction, but we pick some direction for now. Okay. Once we've defined a direction for the voltage, the inductor current must be defined in a direction that flows through the inductor from the plus terminal to the minus terminal of the voltage. So IL of t is a quantity having a reference direction that goes from left to right through the inductor. Likewise, here I've drawn the output voltage, which coincides with the capacitor voltage as being plus on top and minus on the bottom. And so the capacitor current must be defined as flowing through the capacitor from the plus terminal to the minus terminal in this direction. So positive capacitor current is flowing in this direction. Okay. Now we draw the circuit with a switch in the two positions. So on the bottom left here is the circuit that we get with the switch in position 1 with the right-hand side of the inductor connected to ground like this. And for this circuit, I now carefully copy over the directions of the voltages and currents that were labeled on the original circuit. So VL of t is shown here, IL of t is shown there, etc. And you have to keep the same polarities. Likewise, for the switch in position 2, the right side of the inductor is connected to the output, like this. And I again copy the voltage and current reference directions for the switch in position 2 and use the same reference directions as in the first position. Okay, having done this, now we can write the expressions for the voltage and current in each case. So with the switch in position 1, we got this circuit the MOSFET is on and the right side of the inductor is connected to ground. So the inductor voltage here we can see is equal to the input voltage VG, like this. And the capacitor current we can see flows this way, and it's equal to minus the load current. So the load current here is V over R, and from the node equation at the output node, the capacitor current equals minus V over R, like that. These are the two things we need to know for this interval in order to apply volt-second balance to the inductor and charge balance to the capacitor. Okay, next we make the small ripple approximation. And in particular, we have the output capacitor voltage right here, V of t, which we will approximate with its DC component, capital V, like that. So for the first interval, we have an inductor voltage VL that's equal to VG, and we have a capacitor current that's equal to minus V over R. Okay, let's do the same thing for the second interval. With a switch in position 2, the right-hand side of the inductor is connected to the output node, so we get this circuit, and our inductor voltage now is VG minus V. We'll add VG on the left minus V on the right. And the capacitor current here we can express from the node equation at the output node as being equal to the inductor current IL minus the load current V over R. So we get these equations. We again make the small ripple approximation. So V of t can be replaced by its DC component, capital V. And also we have an inductor current term here. We're going to make the small ripple approximation on it and replace the inductor current IL of t with its DC component, capital I, or capital IL. Here it's, on this slide it's called capital I. Okay, let's sketch the waveforms now. So the inductor voltage waveform we need to sketch in order to apply volt-second balance. And what we found was that the inductor voltage during the first interval was equal to Vg, and that's for interval of length dts. Okay, and that's supposed to be a straight line equal to capital Vg. During the second interval, the inductor voltage we found was Vg minus V. Now, where should I draw Vg minus V? Is that a positive number or a negative number, and why? Well, if the volt seconds are going to balance, so the average VL is 0, and if we have a positive voltage during the first interval, then the voltage had better be negative during the second interval if we were to have any chance of making the average come out to be 0. So I'm going to draw this voltage during the second interval as a negative quantity. And you can see that since the voltage has to be negative to get the volt seconds to balance, V needs to be bigger than Vg. So therefore this is a boost converter where the output voltage V is bigger than the input voltage Vg. And volt seconds won't balance otherwise. So this is during interval d, the second interval of length d prime ts. That's our inductor voltage waveform. We can now apply volt second balance to this waveform. So the average VL will be, well, we can find the area under the curves and divide by the period, but an easier way to find the average is simply to take the value during the first interval, Vg, multiply that by the duty cycle d, and add to that the voltage during the second interval, Vg minus V, multiplied by d prime. and that'll give us the average. So in steady state, by volt-second balance, this must be equal to 0. And now we have an equation that we can solve to find the output voltage. Let's in fact solve it. Let's collect terms. We have Vg times, let's see, d plus d prime. Then we have minus d prime v equals 0. Recall d plus d prime equals 1. So we have d prime v equals vg, and solve for v, we get v equals 1 over d prime times vg. Okay, so that's the equation for the output voltage of the boost converter in steady state. Since d prime is a number less than 1, v is greater than vg. Given this voltage waveform, we can also find the inductor current waveform. Well, we don't know where it starts, but in steady state it starts at some current. We'll call it IL of 0. And for the first interval it increases because we have positive voltage. So again, recall the inductor voltage is L di dt. So the slope dIL dt is the inductor voltage over L. So when we have positive voltage, we have positive slope in the current. The current goes up with a slope of the applied voltage Vg over L. And during the second interval, we have negative voltage, so we get a negative slope, and the inductor current goes back down with a slope of Vg minus V over L. If we're in steady state, we end up at the same current that we started at. Okay, so there's the inductor voltage waveform that I drew. Here's the volt-second balance that we just worked out. And here's a plot. This is the plot of the conversion ratio of the boost converter, which is the output voltage over the input voltage, and it's the 1 over d prime factor. At d of 0, we have d prime is 1, and the conversion ratio is 1, meaning that the output voltage equals the input voltage. And as we increase the duty cycle, this function gets larger and larger. And in fact, as d goes to 1, d prime goes to 0, and the ideal conversion ratio function heads to infinity at d of 1. Now, of course, real converters won't do that. They won't make infinite voltage. And we'll find next week that the maximum output voltage of the boost converter is limited by losses. But we haven't modeled any losses yet, and so to the extent that the converter is ideal, we can get conversion ratios that approach very large numbers. Okay, to find the DC component of the inductor current, we apply charge balance to the capacitor. So here's the capacitor current waveform. We found that it was minus the load current during the first interval. During the second interval, it is the inductor current minus the load current, and to get the average to be 0, that second interval had better come out to be a positive current. And 0 is right there. So we can find the average capacitor current, or the DC component, and by charge balance set that average current to 0 in steady state. So the average capacitor current will be d times the value during the first interval minus V over R, plus d prime times the value during the second interval, I minus V over R, and that's equal to 0 in steady state. So given that, that's this equation. We can solve this equation for capital I. Again, this quantity here is 1, and when you solve for I, you find that the inductor current DC component capital I, is equal to the load current V over R times 1 over d prime. So the relationship between the inductor current and the load current is the same 1 over d prime factor, just like the conversion ratio of the converter. We may also want to, since V is a variable, we may want to replace V with its solution Vg over d prime. Plug that in for V and you get this equation that is the solution for the inductor current DC component as a function of Vg, the load resistance, and d prime. So charge balance gives us an equation for the average inductor current, and if we're designing a converter and we need to know what the currents are, then we'll need this expression as well. Okay, we can also find the current ripple. We previously drew the inductor current waveform, and we know the slopes, so we can find delta IL, the peak to average inductor current ripple. Here's capital I, the average current is the DC current we just found. The ripple delta IL can be found from the slope. If we simply take the slope, which during the first interval is Vg over L, multiply it by the length of the interval, dTs, that gives us the peak-to-peak ripple, which is 2 delta IL. And we get this expression. We can divide by 2 and find the peak-to-average ripple, delta IL, and we get this equation, which we can use to select the inductor to get a given ripple, if we like. I would also note that the peak current in our inductor, which is also the peak current in our transistor and diode, is the DC component, capital I, plus the ripple. Generally, when we design a power converter, we want to limit the peak current to a value that our components can handle, and so we'll want to control the value of delta IL. Capital I is determined by the load current, but delta IL is determined by the choice of inductor value. So we can choose the inductance here to make the peak current be a desired value that is controlled and not too large. We can do a similar thing to find the capacitor voltage ripple. We found the capacitor current, and from the capacitor current we can that tells us the slope, and we can find the ripple on the capacitor. Okay, so what we found was that for the first interval, the capacitor current was minus the load current. So the load current will discharge the capacitor, and the capacitor voltage will go down with a slope that is the current divided by C. Okay, from here. So knowing the slope, we can multiply the slope, which is this, by the length of the first interval, which is d prime ts, and that's equal to the peak-to-peak ripple, or 2 delta V. So we can solve for delta V and find a value of capacitance then that will make the output voltage ripple be sufficiently small according to whatever specification we have. And the only thing I would add to this is that oftentimes in practice capacitors have significant series resistance. It's called equivalent series resistance. So the model for a practical capacitor, especially say an electrolytic capacitor, is this equivalent series resistance, or ESR, in series with an ideal capacitor, C. And the ripple that we've just found is the voltage ripple on the ideal part of the capacitor, but to that we have to add the voltage drop across the equivalent series resistance. So if we know IC, then you can multiply IC by the ESR and get the voltage waveform across the ESR, and then add that to this voltage ripple waveform that I've just drawn, which would be the voltage ripple on the ideal part of the capacitor. So we've done a boost converter example, and we've used the principles of inductor volt-second balance and capacitor charge balance to find the DC voltage and DC currents of the converter, and we've been able to derive the equation, for example, for the output voltage as a function of input voltage. We've also been able to derive equations for the ripples in the inductor current and capacitor voltage and use them to choose the values of the capacitance. We'll now briefly discuss two more finer points. The first one is an example of a higher order power converter. So here in section 2.4, the slides contain the full analysis of this particular converter. It's an example of a converter that contains two inductors and two capacitors. It's named after its inventor, Dr. Slobodin Chuk, and it's called a Chuk converter. And so here's the converter circuit with two L's and two C's. Here is how the switches can be realized with a transistor and diode. Okay, so the same analysis approaches that we've discussed so far can be applied to this converter as well. But you simply have to realize that since we have two inductors, we need to apply volt-second balance to each inductor, and with two capacitors, we need to apply charge balance to each capacitor. So this will give us four equations, two volt-second balance equations and two charge balance equations, and there are four things to solve: the two capacitor DC voltages and the two inductor DC currents. So we use the small ripple approximation on each inductor current and each capacitor voltage. We draw their waveforms and apply the volt-second balance and charge balance to get four equations. Now I'm not going to go through them all, but for those of you who are interested, you can look through the slides for this section and go through the volt-second balance and charge balance equations. The result of all of that is shown here, where we have volt-second balance on the two inductors and charge balance on the two capacitors. So we have a total of four equations. We have two unknowns, or four unknowns: the two capacitor voltages, V1 and V2, and the two inductor currents, I1 and I2. So we can solve this system of equations, and if we do, we get this solution for the DC voltages and currents of the converter. So the point of this example then is that you can apply the volt-second balance and charge balance techniques to more complex converters. We have to apply volt-second balance on every inductor and charge balance on every capacitor to get a system of equations that can be solved then for the converter steady state. Here incidentally is the result. This is the conversion ratio of the converter. V2 coincides with the output voltage, and it turns out that this converter has an inverting buck-boost type characteristic. We can also work out the ripples, just as in the single inductor, single capacitor case, to find equations that help us choose values of the inductances and capacitances. Okay, one other fine point is a case such as in the output filter of the buck converter, where we want to calculate the output voltage ripple on the output capacitor and choose a value for that capacitance. Okay, this is a case where there is no switching associated with the output node where the capacitor is connected. Instead, we have a two-pole LC filter, and the current in the capacitor has ripple only. And so what we've talked about so far to find delta V on this capacitor using the small ripple approximation doesn't work. To illustrate that, let's look at what is the capacitor current. Well, it's the same for both intervals. For both the first and second intervals, we have the same node equation at the output node, which says that the capacitor current IC is the inductor current IL minus the load current VC over R. So it doesn't switch. And so IL is the current coming out of the inductor. The inductor current, as we've drawn, looks like this. It has a DC component and it has some switching ripple. So first question is, where does the DC component of the inductor current go? Well, it can't go through the capacitor by charge balance. The DC component of capacitor current is 0. So all of the DC component of inductor current, in steady state at least, must flow through the load. Okay. So the DC component goes this way through the load. Now, how about the ripple? Well, in a well-designed filter where the output capacitor actually does some filtering, and then its impedance is low at high frequency. We put a large enough capacitor so that it has a very low impedance at the switching frequency and its harmonics. And so the switching ripple coming out of the inductor, which is this triangular component of the inductor current, that switching ripple will divide between the impedances of the two branches here, between the capacitor branch and the load branch. And in a well-designed filter, the capacitor will have a low enough impedance that nearly all of the ripple will flow through the capacitor, and very little will go to the load, causing ripple in the load. So a good approximation is to say simply that all of the inductor current ripple flows through the capacitor. So let's make that approximation. And in that case, the capacitor current looks like this. It's simply the same as the inductor current ripple, but with no DC component. Okay, now first of all, suppose we make the small ripple approximation on the inductor current. What that does is ignore the ripple, and in that case the capacitor current is 0, which then predicts that there's no voltage ripple. So this is not a useful approximation in this case, because the ripple is the only thing, the current ripple is the only thing that makes voltage ripple in the capacitor. So we have to include the capacitor current ripple and calculate the resulting capacitor voltage ripple. Okay, we can do that using the defining equation of the capacitor. IC is C times dVc dt. So dVc dt is IC over C, and that means that whenever the capacitor current is positive, we charge up the capacitor and increase its voltage. So here you can see for this time as drawn, we have positive capacitor current. Positive capacitor current means the slope of the voltage is positive and the capacitor voltage increases. In fact, at the zero crossing of the current, that's where the derivative of the voltage is 0, so those are the extrema of the voltage waveform. And between this minimum and maximum of the voltage, we have positive current that makes the voltage increase. So over this time, the voltage increases from here to here. Okay, because of symmetry, the voltage waveform is symmetrical, and we can again define the ripple delta V as being the peak to average, and we have one delta V there and another delta V here. So over this interval, the capacitor voltage increases by a net 2 delta V. Okay, we can find the relationship between this change, this 2 delta V, and the total charge. contained in the current waveform using the defining equation for the capacitor of Q equals CV. And in this case, over this interval where we're charging and increasing the voltage, the net change in voltage again is 2 delta V, and that's produced by a total charge that is the area under the current curve. Total charge is the integral of the current. So this total charge Q increases the voltage by 2 delta V, and we can then apply Q equals C times 2 delta V to find the relation, or to find the delta V. All that's left then is to calculate the area of this triangle, or the total charge. So the area of the triangle, we can use the area formula for a triangle, 1/2 the base times the height. The height of the triangle is the inductor current ripple, delta IL, and the base is this distance, which by symmetry is half of the switching period. So the total charge then is given by this equation from the triangle formula, the triangle area formula. We can plug that in to our Q equals CV formula and solve for delta V, and we get this expression for the delta V on the capacitor. And again, I would point out that if we have a capacitor with significant equivalent series resistance, we must also add the voltage drop in the equivalent resistance to this to get the total voltage ripple on the capacitor. So in cases where we have two-pole output filters or higher order output filters, we can't ignore the ripple, and so we have to use arguments such as this in order to calculate the ripple. This week we will cover Chapter 3, concerned with the steady-state equivalent circuit modeling of switching converters. The object here is to develop equivalent circuits that model the important functions that the switching converter performs while ignoring the unimportant things such as the switching ripple. So what we want to do is model the important low frequency, and in this case DC components, of the voltages and currents of the converter. And we'll use these models to gain insight and understanding of how the circuit and converter works, how it performs the important functions associated with these DC components of the waveforms, and we will use it to model the losses in particular and the efficiency of the converter. We'll find that by use of equivalent circuits we can gain a lot of insight as to, for example, how to develop approximations for what is important and what is not, and how to handle more complex circuits. For example, if we want to include all of the sources of loss in our model, we can refine the model and add these loss elements, which can become fairly complicated, but we can handle them in a way by manipulating the circuit that lets us easily get the answers and the insight that we need. Later in the course, we're going to refine these models to include a phenomenon known as switching loss, and even later we're going to extend the models to model converter dynamics, be able to find things like small signal transfer functions and, say, output impedances, and to design the feedback loops of these converters. Okay, so in this lecture I want to talk first about the equivalent circuit model of an ideal DC-DC converter. Okay, what are the basic properties of an ideal DC-DC converter? Well, first of all, we're going to say that an ideal converter is 100% efficient, and to begin with, we won't model the losses. Later, in the upcoming lectures, we'll refine our model and add losses in, but we're going to start with the ideal case. So if we have a switching converter with an input voltage VG applied to the input port of the converter, and what we'll call the input current IG, and if we have an output port of our converter with a voltage V with a current that we'll label I, then we can write that the input power equals the output power ideally, so VGIG equals V times I. I should add that in addition to this 100% efficiency requirement, these equations also implicitly assume that the converter operates in steady state. So for example, if there are inductors and capacitors inside the converter that can store energy, then during transients those reactive elements may store or release energy, and during the time that they're doing that, the input and output powers could differ. But in steady state, there's no net change in energy in these, or stored energy in the reactive elements, and then we get this first basic equation. Okay, the second thing we found in the last chapter was that we could solve the converters and find that the output voltage is some function of duty cycle times the input voltage. And this function of duty cycle we called the conversion ratio, M, and M is a function of D. So for the buck converter, M was equal to D, and for the boost it was equal to 1 over D prime, and so on. Okay, there's a third equation that really comes from the first two. That if you take V from equation 2 and substitute it into equation 1, then let's do it. We get VGIG on the left side of equation 1 is equal to V, which is M times VG, times the output current I. Okay, we can cancel the VGs, and what we find is that the input current IG equals the same conversion ratio times the output current I. And that's our third equation. So it says that the currents are related by the same conversion ratio except going in the opposite direction. Okay, so those are three basic equations for the converter. Now, what kind of equivalent circuit could we construct to go with those three equations? Okay, well, I'm going to actually draw that here. So we had, what, VGIG equals VI was the first one. Second one was V equals M of D times VG. And the third was IG equals M of D times I. Okay, now there's actually two different ways that we commonly model these equations with equivalent circuits. The first one uses dependent sources. So let's consider our converter with an input port having VG and IG, and its output port has voltage V and current I. And one way to model these equations is with a dependent voltage source for equation 2, which says that the output voltage V is dependent on VG with a constant or gain of M of D. So I can draw a dependent voltage source and label its value M times VG. Here in my notation, a square source is a dependent source. Okay, the third equation we could similarly model with a dependent source. The current IG is equal to this gain M times the current I. So I could write a dependent current source that produces IG and label its value M times I. So this is one possible equivalent circuit that models the important low frequency or DC voltages and currents at the terminals of the converter. One can verify that equation 1 is also satisfied. In fact, we derive 3 using 1, but VG times MI is equal to MVG times I. And we can verify from these equations that that's so. This is one way to model a switching converter, and in fact we often use this model in circuit simulators such as SPICE, which have dependent sources in them that can be easily programmed to do this. So that's approach number 1. A second approach is to recognize that these equations are actually the equations of an ideal transformer. So let's draw our terminal quantities and put a transformer between them. So a transformer has input power equals output power, at least ideally, and it also has the voltages are related by a factor which in the transformer is called the turns ratio. So we could write a transformer symbol or an ideal transformer symbol, and the turns ratio is the ratio of the voltages. So here V is equal to the turns ratio times Vg, and the turns ratio apparently is the conversion ratio M. So I can label the turns ratio here as 1 to M of D. And we know with a transformer, if we apply a voltage Vg to the primary with, say, the plus on the top, I'm going to put a polarity mark there where the plus sign of Vg is, then the voltage coming out of the transformer here will be the turns ratio times the input voltage, and it's plus at the top also, so the polarity mark goes on the top of the secondary winding. We also know for transformers the currents follow the same rules, but in the opposite direction. So here the input current Ig flowing into the dot is equal to the current on the secondary flowing out of the dot multiplied by the turns ratio. So M of D times I. Okay. So this is the ideal transformer model of a switching converter, and it's justified because it correctly describes the relationships between the terminal voltages and currents of the ideal converter. Now I should note that real physical magnetic transformers that are constructed with turns of wire on magnetic cores can't even handle DC signals. If you put a DC voltage across a magnetic transformer winding, the volt seconds won't balance and the transformer will saturate. But that's perhaps one of the good reasons to build a DC-DC converter, because we want that function. And so here what we're going to do is we're going to make sure we all understand that this is an ideal DC transformer model by putting a straight line like this through the transformer to represent DC. And we are free to invent an equivalent circuit symbol that that models these functions, and it's defined simply as being a symbol that satisfies equations 1 through 3. Okay, so we have two different ways to model the terminal equations of the ideal DC-DC converter, and they're completely equivalent. And in fact, if you find that you construct an equivalent circuit that has one of these, you can always substitute the other for it. Okay, so again, the DC transformer model is justified because it models the important physical properties of the desired waveforms of the DC-DC converter, which is conversion of the voltages and currents according to a conversion ratio M with 100% efficiency. And this is now a time invariant model that doesn't have switching. So we can replace our switching converter with this transformer model, and we then have a circuit that can be much more easily solved using the techniques of just basic undergraduate circuit analysis. So we can do DC analysis and solve for the important quantities without worrying about what's going on with the switching and the switching ripple. The only slightly strange thing here is that the turns ratio, M of D, is a function of duty cycle. So if we change the duty cycle, we can change the turns ratio at any time. And if you want to turn down the output voltage, just turn down the turns ratio. But that's one of the additional important functions that the converter can do, and it is modeled. Okay, let's do an example of using the transformer model. So here's an example of a circuit. In fact, let's do this on the graph paper as well. So let's suppose we have a switching converter, has its input terminal VG and output terminal V. And we model it with a transformer, so we will draw inside the box of the switching converter a DC transformer with turns ratio 1 to M. And let's suppose that at the input terminals of this converter we have a power source that has some impedance associated with it. So we'll model the power source with a Thevenin equivalent. So I'm going to draw V1 as the Thevenin equivalent voltage and some Thevenin equivalent resistance that we'll call R1 that is connected to the input terminal. Let's also suppose we connect a load, let's say a resistor R, on the output. And the object now is to solve for what is the output voltage. Well, the way to do this, I think the easy way to solve this, is to manipulate the circuit by pushing all of the elements through to the output side of the transformer. So we remove the transformer and then we can solve for the output voltage. So if you recall from basic circuit analysis, when you push a voltage source through a transformer, then effectively on the output or secondary terminals of the transformer, we see a voltage source of value V times the turns ratio. So I'm going to write a voltage source. The round source is an independent source. It's a value V1 times the turns ratio M. Then we also need to push the resistor R through the turns ratio. And when we push a resistance through a turns ratio, we must multiply by the turns ratio squared. So we have an effective resistance, as seen from the secondary terminals, of value M squared times R1. And that's what we get between the output terminals of the converter. Now this is driving a load R, so we'll draw R here. And we have output voltage V. Okay, now the circuit is simplified, and I think it's a straightforward matter now to write the expression for the output voltage. The output voltage V is equal to the effective voltage source, M times V1, times the divider ratio of these two resistors, which would be R over R plus M squared R1. And that's the equation for the output voltage. So the conversion ratio M affects not only the voltage source but also this divider ratio, and taken together we can solve for the output voltage. Okay, so we've derived an equivalent circuit for the ideal switching converter that models the important DC components of the waveforms and the basic power conversion functions that are performed by the converter. In the upcoming lectures, we're going to refine this model next to add in the different kinds of types of losses in the converter and build up a model, an equivalent circuit model that can be solved to find things like the efficiency. I would also note that if you found the derivation of the output voltage by manipulating the ideal transformer circuit to be unfamiliar, or if you need a brush up on how to do that, there's a supplementary lecture posted to supplement this lecture that reviews the rules for manipulating ideal transformer circuits. This brief video is a review of circuit manipulations using ideal transformers. The basic rules for ideal transformers, in which we push an element, a circuit element, through a transformer to what we call reflecting to the other side, goes as follows. If we have a voltage and we push it through a transformer that has a turns ratio of N1 to N2, then as seen between the secondary terminals of the transformer, effectively we have a voltage source whose value is multiplied by the turns ratio. So we get N2 over N1 times V as the effective voltage source is seen by from the secondary terminals. Likewise, with a current source, we can push it through a transformer also, but we have to divide by the turns ratio. So if we have an N1 to N2 turns ratio here, then as seen between the secondary terminals, we effectively have a current source, a value Y, that is divided by N2 over N1, or we can write N1 over N2 times I. And the third manipulation is if we have some impedance, we'll call it Z, and we push that through a transformer. Then we effectively see an impedance between the secondary terminals that is the turns ratio squared times Z. So we would get N2 over N1 squared Z as the effective impedance seen between the secondary terminals. One little case to be careful with here with Z is if Z is a resistor, so if we have a resistor, then effectively between the secondary terminals the value will be the resistance times the turns ratio squared. Likewise, if we have an inductor whose impedance is SL, then we would multiply that impedance by the same turns ratio squared, which is as if the inductance was multiplied by N2 over N1 squared. So sometimes we'll just simplify this to say there's an effective inductor of value N2 over N1 squared L. If we have a capacitor, recall that the impedance of a capacitor is 1 over SC. So the impedance here would be N2 over N1 squared times 1 over SC. But as far as the effective value of the capacitance, you can see that since impedance varies inversely with capacitance, this is as if we have a capacitor that gets divided by the turns ratio squared instead of multiplied. So it's as if we have a capacitor of value C that is N1 squared over N2 squared. Okay, those are the rules for pushing simple elements through transformers. Let's do an example now. Suppose we have, say, a voltage source, and let's take some larger circuit, maybe with a resistor R1, some transformer with a turns ratio, let's say 1 to NA. Maybe we have another resistor here, a value R2, and another transformer that has the dots reversed, so the primary dot is on top and the secondary dot is on the bottom of the winding. And let's give this a turns ratio of NB to 1. And what we would like to do is find the effective network with respect to the output terminals. And in fact, maybe we'll even solve for the output voltage, V out. So one good way to solve this circuit is to use these circuit manipulations and push the elements through the transformers. So what I'm going to do here is push them through the transformers one at a time. So let's start by pushing the voltage source and R1 through the first transformer. So what we will get with respect to the secondary terminals of this first transformer, we'll have the voltage source pushed through, and in the process it gets multiplied by NA. So we have N sub AV as the voltage, the effective voltage, and it's in series with an effective resistor that would be the resistance R1 multiplied by the turns ratio squared, so NA squared. That's what we see effectively between the secondary terminals of this first transformer. Okay, so then I'll copy the rest of the circuit after that. Okay, next let's push the elements through the second transformer. Okay, so here is still our output terminals. So we'll push the elements to see how they appear effectively between the secondary terminals of this second transformer. So when we push R2 through the transformer, we'll get a resistor on the secondary side, and it gets multiplied by the turns ratio squared, but here the turns ratio is 1 over NB. So effectively we would get R2 over NB squared as the effective resistance. The fact that the dots are reversed doesn't affect impedances, because the dot is like having a minus sign on the turns ratio, but the impedance changes by the turns ratio squared and the minus sign cancels out. Okay, next let's push the R1 resistor through. So we'll get an effective resistor here that is the NA squared R1, and then we have to divide by the NB squared for this impedance also. Okay, and then finally we push the voltage source through the transformer. So we have a voltage of value NAV, and then we'll divide by this NB. And since the dots are reversed, we have to reverse the polarity of the voltage source. So I'm going to draw it with minus on top and plus on the bottom. Okay, so this is the effective network that is seen between the secondary terminals of the last transformer. With this circuit now we can solve. So what is the output voltage? We can just use the voltage divider formula. So we would take the voltage source, NA over NB times V, and because the polarity is reversed, we have a minus sign. And then that voltage gets multiplied by the divider ratio of these two resistors, so it would be times the divider ratio R2 over NB squared, all over the same R2 over NB squared, plus the first resistor in A squared over NB squared times R1. So that is the solution then for the output voltage. So we've taken a fairly complex circuit and by manipulating it reduced it to something where we can just write the answer in the end. One other thing I would point out is that you do have to be a little bit careful in manipulating here. If we had wanted to solve for some other signal that's not at the output, like suppose we wanted to find this current right here, I'm going to call that IA. IA does not explicitly appear in this final circuit, and in fact when we push the elements through the transformers we have to be careful. On the second circuit, IA is this current, and what happens to IA on the third circuit? Well, when we push these elements through the transformer we end up pushing IA through the transformer also. So here's a current related to IA, but IA got pushed through this turns ratio, and the current on this side would actually be NB times IA. Okay, so we could solve this circuit for that current, but we would be solving for NBIA, and then we have to divide by NB to get back what the actual IA is. As a first example of modeling loss in a converter, let's model the resistance of the wire in the inductor of a boost converter. The resistance of the winding, or DC copper loss, of an inductor is important because it has a first order effect on the cost and efficiency of the inductor and the converter. If you don't care how large this resistance is, I can wind you an inductor that is arbitrarily small and inexpensive that can give you the desired inductance and handle the desired current without saturating. But it will use many turns of very thin wire that will have a very high resistance. So the inductor then will actually have very large loss and will burn up. So the resistance of the wire is important, and one of the important things we have to specify and design in order to optimize the cost and efficiency of our converter design. So to model this, a common way to do it is with a lumped element model as shown here, where we replace the physical inductor with a model consisting of an ideal inductor having a voltage VL in series with a resistor that is the resistance of the winding. Okay, so between these terminals, this is the model of the physical inductor. And what we do is we insert this model into the converter circuit like this, and then analyze this circuit. So here is our inductor model. Okay, the ideal part of the inductor with its voltage V sub L still must obey inductor volt-second balance. But now we have an added resistor in series in the circuit that has a voltage drop equal to the inductor current multiplied by the resistance. So we apply volt-second balance to VL of t in this model, and as usual we apply charge balance to the capacitor current, and we can get a set of equations that we can then solve for the output voltage and other quantities of the converter. Okay, so let's do it. Here's our circuit now to be analyzed. Here's the inductor voltage, or the voltage of the ideal part of the inductor model, and we'll have the capacitor current there. And as usual, we now write the circuit with a switch in the two positions and proceed to work out the waveforms of VL of t and IC of t. So with a switch in the first position, we get this circuit. We can identify what the inductor voltage is. From this loop equation, the inductor voltage VL will be equal to the input voltage VG minus the voltage drop on the resistor RL, which is IRL, like this. The capacitor current for the switch in the first position is found from the node equation at the output, and as usual, it is equal to the load current, actually minus the load current. So IC is minus V over R. We now apply the small ripple approximation as usual. So the output voltage V of t we replace with its DC component, capital V. And additionally, on the inductor, we will assume that the inductor has small ripple as well. So we will replace I of t with its DC component, capital I. Similar for the switch in the second position, we get this circuit. The inductor voltage this time is the input voltage VG minus the drop on the resistor IRL minus the output voltage V. And the capacitor current is the inductor current I minus the load current V over R. So we get these equations, and we again apply the small ripple approximation as appropriate. Okay, so here are the waveforms then. This is the inductor voltage waveform and the capacitor current waveform. Both of these must have zero average when the converter works in steady state. The inductor voltage waveform now has some additional terms that come from the voltage drop on the winding resistance. But we can apply volt-second balance to this as usual. So zero, or the average inductor voltage is 0, and it would be D times the value during the first interval, VG minus IRL, plus D prime times the value during the second interval, which is Vg minus IRL minus V. Okay, we can collect terms and equate this to 0, and we get this equation for inductor volt-second balance. Okay, in the ideal case, we were able to solve this for the output voltage and get an expression for the ideal output voltage. But now we have an added term that comes from the inductor winding resistance, and there's an added variable, capital I. The inductor current at this point is an unknown. So we have one equation with two unknowns, and we can't yet solve. So to get a second equation, we get that from the charge balance on the capacitor. So the average capacitor current must be 0 in steady state, and we actually get the same waveform and same equation as in the ideal case for the capacitor current. And when we collect terms, then we get this equation, which is a second equation that relates the inductor current and the output voltage. Okay, so when taken together, then we have these two equations. The first is from volt-second balance, the second is from charge balance, and we have two unknowns, capital I and capital V, so we can solve now to find the output voltage. For example, we could solve the second equation for I and plug the result into the first equation and then solve for V. And if you do that, here is the result, V over Vg. I've written this equation in a nice form. It has two terms. The first term, 1 over d prime, is the result for the ideal case with no loss. And the second term we can think of as a modification of how the inductor resistance affects the output voltage. And you can see that if you let RL go to 0, the second term goes to 1, and we get the ideal expression 1 over d prime. Okay, I've also written this second term in a nice form where every term is normalized, and the denominator is 1 plus a function of RL. So as RL is increased, the denominator is increased and the output voltage goes down. If you would like RL to have a small effect on the output voltage, then we need RL to be small compared to the term it's divided by, which in this case is d prime squared r. So for example, if RL was 1% of d prime squared r, then the denominator would be 1.01, and the overall second term would be approximately 0.99, so the output voltage would decrease by 1%. It's nice to write the second term in this form because we can see what to compare RL to and get a good idea then of how small RL needs to be. Okay, on the right we can see a plot of this expression, V over Vg, for different values of RL over R. The top curve is with RL equal to 0, and then we get the ideal case, that's 1 over d prime, and this function goes to infinity as d goes to 1. The lower curves are for different values of RL, and you can see that as RL increases, the output voltage goes down, as we would expect. But not only that, there's a major qualitative change, where the curve actually bends over. It reaches a maximum, and then it starts decreasing, and at d of 1, the curve goes to 0. So this is a pretty big difference. You add a small amount of RL, anything bigger than 0, and at d of 1, the curve goes to 0 instead of infinity. So what's exactly going on there? Well, we can go back and look at the original circuit. What happens in the original circuit as you let d approach 1? Well, if d goes to 1, then the switch is always in position 1 and never in position 2. So we just connect the inductor across Vg, and the inductor current is large. And in fact, with 0 RL, the inductor current tends to infinity. And the volt-seconds don't even balance. If there is some d prime interval that's greater than 0, then during the d prime interval some current will go to the output and can charge up the output voltage. In the ideal case, as D approaches 0, the average current driving the output is infinite amps times something approaching 0 duty cycle. And what is the limit? Well, the ideal equation tends to infinity, at least as approached from the left, but it's a non-physical answer. And with any amount of RL at all, the inductor current is limited to a finite value, and as D goes to 1 in any event, we get essentially 0 average current driving the output, and there's no output voltage. And so the actual case with the loss resistance is the physical answer, in which the output voltage is limited and doesn't go to infinity at D of 1, and in fact it goes to 0. Moreover, we can see that the maximum voltage that we can attain is limited by the loss resistance. So for example, suppose we wanted our converter to boost the voltage by a factor of 3. Well, if an RL over R was, if you have RL over R equal to 0.05, that's no good. It's not going to work because we can't make enough output voltage. RL over R equals 0.02 looks like it would work, and 0.01 would be even better. So the peak amount that we can boost by is a function of RL. So we've seen in this first example how we can model loss, and in this case we modeled the inductor winding loss with a lumped element model that had an ideal inductor in series with an effective resistor. The ideal inductor still obeys volt-second balance, although the total inductor model does not because of the resistor. So in general, we can model losses by adding elements to our converter and then applying volt-second balance to the ideal part of the inductor model and charge balance to the ideal part of the capacitor model. We then get a set of equations that we can solve for things like the output voltage. In the last lecture, we modeled the copper loss of the inductor of a boost converter by inserting an extra resistor in series effectively with the inductor in a lumped element model. And with that model, we then calculated the effect of this resistor on the output voltage of the boost converter. In this lecture, we're going to extend that result and construct an equivalent circuit model to go along with the equations. So here are the equations that were found in the last lecture for this example. The first equation was from inductor volt-second balance, and the second equation we got from capacitor charge balance. And the object now is to find an equivalent circuit to go along with these equations. Okay, the approach that we're going to take is to view these equations as the loop and node equations of our equivalent circuit model. And indeed, the first equation was found by finding the average voltage around the loop where the inductor is connected. So this effectively is a loop equation in our model. The second equation was found by finding the average current flowing into the capacitor from the node where the capacitor is connected, namely the output node. So we can view this equation as a node equation in our model as well. So what we're going to do is construct equivalent circuits to go with each of these equations. Okay, now in basic circuits classes, I hope you were taught how to take a circuit and apply Kirchhoff's laws to find the equations. Here we're going backwards. We're given the equations and we want to construct a circuit. Well, this process of going backwards turns out to not be unique. There's more than one way to construct a circuit that satisfies these equations. And so we have to be careful how we do it to make sure that our resulting model has physical significance. And my advice here is to use the equations in the form that they come without further manipulations. So the first equation was found from inductor volt-second balance. We should keep it as a sum of voltages around a loop corresponding to a Kirchhoff voltage law equation, and don't manipulate this. If you, for example, divided through by say R, then this first equation would have terms that have dimensions of current rather than voltage, and you might think then that this is a node equation with currents flowing into a node. While that equation might be mathematically correct, the resulting model is not physically connected to the actual converter. So we don't manipulate these equations or do any kind of algebra on them. We construct circuits to go along with the equations right away. Okay, so let's do it. I'm going to copy this equation that the average inductor voltage is Vg minus IRL minus d prime V, and we will construct a circuit to go with it. Okay, it's on the next slide, but I'm going to do it actually on some graph paper here. So our equation was that 0 is the average inductor voltage, which is Vg minus IRL minus d prime V. Okay, so this is an equation describing the loop where the inductor is connected, and it's describing actually the DC components of the voltages around that loop. So I'm going to draw a little dashed inductor in that loop. That has an average inductor voltage equal to 0. And there's a current flowing through this inductor that is the inductor current, DC component, that we've been calling capital I. Now, the average inductor voltage is 0, and in fact the impedance of the inductor at DC goes to a short circuit. So in fact, this is a short circuit in our DC model. But it's a good starting place to have a physical connection to the actual model and the actual circuit, to recognize that the current in this loop is the inductor current I, and the voltage is VL, is the average inductor voltage that is defined with a reference direction or polarity that is consistent with the direction of the current. Okay, so that is the voltage on the left-hand side of the equation. On the right-hand side of the equation, we have the input voltage Vg. So what should I draw in our loop to represent that? Well, we'll draw an independent voltage source of value Vg. And since it's on the other side of the equation, then as our current goes around the loop, and it's going from plus to minus through VL, because Vg is on the other side of the equation, our current will go from minus to plus, or with the other direction, through Vg. Okay, the next term is I times RL. That term sounds like the voltage across a resistor having current I, which is the current in this loop, multiplied by a resistance RL. So we'll draw a resistor here and label its value RL, and the voltage across it, with I going from left to right, would be a voltage from left to right of value IRL, and that polarity has the opposite polarity going around the loop as the Vg term had, which is consistent with the minus sign. Okay, the last term is minus d prime V. How do we handle this term? Well, here's how. V is the output voltage. This isn't exactly the output voltage, but it's d prime times the output voltage. So I'm going to draw for now a dependent source of value d prime V. So it's a voltage source that depends on the output voltage V, but it's multiplied by d prime. And let's see, the minus sign would mean that this voltage is plus on top and minus on the bottom. It has the same polarity going around the loop as the RL, or the IRL voltage. Okay, so here is an equivalent circuit whose loop equation is the same as the equation that we got from volt-second balance, and it is the inductor loop part of our equivalent circuit. Okay, let's do the other other equation. So the other equation was from capacitor charge balance, which said that the average current through the capacitor, or DC component of capacitor current, is 0. And what we found there was that that current was equal to d prime I minus the load current, capital V over R. Okay, this equation was found by charge balance on the capacitor, and again, basically it was found by computing the DC components of the currents going into the node where the capacitor is connected. And so we can view this as a sum of currents equaling 0, which sounds like a node equation. So I'm going to draw a node, and this is the node where the capacitor is connected, so I'll draw a dashed capacitor. So the current through this capacitor, our average IC, is 0, and we know the voltage across the capacitor is V, capital V actually, in our DC model, the DC component of the output voltage. In our model, our DC model, the impedance of our capacitor at DC is an open circuit, so this will actually be an open circuit, but for reference we know that V is the voltage at the node and IC is coming out of the node and flowing into the capacitor. So what our equation says, our charge balance equation says, is that there are two other currents flowing into the node. The first one is d prime I. Okay, so this is a current that is dependent on the inductor current, which was in our other circuit, our earlier circuit. But it's not just I, it's d prime times I, so I'm going to draw a dependent source with a current d prime I that flows into the node. Okay, and then the second term is minus V over R. So this is the load current and it is flowing out of the node because of the minus sign. We can model that as a resistor of value R that has a voltage V across it. So the resistor is in parallel with a capacitor. And that way we get a current capital V over R flowing through our load. Okay, so this is the equivalent circuit that comes from the capacitor charge balance equation. The last thing to do is to combine the two circuits together. So let's go back to the slides. When we draw the two circuits together, we get this top circuit. So the left-hand side was the inductor loop equation, where the inductor went right here. And the right-hand side was the capacitor node equation, where the capacitor went right there. The last thing to say about this is that we recognize we have two dependent sources that, as discussed in section 3.1, are equivalent to a DC transformer. So we have one dependent source, this d prime V source, depends on the voltage V across the other source with a factor of d prime. And the dependent current source depends on the current I through the voltage source with the same factor of d prime. So since the factors are the same and they depend on the voltages and currents of the corresponding sources, we can combine these into the DC transformer, as we've discussed previously. I think the easiest way to understand what the turns ratio and polarity mark should be is to look at the voltages. So we have a voltage V on the output side and d prime V on the input side of our transformer. So the turns ratio is d prime to 1, which will get us the correct polarities of voltages. And to look at the polarity marks, we look at the polarities of the voltages. So we have V is positive on the top on the secondary side, and d prime V is positive on the top on the primary side. So the polarity marks are of the same phase. We have the dots on the top in both cases. As a check, we should look at whether the currents work. So here in our model, we have a current I flowing into the dot on the primary side, and coming out of the dot on the secondary side should be d prime I, and that's indeed what the model says. So the currents are consistent with the transformer model as well. Okay, so we have an equivalent circuit now for our boost converter that has the ideal transformer, in this case d prime to 1 is its turns ratio, or if you want to call it 1 to m is 1 over d prime. And then it has an added loss resistor that comes from the inductor loss resistance. Okay, an easy way to solve this, I think, is to push the elements through the transformer. We've actually already done this exercise. We push VG and RL through to the secondary side if we want to solve for the output voltage. So when we do that, VG will be multiplied by M, or divided by d prime. RL will get multiplied by M squared, or in fact divided by d prime squared. So that's the effective circuit between the secondary terminals of the transformer. We connect that to our load resistor and recognize that the secondary voltage is V. And we can then just solve this circuit using the voltage divider formula. V would be the voltage source, Vg over d prime, multiplied by the divider ratio of these two resistors here. And if you like, you can divide top and bottom by R to write the expression in this form, which is the way we wrote the expression in the last lecture. Okay, so we found the same result as in the previous lecture, except instead of using algebra, we found it using circuits. But we can do more with the equivalent circuit than just solve for the output voltage. We could also, for example, solve for the current I on the primary side. So if you, say, push the load resistor through the transformer to this side, we'll get effectively between these terminals a resistor that would be d prime squared R. And we can then find the current. I would be Vg divided by the sum of the two resistors, like this. Another thing we can do is find the efficiency. To find the efficiency, we find the input power and the output power. So the input power is the power going into the converter terminals here, and the output power is the power coming out the output side, and the efficiency is the output power over the input power. Okay, so from the circuit we can easily write expressions for the input and output power. So the input power we can write is the input voltage Vg multiplied by the input current I. And the output power would be the output voltage V multiplied by the output current. What is the output current, or the current flowing here? Well, use the transformer. We have current I flowing in the dot on the primary, so the current coming out of the secondary will be d prime times I. So we can write that the output power is V times d prime I. Okay, that's shown here. And now we can cancel the i's, and we get that the efficiency is V over Vg times d prime. Okay, we previously found that V over Vg for this converter is 1 over d prime times 1 over 1 plus, what was it, RL over d prime squared R. So we have to take that V over Vg and multiply it by d prime. So if you multiply by d prime, the 1 over d prime factor goes away, and then this added multiplying factor is in fact the efficiency. Here's a plot of the efficiency. So for different values of RL, Actually, for different values of RL over R, we can plot a series of curves of efficiency versus duty cycle. And what you can see is that for low duty cycles, the efficiency is a lot higher, whereas for high duty cycles, the efficiency comes to some shoulder and then drops off quickly. So there's a range of duty cycles from 0 up to some value depending on RL, where we have high efficiencies, and beyond that the curve, we get low efficiencies very quickly. The efficiency drops off quickly. And this drop-off coincides with the voltage, the output voltage, deviating substantially from the ideal case, the 1 over d prime curve. So we can take our volt-second balance and charge balance equations and view them as the loop and node equations of our equivalent circuit model, and therefore we can reconstruct loop equations that go with our volt-second balance equations and reconstruct equivalent circuits that go with those. We can also reconstruct equivalent circuits based on node equations that correspond to the capacitor charge balance. And finally, we can combine these using ideal DC transformers to get a final model. This final model has a physical interpretation. We can plug this into a larger system and then model how the converter works in the larger system, and we can solve it for things such as the efficiency or do manipulations on the circuit to find things like the voltages and currents of the converter. Now let's work a second example of a buck converter containing an inductor with some DC resistance. So here's our converter. We will model the inductor in the same way we did previously for the boost converter, where we have a lumped element model of an ideal inductor in series with an effective resistor that models the winding resistance. Okay. We can go through the same procedure to work out volt-second balance on the ideal part of the inductor model and charge balance on the capacitor. And if we do this, I won't go through the details, but if we do it, here are the equations that we get. So we get this equation from volt-second balance on the inductor. It's like in the ideal case, except that it has an additional term from the voltage drop across the winding resistance. And we get this term from capacitor charge balance that is in fact the same as in the ideal case. So we got an equation from inductor volt-second balance that was D times Vg minus the inductor current times the inductor resistance minus the output voltage. And for charge balance, we got the average capacitor current, which was 0, was equal to the inductor current minus the load current. So from the first equation, we have a source, a dependent source that depends on Vg that we can write like this. Here's where our ideal inductor model goes. That's effectively a short circuit with a current I flowing through this voltage. We have now a term that is the voltage drop across the winding resistance. And then we have the output voltage right here. In the buck converter, we know that the inductor is always connected to the capacitor node, and so in fact we expect our inductor model to connect directly there. So this would be the capacitor node. And we also have our load resistor, as usual, connected across the capacitor. So here is the equivalent circuit that we get from the two equations. This model is okay as far as it goes, but there's the big question of where is the DC transformer? In a buck converter, we would expect to have a DC transformer with a turns ratio of 1 to D, equal to the conversion ratio. And here we have a voltage source that is D times VG that looks like maybe it's part of the transformer, but where is the rest of the transformer? And for that matter, where is the input voltage source VG? The problem here is that we're missing an equation that describes how the converter connects to the input terminals, or up to VG. We need another equation to describe that connection. In fact, what's happening here is that in our original converter, both inductor and capacitor are on the same side of the switch. So we don't have a volt-second balance or charge balance equation that describes the connection to the input port of the converter. And so we need to manufacture another equation that describes the input port. Okay, so we have an input port here. We know there's a voltage source VG, but we need to write an equation of what the converter does. What current does it draw out of VG? And so the way to get that is to write an auxiliary equation, or a third equation, that really tells us the DC component of IG, which is the current drawn out of VG, or drawn out of by the converter out of the node at the input port or input terminals of the converter. In general, IG is a dependent quantity. It's switched. It switches when the switch changes between positions 1 and 2. It's a discontinuous waveform. The small ripple approximation does not apply to it, but we need to sketch what IG is and express it in terms of things that have small ripple, like the inductor current, and then find its DC component to give us another equation that we can use to complete our model. Here's our converter with our IG of t. And because our switch is at the input terminal of the converter, we need another equation. See, we called the current IL. So so we can sketch IG of t. And basically, when the switch is in position 1, IG is equal to IL. So IG follows the inductor current. And when the switch is in position 2, IG is equal to 0. So IG looks like this. Okay, what we need to do is calculate the DC component of IG, or the average value of this waveform. Okay, so we follow IL during the first interval, and the first thing we will do is make the small ripple approximation on the inductor current. Again, the inductor current has small ripple and is a continuous waveform, so we can replace IL of t by its DC component, capital IL, in the usual manner, and then find the average value of this waveform, which is just d times the capital IL plus d prime times 0. So this is an equation, it's an auxiliary equation for a quantity that we need to know. It's a dependent quantity we need to know in order to complete our model. We can construct an equivalent circuit that goes with this and then append it to the rest of the model. So this equation is really the equation at the node of the input terminals of the converter. And what it says is that the current IG, which is the current drawn out, the DC component of current drawn out of VG, so I'm going to draw our VG source and label the current coming out of VG as capital IG for our DC model. and this is equal to D times IL. So it is a dependent source that is dependent on the inductor current IL elsewhere in the model, and we can draw a dependent source then, current source, and label its value DIL. When we append this to the rest of the model, now we can get a complete equivalent circuit. So here is the input port equivalent circuit that we just derived. Here is the equivalent circuit that we got from volt-second balance and charge balance. And you can see that there are now two dependent sources that can again be combined into a DC transformer. And they have a turns ratio of 1 to D. If you follow the voltages, VG gets multiplied by D to produce the secondary voltage, and the dots follow the plus terminals and are always on the top. So here is now an equivalent circuit for the buck converter that includes the DC transformer that we expect. So in general, when we have switching at one of the ports of the converter, we may need to write an equation for an auxiliary variable, in this case the node equation at the input port terminals of the converter, that gives us a complete set of equations to describe the equivalent circuit. So here we found the waveform of Ig of t. We expressed it in terms of things that had small ripple, such as the inductor current, and used the small ripple approximation on the inductor current. And we were able to express the DC component of Ig then as a function of the DC IL to get an equation that could give us the complete transformer. In general, we may have a similar situation at the output if there are switched waveforms on the output side of the converter, and we may have to do a similar thing there. Okay, so in converters such as the buck or other converters, even say a buck boost is another one, that have switching on the input port, we will in general need an equation for the average Ig. Let's work another example in which we will include the semiconductor conduction losses in our equivalent circuit model. The semiconductor conduction losses are the power losses that come from the forward voltage drops of the semiconductor devices. So what we're going to do in this example is to model a boost converter. We will again include the the winding resistance of the inductor. But now we'll also include the on resistance of the MOSFET and the forward voltage drop of the diode. So for the MOSFET, the typical power MOSFET behaves as a resistance when it is in the on state. And so an equivalent circuit that we might use for the MOSFET is an ideal switch in series with a resistor that we'll call R on. For the diode, there's multiple ways to model a diode, but if we have say a p-n junction diode, we can model it as a constant voltage drop, that is the forward voltage drop of the diode. Or if we like, we might further refine the model by adding an on resistance for the diode as well. And in fact, I'm going to call these VD and RD for the diode voltage drop and the diode on resistance. Typically we extract these quantities from the semiconductor data sheets. For MOSFETs, the on resistance will be specified, and for the diode, typically there'll be a plot of the current versus voltage curve of the diode, and from this plot we can fit a curve. So if we model the diode as a forward voltage plus a resistance, we might approximate this curve with some straight line that's valid over the intended important operating range. And so this intercept voltage would be V sub D, and the slope here would give us R sub D. The slope on these axes is actually 1 over R sub D. Okay, so for the diode then, we have this model when the diode is on. If we put it in series with an ideal switch like the MOSFET model, then we get a model that can be used in the switching converter for both intervals. So what we do is we then as usual, write the circuit when the switch is in the two positions. So what we call position 1 is when the diode is conducting and the MOSFET is off, and the circuit reduces to this, which now includes the on resistance of the MOSFET in the subinterval 1 circuit. For subinterval 2, the MOSFET is off, or its switch is off, the diode is on, and the circuit reduces to this, where now we have the V sub D and R sub D model for the diode forward drop in our equivalent circuit, or in our sub-circuit. With these, as usual, we can write the inductor voltage and capacitor current waveforms. So here, as before, VL of T is the voltage across the ideal inductor part of the lumped element inductor model, and I sub C of T is the current in the capacitor. The capacitor current waveform is the same as it has always been. So far, none of the losses that we modeled have affected that. But they all of the loss elements add terms to the inductor voltage waveform. But no matter, we can work out the average inductor voltage anyway. VL of T is D times the voltage during the first interval plus D prime times the voltage during the second interval So there are more terms, but it's a straightforward matter to write them, or to write the average voltage. And by volt-second balance, we equate this voltage to 0. For the capacitor current, since its waveform is the same, we get the usual equation for the average, or for charge balance on the capacitor. So now we construct the equivalent circuit, and I'm going to do this on some graph paper also. So here is the inductor voltage equation that we got. The average inductor voltage is 0, and it is equal to VG minus IRL when we collect terms, minus DI R on, minus D prime VD minus D prime I RD minus D prime V. So there are more terms, but we can write this equation and construct an equivalent circuit that includes an element for each term, as usual. Okay, so the first term is VG. We'll write a VG voltage source. The next term is I times RL. We recognize that as usual. It is the voltage drop in the inductor winding resistance. So we'll put a resistor value RL. The next term is minus D times I times R on. And what's new here is that there's a factor of D. So the question is, what should the element in our equivalent circuit be to correspond with this term? And I would say there are perhaps two choices we could consider. Should this be a resistor of value R on? If so, then that means that the current through the resistor is D times I. Or the other choice is that we associate D with the value of the resistor, so perhaps this should be a resistor of value D times R on that has a current of I. So what do you think is the correct answer? Well, the correct answer is that this is a resistor of value D times R on that has a current I flowing in it, and the reason is that the current in this loop, for this loop equation, is the inductor current. And if you recall in previous lectures, I've drawn a little dashed inductor to model where the inductor goes. It has an average voltage that is 0, and it has a current that is the inductor current I. So this is the loop equation that contains the voltages around the loop where the inductor is connected, and the current in that loop is in fact the inductor current I. So we have to have a resistor with a value I, and therefore the value of the resistor is D times R on. Well, so now we have an element, a resistor, whose value varies with the duty cycle, which is a kind of strange element. Why do we get such a thing? Well, the reason is that the on resistance is only in the circuit when the MOSFET is on, which is during the first interval of length that has a duty cycle of D. So for example, if we let D go to 0 and we never turn the MOSFET on, then we would not expect there to be any power loss in this resistor. And the power loss that you get is a function of the duty cycle, or the fraction of time that there is current flowing in this resistor making loss. So this model predicts that the power loss in this resistor is the current squared, or I squared, times the element value dR on. Now in fact what's happening is during the first interval we're getting a power loss of I squared R on, but we're only getting it during the DTS interval, and so the average power loss, with 0 loss in this resistor for the second D prime interval, the average loss will be the duty cycle times I squared R on. And so by changing the effective value of this resistor, the model correctly predicts the power loss in the MOSFET. Okay, let's keep going. The next element is minus D prime V sub D. Okay, so V sub D is the diode forward voltage drop in our diode model, and it is a constant voltage. I'm going to draw it as an independent source. That's the value D prime V sub D, and it's plus to minus from left to right. So the power loss in this element also depends on the length of time that the diode conducts, and the V sub D source gets multiplied by D prime. The diode resistance RD similarly is an effective value of D prime RD. And finally we have the output voltage multiplied by D prime. This is a voltage that depends on the output capacitor voltage, and we'll draw it as a dependent source, a value D prime V. So there's our circuit model for the inductor loop that includes all of the terms in the inductor equation. Okay, here is the model we just constructed. The capacitor node equation model is the same as it's been in the previous examples, at least in the boost examples. So we get this equivalent circuit as usual, and we can now combine the two dependent sources into a transformer. So here are the two models written together. We combine these sources into a transformer. We get a D prime to 1 boost type transformer, and this is the equivalent circuit model then for the converter. Here is the model that we derived, and let's solve the model now for the output voltage. The way to do this, I think that is easiest, is to push all of the elements to the secondary side and combine them together. So first of all, I'm going to combine the two independent voltage sources. Since the V sub D voltage source is in series with these resistors, we can swap the order without changing the circuit, and I can combine it with VG into one source. So I'm going to write one source that is a value VG minus D prime V sub D. Then I can combine all the resistors together. By simply adding them. So we have one effective resistor, call it RE, which is equal to RL plus DR on plus D prime RD. We have our D prime to 1 transformer and the output voltage. Finally, we can push these elements through the transformer. When we push the voltage source through the transformer, we'll multiply by M or divide by D prime. So we get an effective voltage source of value Vg minus D prime V sub D all over D prime. When we push the resistor through, we get an effective resistance as seen from the secondary side of the resistor multiplied by M squared or divided by D prime squared. So we'll get Re over D prime squared. Then we have our load resistance and the output voltage. So we can write now the expression for the output voltage from solving this circuit. It's again just a divider ratio where the reflected voltage is seen at the secondary terminals is Vg over D prime minus V sub D. And then times the divider ratio, which is R over R plus Re over D prime squared. And that's the expression for the output voltage. You can see the divider ratio again is changing quite a bit with duty cycle. All of these resistor values effectively are changing as the duty cycle changes, as does the effect of the input voltage. So here is the result that I just derived on the previous slide, and it's manipulated to make dimensionless terms. So this is writing the result in the nice form, where the first term is the ideal conversion ratio with no losses. The second term is a numerator term that accounts for the losses that appear in the numerator, and in this case the V sub D voltage drop of the diode appears in this term. And the final term is the denominator that comes from all the resistive voltage divider terms. We can work out the efficiency as well, as usual. So we find the input power going into the converter, we find the output power coming out, and the efficiency is output power over input power. The input power is Vg multiplied by the current on the input terminals, which is the inductor current I, and the output power is the output voltage V multiplied by this current coming out of the terminals, and that current is the current I reflected through the turns ratio, which gives us D prime I. So V times D prime I is the output power. So if you divide those, then the efficiency becomes equal to V over Vg times 1 over D prime, and the i's cancel out. So if we go back to our previous expression for the V over Vg, I'm sorry, not times D prime, not 1 over D prime. So if we go back to our previous expression and multiply V over Vg times D prime, the 1 over D prime term cancels, and the remaining terms are the efficiency, and so we get this expression for the efficiency. And basically we have a term in the numerator from the V sub D source, and we have all the resistive terms in the denominator. And this expression, again, because it's written in this nice normalized form, tells us really the relative effects, or the effect of each of the loss elements on the efficiency. So here, if we want the V sub D term to have a small effect on efficiency, then V sub D should be small compared to Vg over D prime. Likewise, if the on resistance R on is to have a small effect on efficiency, then R on should be small compared to D prime squared R over D, and so on. Okay, one last little point about prediction of the conduction losses using this averaged model. So we found with the MOSFET on resistance that the model effectively changes the value of R on. It gets multiplied by a factor of D. And this makes the model correctly predict the average power loss in the on resistance of the MOSFET. We should take this just a little bit further and recognize that we've also made the small ripple approximation, and so these models are ignoring the effects of switching ripple. And so we would expect the accuracy of the models to be good as long as the ripple is small, but if the ripple gets large, then the model could be inaccurate. So let's consider, for the case of the MOSFET on resistance, how does the ripple affect the prediction of loss? Okay, so here's a plot of the current in the MOSFET. This I of t here is the MOSFET current. Basically, we have a MOSFET that we're modeling with a switch that turns on and off as the MOSFET turns on and off in series with an on resistance. And there's a current I flowing in this switch. This is I is different than the inductor current. This is really the MOSFET current. And so the power loss in the on resistance is the RMS current, so I RMS squared times the on resistance. And here's what that I of t looks like. It's 0 when the MOSFET is off, and when the MOSFET is on, the MOSFET current follows the inductor current. Okay, so when we ignore the ripple, we're really drawing I of t as case A shown here, where there is no ripple. And with no ripple, I then simply looks like this. When it's on, we have a current capital I, the DC inductor current. And when the MOSFET is off, we have a current 0. Okay, and in that case, we can show that the RMS value of I for this case A is the square root of the duty cycle times capital I. Okay, so then the predicted power loss in the on resistance is this RMS current squared, so root D times I squared times the on resistance, and we get D times I squared R on, which is exactly the loss that our equivalent circuit model predicts. Now, case B and case C show examples where the ripple is greater than 0. And one can show that when ripple is included, the RMS current is this value, root D times I, and then times another factor that accounts for the ripple, and that factor turns out to be 1 plus 1/3 delta I over capital I squared. So this extra term accounts for ripple. And here is the value then of the RMS current, including ripple, for two cases. In case B, the ripple delta I is 10% of the DC current, capital I. And we would expect the small ripple approximation to be pretty accurate there. So you can compute this term and see how big the RMS current is. It turns out to be 0.167% higher than the ideal case with no ripple. So this factor here is this term right here, and it's very, very close to 1. So when you square this to find the power loss, we find that the computed average power loss is 0.33% higher than our model with the small ripple approximation predicts. 0.33% is a pretty small difference, and I think the model is very good here. In fact, the tolerance on the on resistance is a lot more than that. Case C is the extreme case shown here, where the ripple is equal to capital I. So we have 100% ripple relative to the DC current, and the actual current waveform starts at 0 and ramps up to twice the average. So in that case, where delta I equals I, we can calculate this quantity, and it turns out to be 15.5% higher, so 1.155. When you square that, and calculate the average loss, we find that there is 1/3 more loss than we predict. So even in the extreme case of ripple equals DC component, we're still only off by a factor of 1/3, and it's not bad. But when the ripple gets that large, then we know that perhaps we should account for the ripple in our computation of the loss. This week we will discuss the realization of switches in our power converters using semiconductor devices such as power transistors and diodes. And there's really three major topics that we need to discuss. The first is, when we have an ideal switch, how do we decide whether to replace it with a transistor or diode or something else in order to make it work in the power converter application? And I'm going to introduce in this lecture and the next several lectures the ideas of single quadrant, two quadrant, and four quadrant switches, and how to decide which of these to use depending on the application. The second topic is we need to talk a little bit about the real semiconductor devices. And so I'm going to discuss power diodes, power MOSFETs, and the power IGBT, or insulated gate bipolar transistor, which are some of the most popular and major power devices in use today. And I don't want to get too heavily into semiconductor device physics, but we're going to talk enough about them so that you can appreciate what are the major limitations and important features we need to think about from the standpoint of their use in power electronics. And then the third major topic is switching loss. So far we've talked about modeling conduction losses in a switching converter, but what one finds in practice is that the conduction losses are not the largest source of power loss, at least in most applications. And in fact, it's the switching loss that occurs during the switching transitions from the on to the off state and vice versa that are the largest loss in the converter. So what we're going to do is to refine our equivalent circuit models that we derived in Chapter 3 to include switching loss, and so that we'll have equivalent circuit models that include things like the diode reverse recovery and its effect on the converter efficiency. Semiconductor devices are single pole, single throw type devices. So they have two power terminals, and a transistor or a diode really acts as an on-off single pole, single throw switch like this. Now, so far in the course I've been drawing single pole double throw switches, such as this one, in which the switch is either in position 1 or in position 2. So the first thing we have to do is to replace the single pole double throw switch with two single pole single throw switches like this. And then we can realize each of the single pole single throw switches with a semiconductor power device. Now this may seem like a trivial step, but in fact it's not. That with a single pole double throw switch there are only two possible positions, whereas with the two single pole single throw switches we have two more cases. The switch can be in position 1 or in position 2 if switch A is on only or switch B is on only. But we also have the cases where we could turn both switches on or we could turn both switches off. And this really happens, and it's something we need to consider. For this particular example of the buck converter, if you turn both switches on at once, you probably destroy your switches because you short out the power source and you can get a very large current flowing around this loop that can destroy the devices or at least cause a lot of power loss. So we have to go to some lengths in our drive circuit to make sure that that never happens, even for a few nanoseconds. The other case, where both switches are off at the same time, can happen, and it completely changes the characteristics of the converter when it does. And so we're going to talk about that case in Chapter 5 and see that it leads to the discontinuous conduction mode, which is something we haven't talked about yet, but we need to. Okay, we also talk about switches with respect to how many quadrants of operation do they have to work with. And this is really imposed on the switch by the rest of the converter. So here I plotted what we're talking about. The horizontal axis is the off-state voltage imposed on the switch by the converter when the switch is turned off. So we also call this the blocking voltage, or how much voltage does the switch have to block when it is off. So the switch off-state voltage generally is determined or given by the input voltage VG, or perhaps a capacitor voltage in the converter, and we have to see whether, or maybe the output voltage, but we have to see how large that voltage is and whether it changes polarity. So perhaps it is positive at some values of duty cycle and negative at others, and that affects how we realize the switch. Likewise, the switch on-state current is the current imposed on the switch by the external converter, or by the converter itself, when the switch is turned on. Generally, the on-state current is an inductor current or some combination of inductor currents. And this can be a function of duty cycle also, and perhaps it's a function of the load current. So again, we have to see what is the on-state current and how does it vary with duty cycle. Is it, say, always positive like sketched here, or can it be positive sometimes and negative other times? So what's sketched here is the case where both the off-state voltage and the on-state current are positive, and so we say that this is in the first quadrant of this plane, and we call this a single quadrant switch for this particular example. Okay, there are many different possibilities, and these, in different applications, we may require one or more of these. So the single quadrant switch that I just mentioned is one example, and in fact, which quadrant does it have to operate in? You can see there are 4 possible quadrants, and so there are 4 ways in that sense to realize a single quadrant switch. The next case here is called a current bidirectional 2-quadrant switch, where the switch must conduct both positive and negative currents. So perhaps at one duty cycle the current is positive and at another it's negative. But it only has to block positive voltage when it's off, and so we call this a current bidirectional 2-quadrant switch. There are 2 possibilities here depending on whether the blocking voltage is positive or negative. The third example is a voltage bidirectional 2-quadrant switch, in which the switch has to block both polarities of voltage when it is off, but only conduct one polarity of current. And finally, the 4-quadrant switch is the most general case where the switch may have to do anything. It can block either positive or negative voltage when it is turned off, and it can conduct either positive or negative current when it's turned on. So this is the most complex case to both control and to realize with semiconductor devices, but there are examples, most notably AC to AC type converters that need 4-quadrant switches. Okay, so let's talk here about the single quadrant case. So here I've defined a switch, an ideal switch. I've defined a voltage across this switch with some polarity, and I've defined the current as flowing from the plus terminal to the negative terminal of the reference voltage of the switch. And so if the on-state current and the off-state voltage are of a single polarity, then we have a single quadrant switch. Further, we have what are called active switches, and in these switches the switch state, whether it's on or off, is controlled only by a control terminal, like the gate of a MOSFET or IGBT. And so if we know at any given time the conducting state of the switch by the control signal that we have applied to it. On the other hand, a passive switch doesn't have a control terminal, for example a diode, and instead its switch state is controlled by the converter waveforms that are applied to the switch. So if the converter voltage or current forward biases the diode, then the switch will be on, for example. The silicon controlled rectifier, or SCR, is a special case. it is turned on with a control signal, so the turn on transition is active, but once it's on, it behaves like a diode in which it won't turn off until the external circuit or the power converter circuit reverse biases the SCR. Okay, so here's the diode, and what I've drawn here is different than the on-state current and off-state voltage. This is the voltage versus current characteristic of the diode. And really you can think of this as the classic exponential characteristic of the diode that looks like this. And I've idealized it here to ignore the forward voltage drop and put the IV characteristic right along the axis. Okay, so when the diode is on, basically it conducts positive current, and when the diode is off, it blocks negative voltage. So in the planes that we have been drawing in the previous slides, the off-state voltage is negative, and the on-state current is positive, and so the diode operates then in this quadrant, in the second quadrant. So if we work out these quantities by solving the converter to find its voltages and currents and see what it applies to the switch, and it turns out that we get quadrant 2, then we can realize it with a diode like this. Incidentally, suppose I had defined the voltage in the other direction. I'm free to do that. We could just as well define voltage upside down, and this is an arbitrary choice at the outset. So if we define voltage that way, then we have to define current consistently as flowing from the reference positive to negative terminals. And if we did that, we would find that the diode would operate in the fourth quadrant instead of the second. So if we do our analysis of the converter and see the applied voltages and currents on our switch, and it turns out to be in this fourth quadrant, then we know we need to connect a diode in the opposite direction to realize the switch. Okay, power transistors such as the bipolar junction transistor or the newer insulated gate bipolar transistor are devices that have, if we plot the instantaneous voltage and current, they have characteristics like this. Depending on the gate voltage of the IGBT or the base current of the BJT. And so these devices, when they're on, they operate with a voltage on this part of the curve that is close to zero voltage, and they conduct positive current. When they're turned off by their control terminals, then the characteristic is here, and they can block positive voltage. On the other hand, practical transistors such as these generally are not capable of blocking significant negative voltage. And if you plot their reverse characteristic, it does something like this, and the device will break down if you apply more than a few volts of reverse voltage. So this is a practical detail in how the devices are built. So they are not capable of blocking significant reverse voltage. And basically then we can approximate the instantaneous IV characteristic of this like this. As the off state is on the positive horizontal axis, and the on state is nearly on the positive vertical axis. And so we actually have a single quadrant switch that operates in the first quadrant. The MOSFET is very similar. It's also a power transistor in wide use that has similar forward characteristics. So it can conduct positive current and block positive voltage. In addition, the power MOSFET channel is symmetric, and it can actually conduct reverse current as well. But in addition to that, the MOSFET also has what's called a body diode, that is a built-in diode that comes from shorting the substrate of the MOSFET to the source of the MOSFET. that adds an extra p-n junction that effectively acts like a diode in parallel with the MOSFET channel. And so that diode can also conduct reverse current. So in that sense, the MOSFET is a current bidirectional device. I have to add a few caveats to that, though, because the body diode in many MOSFETs is not optimized to be a good, fast recovery diode. We'll talk about that in a few lectures from now. And in fact, if the diode is slow enough and you switch it off quickly, you can actually get such high currents flowing through that diode that it will make the device fail. So there are failure mechanisms associated with turning off the slow body diode. So we have to be careful if we want to operate the MOSFET in the reverse direction. But there are significant applications today where we do that, and there are MOSFETs that are designed to have fast body diodes that can work in that can work like that. So the MOSFET is widely used as a single quadrant switch, just like the BJT and IGBT, and also there are some applications where it is used as a current bidirectional switch. So here's an example. Here's our buck converter again, and what I've done here is draw the switch in the buck converter as two single pole single throw switches. And what I want to do is illustrate now by example how to go through the analysis of those switches to decide how they must be realized with transistors and diodes. So what I've done is I've labeled them. We have a switch A and a switch B, and I've arbitrarily defined voltages across the switches. So VA I've just defined and taken as a reference direction that it's plus on the left and minus on the right. I could just as well choose it the other direction at this point, but this is how I've chosen it. Having chosen that, I define the direction of the switch current IA is flowing from the reference positive terminal to the reference negative terminal. Likewise for switch B, I'm going to arbitrarily define the voltage across switch B as having a reference direction of plus on the bottom and minus on the top. And so the reference direction for the current IB will flow from plus to minus through switch B. Now what we have to do is figure out what is the on-state voltage or on-state current imposed on each switch by the converter, and also what is the off-state voltage that the switches have to block. So let's do switch A first. Okay, so when the switch is on, so we have A is on and B is off, then you can see the current that switch A conducts is the inductor current. So IA equals IL. Now we've already solved this converter previously, and we know that the inductor current IL is the load current. So IL is the load current over R, and I mean the load voltage over R, which is the load current, and V is D times VG. So I get dVG over R is the current that the switch has to conduct. Now all of these are positive quantities. We'll assume VG is positive, the duty cycle is positive, and R is positive. It's a passive load. So that the on-state current IA is positive. Okay? So here's the on-state current of IA, and it's a positive current. When A is off, it has to, what voltage does it have to block? Well, when we turn A off, we turn switch B on. And with A off and B on, the voltage VA is equal to VG. And that's a positive quantity. So when the switch is off, it blocks a voltage VG. So the on-state current and the off-state voltage are both positive. We're in quadrant 1, and therefore with quadrant 1 we can realize the switch with a transistor, say an IGBT. Okay, so with an IGBT there, it will block positive voltage and conduct positive current, which is how it's designed to operate. Okay, let's consider switch B next. When switch B is turned on and switch A is off, what current does it have to conduct? Well, with switch B on and switch A off, you can see that IB equals IL. And the defined polarities of IB and IL are the same in this case, and so this is a positive quantity, and we're conducting positive current. When switch B is off, then we have switch A is on, and switch B has to block VG. But be careful, the way we define the direction of VB, VB is actually minus VG, which is a negative quantity. So I have to block negative voltage. Okay. So in this case, we have a positive current, on-state current, a negative off-state voltage. We're in the second quadrant, and that's a diode. Okay, so switch B must be realized with a diode. Now you can see here also that the choice of switch isn't arbitrary. I couldn't put a diode at switch A or a transistor at switch B, at least not an IGBT or a BJT, so we have to realize the switches correctly. But by doing this simple exercise, we can follow in a systematic way to see exactly how to realize the devices. So here's a summary then. I put a BJT for switch A and a diode for switch B. Okay, in the next lecture we're going to consider two-quadrant switches and see some examples where they're needed. In this lecture we'll talk about current bidirectional switches. So here is a realization, one way to realize a current bidirectional switch. So this is a single pole, single throw switch that is actually a transistor connected with what we call an anti-parallel diode. The combination of the two is able to conduct current in either direction. So if we have our I of T switch current is positive, it can flow through the transistor, and if it's negative, it can flow through the diode. And of course, we could use a bipolar transistor here, or we could use a MOSFET or IGBT or other single quadrant switch. So the combination can conduct current in either direction. However, it can only block voltage in one direction. So when we want the switch to be off, if it blocks a voltage that is positive, so plus to minus in this direction, both devices can be off. But if we reverse the direction of the voltage, you can see that the diode will turn on and short out the voltage source. So this combination is capable only of blocking one polarity of voltage, and so it's what we call a two-quadrant switch that is current bidirectional. Okay, so formally, here is the single quadrant switch with the voltage and current directions defined. The combination of transistor and diode have this composite IV characteristic, and as far as the plane of off-state voltage versus on-state current is concerned, we can operate anywhere in the first quadrant or the fourth quadrant. And of course also, if we want to build a current bidirectional switch that operates in only the second and third quadrants, all we have to do is connect our transistor and diode up backwards. Just define things going in the opposite direction, and we'll get the second and third quadrant. The MOSFET, I mentioned in the last lecture, is in fact a current bidirectional switch. So the MOSFET channel itself can conduct current in either direction, and in addition it has this built-in body diode that can conduct negative current. And so the MOSFET by itself can be a current bidirectional two-quadrant switch. I also mentioned that the body diode of practical MOSFETs may not be a very good diode. So if we have a slow body diode, we might not want to let it conduct and have to switch it off because of its slow switching time. So what one can do if you really have to is to put an external diode in series with a MOSFET that only lets current flow in the positive direction, and then put an external anti-parallel diode to get a current bidirectional switch. We generally don't like to have to do this, and if we're in that situation, we really have two other choices. One is to buy a MOSFET that has a very fast and good body diode, and especially at low voltages this is a good solution. Or at high voltages, the other option that we have is to use a different kind of device, such as an IGBT, and nowadays you can get good IGBTs that are co-packaged with fast anti-parallel diodes built in. Here's an example of a two-quadrant switch application. So this is a simple inverter. We have split DC input voltage. So we have plus VG coming into our converter here. This is ground or 0 volts, and we have minus VG there. And net, this is a DC input to the converter. And then we have a load, and we want to produce AC across this load, and this node here is connected to this ground. So each of these is a two-quadrant current bidirectional switch. If we succeed in producing an AC output, then the current in our load is AC and can go either direction. And that will coincide with the inductor current. So our inductor current can go either direction as well. That means that our switches, when they're on and conduct the inductor current, must be able to conduct either polarity of current. So they have to conduct the AC output current. On the other hand, the switches block the DC input voltage. So for example, if the top switch is on and the bottom switch is off, then this node gets pulled up to plus VG, and the voltage across the lower switch will be plus VG minus minus VG, or 2VG. But it's DC, and since our DC input voltage doesn't change polarity, we only have to block positive voltages with this switch. So a current bidirectional two-quadrant switch will work. And in fact, current bidirectional two-quadrant switches are commonly used in inverter applications. Let's work out exactly how this converter works. So let's sketch the voltage at the switch node. So when the upper switch is turned on, Q1 is on, then this node gets pulled up to plus VG. And we leave it on for some duty cycle or some first interval length. Then we switch the upper devices off, turn the lower devices on, and that pulls this node down to here, which is minus VG. And we'll leave them in the lower position for the remainder of the switching period for D prime TS. And then we repeat. They're supposed to be straight vertical lines. Okay, so the average value of this waveform, or DC component, or at least the low frequency component, is equal to D times the voltage during the first interval plus D prime times the voltage during the second interval. And you can work that out then. It's equal to VG times D minus D prime d prime is 1 minus d, so we can also write this as Vg times 2d minus 1, which is what's shown here. So this low frequency component of this waveform gets filtered out by the LC filter, and that's what's applied across our output load. Here's a plot of that function. You can see if d is a half, the function goes to 0. So we have 0 net output voltage at duty cycle of a half. And if you increase the duty cycle above a half, we get positive voltage. And when we decrease the duty cycle below a half, we get negative voltage. And the overall conversion ratio function looks like this. So what you can do is you can vary the duty cycle about a half. Say, vary it sinusoidally like this. Okay, and if you do that, what happens to the output voltage is that the output voltage will vary sinusoidally about 0. So if you plug this function into here, you can find that the output voltage is sinusoidal. So we vary the duty cycle sinusoidally. If we wanted to make, say, a 60 Hertz output, we could make this this modulation frequency of the duty cycle be 60 Hertz, and we would get a 60 Hertz AC output. The inductor current, which is the load current, will also vary sinusoidally in the same way. So again, it's positive or negative depending on which part of the sine wave we're on, and so we need current bidirectional switches. Here's a three-phase version of the same circuit. Each of the three phases here is one of those circuits we just talked about, so it has our current bidirectional switches and an inductor driving one phase of the three-phase output. So here's the three-phase AC load. So we vary each of these phases, or vary their duty cycles sinusoidally in a three-phase manner. So they're 120 and 240 degrees shifted in phase to get a three-phase AC output. And with this we can get, by varying all three phases in this way, generate a three-phase AC and drive an AC load, such as, say, a motor, an AC motor, or even build an inverter to connect to the utility here. So again, the switches have to block the DC input voltage, and they have to conduct to the AC output current. So this is fundamentally a two-quadrant current bidirectional application. Here's a DC-DC application of the same thing. This is basically a buck converter, where our input voltage here, Vg, is some bus voltage, and one example is a spacecraft power bus. And in this case, the load resistor is replaced with a battery, and there may be a filter capacitor here or not. But this is basically a buck converter, except that what we were calling the resistive load before now is a battery that can both store energy or supply energy. So when we charge the battery, we have power going this way. So it comes out of the source. This actually works like a buck converter, and if you just draw transistor Q1 and diode D2 here and ignore the other two devices, you would recognize this as a buck converter that we've already talked about. In this case, you don't have to turn Q2 on, but in fact it doesn't hurt to turn Q2 on anytime Q1 is off. So we can actually drive Q2 with a complement of the gate of the base drive of Q1. If we want to supply energy out of the battery back to the bus, we reverse the direction of current. And in that case, Q2 and D1 are the ones that conduct. And again, we can turn on Q1 whenever Q2 is off and just continue to drive Q1 with a complement of the Q2 drive signal. Operated together, we simply have current bidirectional switches that can conduct current in either direction, depending on whether we're charging or discharging the battery. This is one circuit that is popular on some spacecraft. They have, say, DC power supplied by solar panels, but when the spacecraft is eclipsed, say in Earth orbit, it's eclipsed by the Earth and we don't have sun, then we need to supply power to the spacecraft from the batteries, and so we need to both charge and discharge the batteries. So we can build current bidirectional switches basically as a parallel combination of a transistor and a diode. We call it an anti-parallel diode. This is basically taking two single quadrant switches and putting them in parallel so that they can conduct current in either direction. Let's continue our discussion of switch applications to talk about voltage bidirectional two-quadrant switches and four-quadrant switches. So another possible function that a switch must perform is the ability to block both polarities of voltage when the switch is turned off. And so this is a voltage bidirectional function for a switch. We can build a voltage bidirectional switch by putting two single quadrant switches in series, one of which blocks positive voltage when the switches are off and the other which blocks negative voltage. So here is one well-known way to do it, in which we put a diode and a transistor in series. So if the voltage is negative and we want the switch to be turned off, so if we have negative to positive, in this case, the transistor isn't designed to be able to block any significant amount of negative voltage. However, the diode in series will be reverse biased when the voltage is in this direction, and so the diode will turn off. And even if the transistor breaks down from having too much voltage across it, the diode will still be off, and it will prevent any current from flowing. So effectively, the diode performs the function of blocking the voltage when the voltage is in this polarity. With positive voltage across the switch network, we can block this voltage by turning off the transistor, and then it operates in the normal fashion when it's turned off to block the voltage. So the diode in this case will be forward biased, but still no current will flow because the transistor will block. On the other hand, as far as conducting current, you can see that this switch really only is designed to work with positive current when it's on. If the current reverses polarity, of course the diode will become reverse biased and turn off, and with reverse polarity the transistor in general isn't designed to conduct reverse current either. So we can only have positive current, and so this is a two-quadrant switch in which we can conduct conduct positive current only, but block either polarity of voltage. Another well-known device that can function in this way is the silicon controlled rectifier, or SCR, which is able to block reverse voltage or positive voltage if it's not triggered, but it can conduct current in only one direction. So then, here's our ideal switch. The IV curve of the composite connection of semiconductors is this, where we can be anywhere on the horizontal axis when the transistor is off, and we can be on the positive vertical axis when the transistor is on. So this switch will work in quadrant 1 and in quadrant 2. And of course, if you need a voltage bidirectional two-quadrant switch for quadrants 3 and 4, you just need to connect the transistor and diode in the opposite direction to get it to conduct current in the other direction. There are examples of the need for voltage bidirectional switches. They aren't as varied as the current bidirectional case. Here is one that it's a DC to three-phase AC inverter that is based on the buck-boost converter. And the left-hand side looks like a buck-boost converter, where the inductor is connected to VG during the first interval by turning this transistor on. During what we normally call the D prime interval of the DC-DC version of the converter, here is actually divided into multiple intervals, and what you do is you take the energy that was stored in the inductor during the first interval and you release it to the output by connecting different combinations of these switches, or turning them on. So for example, if you turn this one on and this one on, then the inductor current will flow this way. It'll charge this capacitor and flow that way. By controlling the relative amounts of time that these different switches are on the output side, we can control the amount of current that we send to each of the three phases and synthesize output sinusoidal waveforms in that manner. I'm not going to go into that in great detail. It can get complicated. But basically we can build a DC to three-phase AC inverter that synthesizes output side current waveforms that are sinusoidal. A perhaps more well-known converter that is similar to this one is called the current source inverter, and we can view that one as being derived from the boost converter. So basically, instead of this part of the circuit, we replace it simply with a DC source and an inductor, and connect it here. This inductor has a current with small ripple, and that current is again switched to the different three-phase outputs to synthesize output sinusoidal current waveforms. So that's based on the boost, and it's called the current source inverter. It's a well-known inverter circuit, and it requires these voltage bidirectional switches as well. The reason we need voltage bidirectional switches is that these switches have to block the output line-to-line voltages. And since the output voltages are AC, they have to block either polarity of voltage. On the other hand, if power only flows in one direction, then the inductor current is always of one polarity, and that current is what the switches have to conduct. So a unidirectional current flow type switch is appropriate in that case. Okay, the most general kind of switch is the 4-quadrant switch. And here we have a switch that's capable of blocking either polarity of voltage and conducting either polarity of current, so it can work at all four currents, in all 4 quadrants. This essentially has to be an active switch that is controlled by a control terminal. There's some exceptions, but in the general case it is active. And you have to be careful what you wish for, because it can be complicated to control the switch to turn on and off at exactly the right time. We don't have a diode that will turn on or off when in coordination with some other switch in the circuit. Here are some ways to realize a 4-quadrant switch. This first one involves taking 2 voltage bidirectional switches that are 2-quadrant and putting them in parallel. So each of these switches here can block either polarity of voltage, and the left side switch conducts positive current and the right side switch conducts negative current. So together they can conduct either polarity of current. The second case here involves 2 current bidirectional switches that are put in series. So each of these can conduct either polarity of current, but the top one can only block positive voltage, while the bottom one can only block negative voltage. But when you put them in series, they can block either polarity of voltage. And then the third case is not derived from any of the previous configurations. Basically, these diodes connect the transistor up in either direction as appropriate to conduct current in the right direction. And when the transistor's off, the switch network will block either polarity of voltage. The most commonly used version here when we need 4-quadrant switches is the first one. And the real reason for that has to do with how we coordinate the switching, turning off one 4-quadrant switch and turning on the next one. it's easier to coordinate that switching with this network than with the other two, but that's beyond the scope of what we're going to talk about. But just to give you an example, here is a well-known converter that uses 4-quadrant switches. This is called a matrix converter, and it converts 3-phase AC into 3-phase AC of a different frequency and voltage. And basically it takes 9 4-quadrant switches. And these switches are able to produce output voltage waveforms of these 3 nodes here that are different combinations of the input voltage, the 3-phase input voltages. And by pulse width modulating or quickly switching these devices, we can actually make the average values of these output voltage waveforms be controlled. So we can actually synthesize switched waveforms here whose low frequency components have a different frequency and amplitude than the input. These require 4-quadrant switches because the switches have to block the line-to-line AC input voltage, which is AC, and they have to conduct the 3-phase AC output current, which is also AC, so we need the most general type of 4-quadrant switch. This is a pretty interesting converter, but it takes some extended time to understand how to control these switches and synthesize the waveforms, and it can get pretty complicated. Okay, I want to talk also just for a minute about synchronous rectifiers. We've talked about the idea that a MOSFET is inherently a current bidirectional switch, and this property can be used in what is called a synchronous rectifier application, where we replace a diode with a MOSFET and take advantage of this reverse current capability. So if we need a single quadrant switch that turns out to be a diode type characteristic, what we can do is take the diode in this polarity and replace it with a MOSFET here, in which the current goes what is normally considered backwards, from source to drain instead of from drain to source. So with a MOSFET connected backwards, its IV instantaneous characteristic looks like this. Basically, I've just flipped the voltage axis because, in fact, I flipped both axes because we've connected the MOSFET up backwards. And what we do is we take advantage of this part and this part of the instantaneous IV characteristic to get a characteristic that works like a diode. Now, to get this to happen, you have to have some control circuit that drives the gate as needed to make the MOSFET turn on and off when the diode would have turned on and off. But we can build a circuit to do that and get the MOSFET to work like a diode. Now, why would you want to do that? Well, the celebrated application of this, it was the original application I'm aware of, was in low voltage computer power supplies. And the trend for decades in computer power supplies has been that the voltage goes down and the current goes up as time passes. And we now have processor chips with gate lengths of tens of nanometers, and what happens when the gate lengths are scaled down is that the voltage of the power supply has to scale down as well. At the same time, we're increasing the number of transistors on the chip, which makes the current go up. And so what's happened in the computer business is that we need power supplies that are a fraction of a volt and tens of amps or hundreds of amps even, depending on the size of the system. So how do we build a converter that can operate with high efficiency and produce such low voltages and high currents? Well, in the chapter 3, we looked at modeling these converters, and what we found was that the diode forward voltage drop appeared in our model and was a source of conduction loss. And so if we have a diode with a forward voltage drop of, just to pick a round number, 1 volt, and our output voltage is less than a volt, then we're going to have a lot of power loss in the diode. And nowadays the diode power loss, or just conduction loss, may be greater than the power that goes to the load. So we don't have a high efficiency system. And the forward voltage drop is something that is hard to scale. We can't just buy a larger diode chip and get the voltage to go down. There are Schottky diodes. Low voltage Schottky diodes may have a forward drop of say 0.4 volts instead of 0.7 or 1 volt, but even then we want to get the voltage drop of our switches to be below 1/10 of a volt to get good efficiency. So the solution is to put a MOSFET here where the forward voltage drop is dependent simply on the on resistance and the current. And so if you buy a bigger MOSFET, you can get a lower on resistance. And if you're willing to pay, you can buy as big of a MOSFET as you want and get as low of an on resistance as you want and make the forward voltage drop be low so that you can get high efficiency. And so that's what's done. So we have our main MOSFET that is the normal MOSFET of the buck converter here. And then we replace the diode of the buck converter with a synchronous rectifier, and we basically drive the synchronous rectifier with a gate drive signal that is the complement of the gate drive signal of the main FET, so that when the main FET turns off, the synchronous FET turns on, and vice versa. There's actually a little bit of dead time there where we make sure that we don't have the case where both FETs are on momentarily at the same time and shorting out VG. So this is useful in low voltage, high current applications, and we find nowadays that even at applications of tens of volts, below 100 volts, I would say, the synchronous rectifier will lead to higher efficiency. And so we find it used quite a bit in applications at below 100 volts where we're concerned with the efficiency. For the next several lectures, we're going to discuss power semiconductor devices. So we will cover some of the most widely used devices currently in power electronics, specifically power diodes, power MOSFETs, and the insulated gate bipolar transistor, which is an evolution of the bipolar junction transistor. Some of the things we're going to talk about, first of all, we're going to talk about this basic trade-off that's important to power electronics, the trade-off between the on resistance or forward voltage drop of the device versus its breakdown voltage versus its switching times. And these different devices have different trade-offs between these three figures of merit. We'll also talk about minority carrier versus majority carrier devices and how they lead to different trade-offs. And then the other thing we really want to understand is, from a power electronics standpoint, is switching times of these devices, where the switching times come from, how they work, and how they lead to switching loss, which is one of the important loss mechanisms in power converters that we haven't yet modeled. And so another objective here is going to be to extend the equivalent circuit models of Chapter 3 to include switching loss, and we'll talk about how to do that as well. Now, I don't want this to become a course in semiconductor device physics. The assumption here is that you have been introduced to semiconductor devices in an electronics class. My intention is to perhaps remind you of some of the introductory basics and then discuss at a high level the important things that happen in these devices from a power electronics standpoint. So we want to build power switches effectively out of semiconductor devices. And what this means is that the power switch must be able to change between the off state and on state. And another way to say that is the off state is an insulating state in which the device does not conduct current, and the on state is a conducting state where we have mobile charges that can conduct current, and we need to be able to switch between the two. So here's a diagram of some kind of device where we have contacts on the two sides that are, say, metal contacts to the outside world, these blue regions, and the clear region in the middle is our switching device. To to be an insulator, what that really means is that there are no mobile charges inside this insulator that can move and conduct current between the two contacts. So if we connect a voltage across this device, there will be no current because we have an insulating element in the path. Conversely, in a conductor, we have we have mobile charges in the conducting material that can easily jump from one atom to the next and conduct current. So, for example, in the classic metal material, the electrons are thermally excited to higher energy states where they're easily able to jump from one atom to the next and conduct current. So in that case, if we place a voltage across the conductor, then what we see is that we'll get a current to conduct. So here the plus charges are really the charges in the nuclei of the atoms, and the minus charges are electrons that are mobile and easily able to jump from one atom to the next. So the plus charges stay fixed and the minus charges move. Now in this drawing, another thing we can say is that there are no big fields coming out of the conductor. The number of plus charges and minus charges is the same, so that overall the conductor is charge neutral. We simply have charges hopping from one atom to the next, and every time an electron leaves the left side, another one comes in on the right side, so that we're charge neutral. So if we say Q minus is the total amount of mobile electron charge, or the charge contained by all the minuses in this volume, and we have what we call a transit time, which is the time it takes your average electron to get from one end to the other of this conducting device, then we can say that the total current, the average current, is the total amount of charge divided by the time it takes to move across the material. Okay. Also, again, since the fixed positive charge is equal in magnitude to the fixed negative charge, another way to say that is that the current is equal to the plus charge divided by the transit time. So these are basic ideas that we call charge control ideas of how a switch will conduct. Another thing to say about the conductor. In a semiconductor material, the basic pure silicon is mostly an insulator. However, we can dope the silicon with impurities in the crystal lattice of the silicon that provide charges that can become mobile. So by doping the silicon to make it N-type silicon, there are extra electrons in the lattice of the silicon, and at room temperature they're in thermally excited states where they are able to easily jump from one atom to the next and conduct electricity. So it's similar in that case to the conductor. And in p-doped silicon, we actually can dope the silicon with impurities in which there is a deficit of electrons, and actually we have what are called holes that are essentially an absence of an electron that can also jump from one atom to the next, and effectively it behaves as if there is a plus charge that we call a hole that can conduct current. Yet another case is a minority carrier, where if we have some N-doped silicon next to, say, p-doped silicon, in the N-doped silicon the electrons can diffuse into the p-doped silicon, where they are electrons at a high energy state in the p-doped silicon, and these are called minority carrier electrons, and they can also conduct current. Likewise, we can have minority carrier holes. Okay, let's discuss the MOSFET now. In the MOSFET we have a source and a drain that are doped silicon, and there are contacts to the source and the drain to the outside world. we have a channel in between the source and drain that is where we can turn the device on and off by putting charge in and out of the channel to provide a conducting path between the source and the drain. The gate in a power MOSFET is polysilicon. It's basically a conducting material that is a control terminal of the MOSFET, and separating the gate from the channel is what we call an oxide layer. It's silicon dioxide that is glass, and it is an insulator. And so basically the gate and gate oxide built on top of the channel form a capacitor. And so the gate and the channel are the two plates of the capacitor, and the oxide layer is the dielectric of the capacitor. So right now I've illustrated the MOSFET in the off state. There is no charge in the channel to conduct current between the source and the drain. So if we apply a voltage between the drain and the source, this is an in-channel MOSFET I've shown. So when we put positive voltage on the drain with respect to the source, we get no drain current because the channel is turned off. Okay, to turn the MOSFET on, we apply positive voltage to the gate, and effectively we charge up the capacitance between the gate and the channel. So what's happening here is you can see the plus charges actually come in from the gate, minus charges come in from the source, and charges up this capacitance of the gate to the channel. And the minus charges now are in the channel, inhabit the channel, and they're able to conduct between the source and the drain. Okay. I should mention that what you just saw with the charges coming in was the turn-on switching time, the time it takes the gate driver to supply this charge through the gate and establish charge in the channel is the turn-on switching time. And during that time we have a current coming in from the gate driver, a gate current, that is supplying this charge. So it's supplying the plus charges to the gate, and we get minus charges, equal number of minus charges from the source, and there's a current then that is the change equal to the change in charge on this capacitance. Okay, once the device is turned on, we don't need to supply any more current. We have a capacitor, it's turned on, and its voltage doesn't change any further, then we don't need to have any gate current, and the gate current can go to zero. So now, with the capacitor charged up, these electrons can conduct current between the source and the drain. So with a voltage applied to the drain, we will get electrons flowing between source and drain, and the drain current then we can say is equal to the total amount of minus charge in the channel divided by the transit time, which is the time it takes an average charge to move across the channel. Okay, since the plus charge on the gate equals the minus charge in the channel, another way to write the drain current is that it's equal to the plus charge on the gate divided by the transit time. So the drain current is effectively controlled by the charge that we put on the control terminal or on the gate. Okay, now let's turn it off. So here I've shorted out the gate to the source, which shorts out the capacitance, and it draws the charge back out of the gate. So that was the turn off switching time that you just saw, and the turn off switching transition. So we have gate current now that is extracting the charge, the plus charges out of the gate, so it's a negative current. The channel charges went to the drain, and the drain current continued to conduct until all of the charge was gone, and after that then the drain current goes to zero. So the turn off switching time is the time that it takes to remove all of this charge. Okay, a bipolar junction transistor has a similar looking structure with an emitter and a collector that are for an NPN transistor. They're in-doped silicon that is connected through contacts to the outside world. And instead of a channel, we have a base region that is P-type silicon. There's a contact there that's the control terminal or the base terminal of the BJT. Here, effectively, the base emitter junction, which is a diode junction, is controlled by the base terminal, and in this way we can control the charge in the base and control the current. So here there is no charge in the base, the BJT is initially off. If we apply a current to the collector, nothing happens, we're in the off state. Okay, to turn the BJT on, we forward bias the base emitter junction. So we apply a positive voltage to the base that is sufficient to forward bias this diode junction, so say plus 0.7 volts or so. When we do that, electrons from the emitter, the in region of the emitter, will diffuse into the base and become minority carriers. Likewise, positive charges or majority carrier holes will come in from the external base driver circuit and come into the base region. Okay, so during this turn on switching time of the BJT, we have positive current flowing into the base that is supplying the holes into the base region. We likewise have equal number of electrons diffusing across the diode junction to become minority carrier electrons in the base. Okay, so we now have our electrons in the base, and they're able to conduct current between the collector and emitter. What I should say though is once we have supplied these minority carriers, to first order we don't need any more base current. Just like the MOSFET, we've supplied the charge to the base to provide conducting or carriers that can conduct current, and so to first order the base current can go to zero at this point. To second order, we have an effect with minority carriers called recombination, where these electrons are in a higher energy state in the base, and they can actually decay out of this energy state. And that's called recombination. So effectively, when they decay, the minority carrier electron combines with a majority carrier hole, and effectively the charges go away. So if we want to maintain our minority carriers in the base region, we have to supply base current to basically supply more carriers to and counteract the recombination. So to second order, we can say that we need a current supplied from the base that is equal to the amount of charge divided by the lifetime, where the lifetime is the average time that it takes a minority carrier to decay and go away. So this is a maintenance current, but it's smaller than the current that we initially had to turn the device on. Okay, having said that, if we apply a voltage to the collector now, then the BJT will conduct. And so we have our electrons that are able to conduct across the base into the collector and provide current. So just as in the previous examples, the current that we get is equal to the total amount of electron or minus charge in the base divided by the transit time, which is the time it takes to get across the base. And since the minority carrier electrons are equal in magnitude to the majority carrier holes, we can say that there's that the current is equal to the total amount of holes or plus charge that came in from the base terminal and is still there in the base divided by the transit time. Okay, let's turn the BJT off now. So to turn the BJT off, one thing we could do is simply remove the base current and wait for the electrons to go away or recombine. But that may take a long time and lead to a long switching time. So a better way to do it, and I'll show it to you again, is to reverse the direction of voltage on the base and actively remove the charge. So if we actively pull the holes or these plus charges out of the base, we can turn the bipolar transistor off faster. So here we put a negative voltage on the base and actively remove the charge, and that was the turn off switching time, or the time it took to remove the charge between the base and collector. Again, this is a charge controlled device like the other devices. By pulling the plus charges out of the base, we can get the minus charges to go away also, and then the device stops conducting. So now we're back into the off state, or the insulating state, where we have no minority charge in the base available to conduct current between the collector and emitter. Okay, so I've introduced the notions that we have charge-controlled power semiconductor devices, and the time that it takes to insert or remove the charge necessary to make the device conduct or insulate is a switching time. And so it takes time to do that. Now, switching time leads to switching loss, because during these switching transitions, the semiconductor devices are not all the way on or all the way off, but they actually have voltage across them and current through them that leads to high instantaneous power. So let's look at that. Here is a first attempt at explaining switching loss, and we're going to refine this several times in the upcoming lectures, but this is a good starting point. So let's suppose we have a buck converter built here with a transistor that has some switching times, and we have an ideal diode. Okay. Now, our real diode is not ideal, but after we talk about diodes, we'll talk about how the diode affects the switching time. But for now, let's call it ideal. And we have a transistor that is driven by some gate driver circuit, and it takes time for the gate driver to turn the transistor on and off. So here's an example of the turn-off transition of the MOSFET. So we start out with a MOSFET on right here. Okay, so by being on, the voltage across the MOSFET is essentially 0, and the current through the MOSFET is the inductor current, IL. Okay, during this time, what's happening on the diode is that the diode is off. It is reverse biased, and the diode voltage is minus VG, like this, and the diode current is 0, which is shown here. Okay, the bottom waveform here is the instantaneous power in the transistor, or in the MOSFET. So it's the product of the MOSFET voltage and current. I'm not modeling forward voltage drops or conduction losses of the MOSFET right here, so initially with the MOSFET all the way on, we have 0 power loss in the MOSFET. Okay, at this point, right here, the gate driver starts to turn off the MOSFET. Okay, so it starts, the gate driver voltage goes low or goes negative, and it starts to pull charge out of the gate of the MOSFET, out of its capacitance, and discharge the gate capacitance to remove charge from the MOSFET. And that takes some time. The gate driver has some Thevenin equivalent impedance, so there's some resistance. We get RC circuits effectively, and it takes time to discharge the gate. Okay, so we start to turn off the MOSFET. Now, the thing about turning off the MOSFET here is that the current in the MOSFET can't change until the diode turns on. If you look at this is called a clamped inductive load. We have an inductor that's large and has small ripple. Its current doesn't change very quickly, and the inductor is connected to this node, and its current has to come from somewhere. And if the diode is off, the only place it can come from is the MOSFET. So what happens is that initially the voltage on the MOSFET rises like this. The gate driver is actually discharging the gate to drain capacitance of the MOSFET during this time. We'll talk about that more in an upcoming lecture. But as long as the voltage across the MOSFET is less than VG, the diode is reverse biased, because the diode voltage, VB, is the MOSFET voltage minus VG. And so the diode voltage is starting out at minus VG, and as the MOSFET voltage increases, the diode voltage increases, and finally, at this point where the MOSFET voltage equals VG, we finally get that the diode voltage starts to exceed 0 volts and the diode can turn on. So that's what happens right here. Okay, so the diode starts to turn on right there. At that point, the current from the inductor can shift from flowing through the MOSFET to flowing through the diode. And during this time, the MOSFET current will fall. And how fast it falls depends on how fast the gate driver can remove charge from the channel and the gate capacitance of the MOSFET, so the gate to source capacitance. And so that takes some time. And during that time, then the diode current increases and the MOSFET current decreases. Finally, right here, the MOSFET is all the way off with no current and with blocking the full input voltage VG. And so after that, we have 0 current in the MOSFET, and the diode conducts all of the current. Okay, so here is a plot of the instantaneous power in the MOSFET. And at this point, it starts to rise above 0 because we have voltage across the MOSFET and current through the MOSFET. And it reaches a peak right here where the MOSFET voltage is maximum and equal to VG, and the MOSFET current is still equal to the inductor current. So we get a peak instantaneous power equal to VG times the output current, or the inductor current. And that's a considerable amount of power in the MOSFET. After that, the current goes down again until at this point the power gets to 0. So we have some high instantaneous power loss. And in fact, the energy that's lost is the integral of the power. So if you find the area under this curve, you get the energy in joules that is lost during the turn-off switching transition. As drawn here with straight lines that are idealized, we could say that that energy is the area of this triangle. So it's 1/2 the base times the height of the triangle. The height is VG times the inductor current. Here's the half. And the base is the switching time. It's total time from here to here. Okay, so every time we turn the MOSFET off, we get that much switching loss. Now we multiply that by the number of times per second that we do this, and we get an average power loss. We also can apply the same arguments at the other transition, where we turn on the transistor. And really the same thing happens in reverse, and we get a similar kind of expression for an energy lost during the turn-on transition. So we get a total switching loss, according to this model, that's equal to the switching frequency times the energy lost during the turn-off transition plus the energy lost during the turn-on transition. Okay, this can be considerable. In fact, often this is larger than all the losses combined from conduction and forward voltage drops that we model in Chapter 3. In many converters, this is the largest loss in the converter. So we have to account for this. And one of the things we're going to do soon is refine our models from the previous chapter to include terms that account for the switching loss. The other thing I'd say is that this is highly idealized, and in fact, it's not really right. It's a good start, but it doesn't account for what happens in the real devices. So back when I was a graduate student, this was what everybody taught, and it led us all to try to do things to reduce switching loss and improve efficiency. And what we did was develop what were called zero current switching converters that would change the order of this switching so that the current would go to 0 first, and then the voltage would rise, and you would think the loss would go away. But people built those converters and found that they got the same exact efficiency and the same switching loss as before. So in fact, while this is a good start, we need to refine the models of the semiconductor devices to understand what the switching times are really happening, what's going on, and how to refine this model to correctly predict the actual switching loss. And so we're going to do that in the next several lectures. This lecture is a short summary of what is going on inside a diode and how it switches. We're going to cover reverse recovery and the basic mechanisms governing switching of diodes. So here is a p-n junction type diode. We have p-doped material on the left side of the junction and n-doped material on the right side. N-doped material, for example, means that we have doped the silicon lattice with impurities that provide additional or extra electrons to the lattice that are of high energy state and easily able to conduct current by jumping from one atom to the next. And we call these majority carrier electrons in the N material. In a similar manner, in the P material, we have majority carrier holes that can easily conduct current and jump from one atom to the next. When these devices are at reasonable temperatures, such as at room temperature, the thermal energy of the majority carriers makes them bounce around inside the lattice. So we can think of them as having thermally induced vibrations or jumping around and bouncing around. Okay, at the p-n junction, what happens then is what's called a depletion region is formed. And this happens because when these majority carriers are bouncing around, they tend to diffuse in the direction of reduced concentration. And so right here at the junction, we have a high concentration of holes on the left side and a high concentration of electrons on the right. And so what happens is that the thermal energy will cause the majority carriers to diffuse in the direction of reducing concentration, and so electrons will diffuse from right to left across the junction, and holes will diffuse from left to right. When these majority carriers diffuse across the junction, they become what are called minority carriers on the opposite side, and in the process of moving across the junction, they leave behind ionized atoms or net charges on the dopant atoms of the region that they left. And so when electrons diffuse into the p region, they leave behind plus charges or positively charged atoms in the n region. And likewise, holes, when they diffuse into the n region, they leave behind negatively ionized atoms in the p region. And as a result, there's an electric field between these charges. And that electric field makes a voltage. Voltage is the integral of the electric field. And so you can see there'll be a net voltage that is plus on the right side and minus on the left side of the junction. And this region here is called the depletion region, or the space charge layer. Across this depletion region, then, this voltage actually opposes the diffusion. So a positive charge would have to basically diffuse uphill, voltage-wise. And what happens is that this voltage across this depletion region builds up until, in equilibrium, the voltage completely stops the further diffusion of holes and electrons across the junction. And at that point, we're in steady state, or the device is in steady state. It has this built-in voltage across the junction, and no further majority carriers will diffuse. Here's what happens under reverse bias conditions. So now we have contacts to the outside world, and we apply a voltage that's normally we consider a negative voltage across the device. So this voltage is negative with respect to the P material, which is the anode, and it's plus with respect to the N material, which is the cathode. Okay, when we do this, we have added voltage. This adds voltage across the depletion region and makes the depletion region get larger. Basically, this entire voltage, externally applied voltage, is blocked by the depletion region. You can see that to increase the depletion region size and have more voltage across it, you have to add charge to it. And that charge actually comes from the external voltage source, or the external circuit. So in this sense, the depletion region acts as a capacitance. We have to add charge to it to increase its voltage. And we generally call this the junction capacitance of the device, and it's a real capacitor that can store energy in its electric field that you can get back later if you change the voltage. Under forward bias conditions, what we do is we increase the voltage of the P region with respect to the N region, and that makes the depletion region get smaller. When the depletion region is smaller, it no longer stops the diffusion of majority carriers across the junction, and so we start to get flow of charge across the junction in each direction, so that holes from the P region diffuse into the N region, where they become what we call minority carrier holes. They're still at a high enough energy state in the N region that they can easily jump from one atom to the next and conduct current. Similarly, electrons from the N region will diffuse into the P region, where they become minority carrier electrons and are able to conduct current there. Under forward bias conditions, then here's what happens. We have current coming in the contact from the external circuit that in the P region gives us holes. Those holes can do one of two things. One is they can diffuse across the junction, become minority carriers in the N region, and eventually they recombine with electrons, majority carrier electrons, in the N region. And so an electron from the negative terminal may come in and recombine with one of these holes. The other thing that the holes can do in the P region is to recombine with an electron that has diffused in from the N region. So we can have a minority carrier electron that recombines with a majority carrier hole in the P region. So those are the two things that can happen, and under forward bias conditions, that accounts for the entire current of the diode. The entire current consists of recombination on one side or the other of the junction. And as long as there are minority carriers in these regions, we continue to have current. So what we have then is, here's a plot of the minority carriers, or the minority carrier concentration on the two sides of the junction. So here, for example, we have holes that diffuse across the junction, and they diffuse at some rate that depends on the slope of this concentration characteristic. So they diffuse towards regions of lower concentration. And they last in this region for some time that we call the lifetime, and that on average after the lifetime is over they will have recombined. They recombine as they diffuse, and we get a concentration that reduces the farther away we get from the junction. And we have that on both sides of the p-n junction. So if we want to turn off the diode, we have to remove these minority carriers on the two sides of the junction, one way or another, to stop the recombination and stop the current from flowing. Thus, the diode is charge controlled by the minority carriers in the P and N regions of the diode. Here is the classic first order charge control model for the diode. It relates first the voltage across the depletion region, V, to the minority carrier charge concentration at the edge of the depletion region. So this Q of T we can take as the charge of the minority carrier holes right here at this point, or the minority carrier electrons at this point. And these are related to the voltage, basically the applied voltage of the diode, but really the voltage across the depletion region. So you're used to seeing perhaps the steady state current versus voltage characteristic of the diode that has this exponential function. That's a steady state relationship, and in fact the correct relationship is this one. Okay, so the charge concentration at the edge of the depletion region is this quantity. Given that quantity, turns out we can find what this entire distribution of charge is, and there's a total amount of charge, or area, under these concentration curves that is the total stored minority charge in the device. In the charge control model, we can make lumped element models of the device, and the simplest first order lumped element model has a single lump of charge that is this total amount of charge stored here, and that charge then is related again with some constant to the voltage across the depletion region with the exponential characteristic. And the charge control equation says that the total charge can increase if we put more current into the diode, which supplies more charge, or it can decrease by recombination. And so this is actually a dynamic equation of the diode that says how the stored minority charge can vary. I should say also that these equations don't include the capacitance across the junction, which we've talked about previously. That's a separate element, and we're talking simply about what happens with the holes and electrons moving across the junction. Okay, so if we look at the charge control equation, in equilibrium, when the diode works in steady state, dq dt is 0. And then we can solve this equation, equate this to 0, and find that the current is equal to this stored charge over the lifetime. And you can plug this stored charge equation here into there, like this. And if you do, you find that the current follows the exponential diode relation that we're all used to, which is the exponential IV curve that does this. But this is an equilibrium equation, and during transients in the diode, this doesn't have to be followed. The dq/dt term can be non-zero, and we can actually, for example, have current that removes stored charge or adds stored charge that deviates from this IV curve. And that's in fact what happens during the switching times of the diode. Here in fact is a plot of a sketch of what really happens. So here we have the diode on initially, so there's some voltage like 0.7 of a volt across the diode, and we're conducting some current, and there's some stored charge. So here I've drawn on one side of the depletion region the stored minority charge and what it looks like. So again, we have a slope here that determines the rate at which the carriers diffuse, and that slope is proportional to the current in the device. And so we'll have charges moving this way and conducting this current. Now at some point t0 then, this is the initial condition, at this point we start to try to switch the diode off. So the external circuit will switch, and as a result we will start removing charge from the diode. And so what we'll observe in the external circuit is this current through the diode, and we can actually remove charge actively from the diode by simply having a reverse current. In our charge control equation, I becomes negative, which makes dq dt be negative, and we actively remove, say, the minority carrier holes backwards across the junction and minority electrons backwards across the junction that contribute to this current. Okay, so with this negative current, then say at time t1, we have negative current and we're pulling charges backwards across the junction. The slope, by pulling these charges, we will reduce the concentration of charge, say in the N region, and with the slope going the opposite direction, you'll see charges actually moving the other direction. At time t2, we've removed enough stored charge, stored minority charge, that the charge right at the edge of the depletion region goes to 0. And that's what happens right here. Okay, At that point, the voltage on the depletion region can start to change. It's no longer this exponential function that is roughly 0.7 volts, but the diode voltage starts to actually finally go negative. So before this point, where we still have positive minority charge at the edge of the depletion region, the diode voltage remains positive, and you can barely see the difference. It's more or less 0.7 volts, and it looks like the diode relay is still on. So at this point, we start to see the voltage change and see some negative voltage. We continue to remove charge, and what happens, say at time t3 here, is that we've removed this charge, and the charge is now 0 at this point x3, and the depletion region has actually grown. And it comes all the way out to x3, which is consistent with having negative voltage across the device. Finally, out here at time t4, we've removed all of the stored charge. There's no more minority charge left. And finally, the diode is all the way off, and it can block the full negative voltage the circuit imposes without conducting current. Okay, let's look a little at the power flow. So power is the voltage times the current, and the power in the diode at this point, before we switch the diode off, we had positive current flowing into the diode, positive voltage across it, and we had some power loss in the diode that is the conduction loss of the diode. You can see where the current goes negative and the voltage is still positive over this time, the diode actually supplies power. It has positive voltage and negative current, and we're actually, some of the energy of these minority carrier charges is being extracted, where we actively pull them out of the diode. Now that amount of power being supplied is not very much, and in fact, in a switching converter, generally that power is lost in the MOSFET anyway, and so it's not a very significant amount of power. But then for the next part, say from this time, we have negative voltage that is substantial, and we have negative current. And this is substantial power loss that happens in the diode itself, and it can make the diode hot. So this is real switching loss in the diode, and in fact we're going to see in the next lecture that we get substantial switching loss if we consider both the MOSFET and the diode over this whole time. And this is a significant amount of loss, and it's often in what we call hard switched or conventional switching converters. This is often the largest single source of loss in the circuit, because you can see this is a lot of current. In a typical diode, this peak negative current may be several times the on-state current, and this is the full off-state voltage. So the product of these is a very high instantaneous power. So this is called the reverse recovery of the diode. This time here is the turn-off switching time that's often called the reverse recovery time, and this charge, which is the minority charge that is actively removed from the device, is called the recovered charge. Now you can also switch the diode off by simply stopping the current and waiting a long time for all the charge to recombine. Or we can do some combination where we maybe reduce the rate at which the current changes and goes negative, which lets more of the charge recombine in the diode and less of it be actively removed. But if we switch the diode off quickly, this is what happens. We basically actively pull all of the stored minority charge out of the diode, and it becomes recovered charge. The familiar IV characteristic of the diode is an equilibrium relationship, and it can be violated during the switching times. In particular, to turn off a diode, we typically have this reverse recovery transient in which we have a large reverse current that violates the equilibrium exponential IV characteristic of the diode. And this reverse recovery time and recovered charge can induce substantial switching loss in the MOSFET and substantial loss in the diode itself as well. In the next lecture, we're going to calculate what the switching losses are and model them in the switching converter. Let's now extend our equivalent circuit models that we derived in Chapter 3 to include switching loss. And in particular, what we're going to do is model the switching loss caused by the diode reverse recovery. Okay, so to obtain tractable results, anytime we're modeling switching loss where we have complicated ringing waveforms and things, we do have to idealize the waveforms. But we can at least include a current spike that comes from the diode switching loss and include the effects of the diode switching time. And this actually gives pretty good analytical results. There are many different things that cause switching loss, as in some of the accompanying lectures here that are discussed. What we're going to talk about here is the loss just from the diode reverse recovery, but we can include other things like the effect of semiconductor output capacitances and their energy stored in a similar manner. So the approach here is to correctly account for how the waveforms change. And in particular, when we apply inductor volt-second balance or capacitor charge balance, or when we calculate the average IG input current, we include how the diode reverse recovery changes those waveforms. And I think the simplest way to do this is to first sketch the transistor and diode waveforms, including the diode reverse recovery, and then relate those waveforms to the inductor and capacitor and other waveforms. So I'm going to do an example of this with a buck converter. So here is a buck converter with a diode that has reverse recovery and with a MOSFET that switches quickly. So we're going to neglect everything, all the sources of loss except for the diode reverse recovery. Okay, so here is the same buck converter, and I've identified the transistor voltage and current VT and IT, the diode voltage and current VD and ID, and I've sketched idealized switched waveforms for all of those here. And they look like the usual rectangular waveforms except for the switching time here of the diode, where we have a current spike from reverse recovery and its effect on all four of the waveforms. Okay, when we do this, there's now somewhat of an ambiguity in deciding how to define the duty cycle. So if we look closely at these waveforms, the switching period, the switching period, TS, goes from here out to right here. And what's happening is that the gate driver and the controller is telling the MOSFET to turn on at this point here, but then we go through the switching transition of the diode and the voltage finally changes out here. Okay, I've also squared up this waveform. This is what we call a snappy diode, that where its voltage changes abruptly at the end of the reverse recovery period to idealize that waveform. So that's a somewhat pessimistic assumption as far as loss goes. But anyway, we have this ambiguity in what is the duty cycle. So actually we can define the duty cycle however we want, and we could define the duty cycle based on when the driver starts to turn on the MOSFET right there, or we could define it based on when the voltage of the MOSFET actually changes right here. And what's sketched here is the second choice. It's based on the voltage in the power stage of the converter. So if I extend this light blue line, which is the transistor drain to source voltage, it's actually falling right there. And if we extend the pink line, which is the MOSFET current, it has the current spike from reverse recovery that is the same as this one, that is happening right before t equals 0. So what I'm going to do is define the duty cycle as being determined by this interval from here to here, so it does not include the diode switching time. The justification for that is that this voltage waveform is what drives the volt-second balance on the inductor and what ultimately determines the effective conversion ratio of the ideal converter, and when we add the switching loss of this converter as well. If we define the duty cycle as being determined by what comes out of our controller, and so this period starts here, duty cycle is defined starting there, we get equations that are valid, but they are not as physically connected to the ideal converter. We predict a different effective conversion ratio, and we get a lot of extra terms around the power stage model. So effectively, the transistor switching and the diode and transistor switching times change the duty cycle from what comes out of the controller, and the duty cycle that the converter effectively works at is based on this voltage waveform of when the voltage at the switch node is high, or when the voltage across the MOSFET switches. Okay, so with that definition, DTS then is this interval that starts after the diode is switched off and ends when the MOSFET is switched off, and then the D prime interval is the rest of the period, going from here out to there. Okay, given those definitions and given these waveforms, let's now work out the inductor voltage waveform and apply volt-second balance. We'll work out the capacitor current waveform and apply charge balance, and we'll work out the input current waveform IG and calculate its average or DC component. So here's the inductor voltage waveform, and with the definition that I just gave you for the duty cycle, here's what it looks like, and it's the same waveform we've been drawing all along this semester. So that definition gives us back the original ideal inductor voltage waveform. And volt-second balance gives us the usual equation, that the average inductor voltage is dVg minus V. The reverse recovery also doesn't change the capacitor current waveform. The capacitor is on the other side of the inductor, and we get the same equation from charge balance that we always have gotten. So far no change. And in fact, from these two equations we can construct the usual equivalent circuit model, which is shown right here with a DVG source, the inductor and capacitor, node and voltage loops, and the load. Okay, the only thing in the buck converter at least that is changed by these switching times is the input current waveform, IG. And what happens is that this inductor, or this current waveform of the transistor current is the same as IG. So the transistor current waveform, which includes the reverse recovery current spike, gets drawn out of VG and changes the IG waveform. So we need to work out the average value or DC component of this current. And we do it in the usual way. Oops. Do it in the usual way by integrating to find its average value. So the average value of IG is the area under the curve divided by the period. The area under this part of this first pulse this area would be the duty cycle, D times TS times the height, IL, where IL is the DC inductor current. We have 0 here, and then we have some area here during the switching time. So we have the area of this rectangle first, which is the diode reverse recovery time. In width and in height, it's the inductor current, IL. Then we also have the area of this current spike, which is the recovered charge that has area QR. Okay, dividing through by TS gives us this expression. So in the ideal case, we had just one term. Average IG was DIL coming from this area, but now the reverse recovery adds two more terms. And the two terms depend on the reverse recovery time and the recovered charge. So an equivalent circuit to go along with that is this. So IG is the current coming out of VG. That's equal to DIL, which is the usual dependent source that is part of the ideal transformer. Then we have two more terms that I'm going to draw as independent current sources that model losses from reverse recovery. So the recovered charge gives us one of the sources. QR over TS is the same as QR times the switching frequency Fs. This is the charge per unit switching period drawn out of the source by the recovered charge, and it has an average value QR over TS. And then the other term from the switching time, we draw an extra amount of current equal to the inductor current during the switching period, or the reverse recovery time, and that gives us another term that is this source. So we put them together and combine the ideals, or the dependent sources, into a transformer, and we get this equivalent circuit. Okay, this looks really like the ideal buck converter with its 1:D transformer turns ratio. Plus, though, it has these two extra sources which model the switching loss. You can see that these sources consume power because they have a voltage VG across them and they draw current out of VG, and so we get a switching loss equal to VG times the sum of these currents. Okay, this can be a considerable amount of power. You have to plug in the numbers to see, but it's very easy for this to be more power loss than all of the conduction losses combined. It depends on the application. You can also see that this power depends on the switching frequency or the switching period. In fact, it's directly proportional to switching frequency, since Fs is 1 over Ts. So if we turn up the switching frequency and switch faster, we turn up this switching loss and we get more power loss, which will reduce our efficiency. Okay, we can solve the model. So the output voltage is easy. It's just the duty cycle times the input voltage. As far as efficiency goes, as usual, we can find the input power and the output power, and then divide. The input power is the input voltage multiplied by IG, and we can solve these things to find IG. It's really from the average input current equation. The output power is the output voltage times the inductor current IL. And so we can divide to find the efficiency, and when we do, we get an expression like this. It has a denominator that's 1 plus this effective switching loss, or terms that depend on the switching loss, and this denominator depends on the switching frequency, so again, efficiency will go down as the switching frequency goes up. Here's a plot. So I'm plugging in some numbers here. I think they're pretty innocent looking numbers. We're 100 kilohertz switching frequency, input voltage of 24 volts. Here are some numbers for the diode reverse recovery time of 75 nanoseconds and recovered charge of 0.75 microcoulombs. This is an okay diode. It's not a super great diode, but it's not a real bad diode either, kind of an average diode. And then I've plotted those equations, and I haven't made any attempt to model how the recovered charge or the reverse recovery time change with the inductor current. it turns out that they do change with inductor current, but it's actually a pretty weak dependence. And modeling exactly how they change with inductor current is fairly complicated. They generally don't give you enough information on the data sheet to have a valid model, and so we'll just keep these constant. But you can see when we plot this, so here I'm plotting efficiency versus duty cycle, what happens is the switching loss degrades the efficiency at low duty cycle. And the reason for that is that as we turn down the duty cycle, we're turning down the output voltage and turning down the output power, but we aren't changing the switching loss by very much. Switching loss does depend on the inductor current, and that is modeled, but the dependence is not very strong. So you can see that what happens is the efficiency becomes poor at low duty cycles. And this is something we observe in practice as well. And in fact, at low output power, the switching loss makes the efficiency become poor. So a converter may have good efficiency at full power, but when you turn down the power, the efficiency goes down for a variety of reasons, but one of the major reasons is because we still have substantial switching loss without having a lot of output power. To provide another example of modeling switching loss, let's derive the equivalent circuit model of a boost converter, including the diode reverse recovery. So here's a boost converter, and we're going to assume that all of the components are ideal except for the diode and its reverse recovery, and we'll derive the averaged or DC equivalent circuit model with terms to incorporate the effects of reverse recovery and its loss. So here is the boost converter and the transistor and diode waveforms. They look qualitatively the same as the waveforms we drew in the last lecture for the buck converter with reverse recovery. The only real difference is that the values are a little different. So the voltages across the semiconductors when they're off is equal to the output voltage V rather than the input voltage. Just as in the buck converter, we need to correctly define the duty cycle to obtain the effective duty cycle that the power converter operates with, and we define this using the voltage waveform. So the voltage at this node, the switching node, or the voltage across the MOSFET, is this blue line shown here, and the effective duty cycle, as judged from the MOSFET voltage, is the time when the MOSFET voltage is low. So we will define this as the interval dTs, and d prime Ts is the remainder of the interval, including the diode switching time. So we have these waveforms with the reverse recovery, peak in current, and the reverse recovery time T sub r. So the first step then, given these transistor and diode waveforms, is to relate the inductor voltage and capacitor current waveforms to these waveforms. So I'll define the inductor voltage here, and you can see from writing the equation of this loop, the inductor voltage V sub L is equal to the input voltage Vg minus the transistor voltage V sub T. Likewise, for capacitor current, we can write the node equation here, and the capacitor current is equal to, for this converter, the diode current, I sub D, minus the load current, which is V over R. Okay, so we can find the average values of these quantities and apply volt-second balance and charge balance, accounting for the effect of the reverse recovery of the diode on these waveforms. One other small point, we in general need to write the equation of the input current Ig, but for the boost converter, Ig is the same as IL. So if we find the average IL, or DC component of inductor current, that's the same as Ig, and we don't have to do any further work. Okay, so let's do inductor volt second balance first. So VL is VG minus VT, and VT is the blue waveform right here. So on the next slide, that waveform is drawn again. And in fact, here the waveform looks the same as in the ideal case. The reverse recovery time doesn't change this waveform, assuming we correctly define the duty cycle, as I previously mentioned. So we can apply volt second balance. The average inductor voltage is the duty cycle times VG for the first interval, plus D prime times this VG minus V, and we get the same equation as usual for the inductor volt second balance, and we can even construct an equivalent circuit model from this. What would we get? VG would be the input voltage source. It has a current capital IG, and this is this voltage is equal to minus D prime V. So we have a dependent source that depends on the output voltage V multiplied by D prime. Okay, so here's our loop equation corresponding to the inductor equation, and again IG is the same as the inductor current capital IL, which is the current in this loop. Okay, for the capacitor, we apply charge balance to the capacitor, and basically the easy way to do this is to write the node equation at the node where the capacitor is connected, which says that the diode current is equal to the capacitor current plus the load current. So one way to apply charge balance is to average these currents. So we can say that the DC component of diode current equals the DC component of capacitor current plus the DC component of load current. Now, DC component of capacitor current is 0 in steady state by charge balance, which says that the DC component of the diode current is equal to the DC load current. So we've drawn the diode current waveform already for the diode. We simply find its average and equate that to the load current, and that effectively gives us the equation from capacitor charge balance. So here is that equation repeated. And to find the average diode current, we need to average this current. So the average diode current is what? 1 over Ts times the integral of ID of t over the period. So we get 1 over Ts times the area under the curve. Okay, so what is the area under the curve? Well, first we need the area of this rectangle, and this rectangle has a height of IL, and it has a length or base that is this time, and that time is in fact what we normally call d prime, but then minus the reverse recovery time. So this length here is d prime ts minus the reverse recovery time t sub r. And then to that we also have to add the recovered charge QR, and in this case it's a negative quantity. We usually on data sheets express QR as a positive number, so we should subtract QR. Okay, we can now divide through by the TS, and what we get is d prime IL minus IL TR over TS minus QR over TS, which is the value, the expression shown here. Okay, let's construct an equivalent circuit then to go with that. So this is the node equation at the output node of the capacitor, and it says that the load current, which is the current coming out of the node, and is the we have a voltage V across a resistor R, that is our load resistor, that is equal to the sum of these three terms. The first term is d prime IL, which is the usual dependent source that will become part of a DC transformer. The second term is IL times TR over TS, and it has a minus sign, so it's drawn out of the node. And I'll draw it as an independent source. It is a loss element. The value IL times TR over TS. And then the last term is minus QR over TS, which is also a loss term. So for the boost converter, we get two extra loss terms from the diode reverse recovery, and in the case of this converter, these currents are actually at the output node where the capacitor is. And in fact, the reverse recovery causes current to be drawn out of the output capacitor, as if it's loading the output. So the switching loss effectively is another load on the output that is a loss element. If we take the two models together for the inductor volt second balance and the capacitor charge balance and combine them, including combining the dependent sources into the usual transformer, we get this model now. So we have the ideal boost transformer that is D prime to 1, and then we have our two independent current sources, or sinks actually, that model the loss caused by the reverse recovery. And these are actual power losses. The voltage across these sources is the output voltage V, and they cause a power loss equal to that voltage V times the sum of the two currents, like this. Here's a sample prediction of this model. This sample here actually includes an inductor resistance, and so the inductor resistance, if we included it, would become an additional resistor in the loop where the inductor is. And so with that resistor included, here's a solution of V over VG for this boost converter with and without the reverse recovery. And so the effect of the diode reverse recovery is to actually appear to load down the output, which reduces the output voltage, especially at high duty cycle. Okay, so to summarize, we can model or incorporate switching loss into our averaged model. What we have to do is draw the actual transistor and diode voltage and current waveforms, and then relate those waveforms to the inductor voltage and capacitor current waveforms, and perhaps also to IG. We then apply volt-second balance and charge balance as usual and proceed to compute the equations of the DC conditions in the circuit, including the effects of this diode reverse recovery, and we can then reconstruct the equivalent circuit by a simple extension of how we did it in Chapter 3 to get equivalent circuit models that incorporate switching loss. We'll conclude our discussion of power diodes with several additional important topics. The first one is the trade-off between the blocking voltage or breakdown voltage of the diode versus the forward voltage drop versus the switching speed. And this is a trade-off that is inherent in any of our power semiconductor devices. But it's interesting to see how it works in the p-n junction type diode. In any semiconductor device, the breakdown voltage is related to the doping concentration of the silicon material. Basically, silicon with heavy doping has a low on resistance, but it also breaks down at a lower electric field strength than if there was light doping. And this is a fundamental characteristic of avalanche breakdown in semiconductor materials. And so in a diode, we have to include a low doping concentration, high resistivity region in order to achieve a specified voltage breakdown. Here's a diagram that's then a more accurate description of the diode. where we have the P region on the left, the N region on the right, and a lightly doped region in the center. Here it's denoted N minus, which means low concentration of doping. Often this is also called I for intrinsic, and this is called a PIN diode. So we have this low doping concentration in the middle of the diode, and under reverse bias conditions, the depletion region extends far out into this N minus region with electric fields that are high in strength, that the light or low doping concentration material can withstand, and we get our voltage breakdown from that. Now, the worry is that by having such a large region that is high resistivity, this will increase the on resistance or the forward voltage drop of the device. In a minority carrier device, though, such as the PN diode, that doesn't happen. And instead what happens is a phenomenon known as conductivity modulation. Basically, the holes from the P region can diffuse into the lightly doped region, where they become minority carriers, and they actually reduce the effective resistivity of the material. They provide charges that are able to conduct current even though the doping concentration is low. And in fact, electrons from the N region can diffuse into this N minus region as well, and so we get a large concentration of minority carriers in the lightly doped region that gives us a low on resistance. So the good news is we can get a high voltage breakdown with a low on resistance at the same time. But the bad news is we have a lot more stored minority charge in the N minus region, and therefore the switching time is longer because it takes longer to remove all of that charge to turn the device off. So then here are what waveforms we actually observe in a real power diode. So we start out with a diode in the off state, blocking negative voltage and conducting no current, with this large depletion region that is blocking the voltage. We then try to turn on the diode, so whatever circuit is connected to the diode will apply positive current to the diode and raise the voltage across the diode. Initially, this positive current charges the capacitance of the depletion region and raises the voltage at some rate. Eventually, the voltage on the diode is positive, and the diode turns on and starts to conduct current. We may or may not observe some voltage overshoot as shown here. What's happening here is that if we turn the diode on quickly, it's possible that we initially observe the voltage of the lightly doped region without conductivity modulation. So we have a high on resistance then, and we have a large forward drop that might be 10 or 20 volts. But then after a short period, we get minority charge and conductivity modulation that brings the forward drop back down to something like 0.7 or 1 volt. And then the diode after that conducts with the low on resistance. When it's time to turn off the diode, the external circuit attempts to reverse polarity or reverse the current through the diode. And as we've discussed in the previous several lectures, we get a reverse recovery transient with current flowing backwards through the diode to extract the minority charge. And the only difference here now is that we have a lot more minority charge from the conductivity modulation of the lightly doped region. So we observe the reverse recovery, which involves removing the recovered charge, and also while the voltage is changing, we're also charging the capacitance of the depletion region. So as we've already discussed then, this reverse recovery can induce substantial power loss in the MOSFET, and during the last part of the reverse recovery in the diode as well. But at a minimum, we see this large reverse recovery current causing a current spike in the MOSFET while the MOSFET is held on with voltage across it. And so we get large instantaneous power loss induced in the MOSFET by the diode reverse recovery. Okay, here's a little terminology. It's traditional in the power semiconductor field to give names to diodes according to their application. A standard recovery diode typically is one that is intended for low voltage or low frequency applications such as 60 cycle or 50 cycle rectifiers. Often for these diodes the reverse recovery time is not specified, but they won't work in a 100 kilohertz switching converter because their reverse recovery times are too long. Fast recovery or ultra fast recovery, or more recently other adjectives like super or hyper fast, refer to diodes where the reverse recovery time is specified and they are intended for switching converter applications. So these will have reverse recovery times for fast recovery diodes that might be between 100 nanoseconds and a microsecond. Or ultra fast might be 100 nanoseconds or below. And nowadays we can get 600 volt PN junction rectifiers with recovery times as low as 25 or 35 nanoseconds. A Schottky diode, we have to mention also. A Schottky diode has a metal semiconductor junction instead of a PN junction. It is inherently a majority carrier device. It does not work on minority carriers as we've been discussing so far. As a result, the Schottky diode for silicon rectifiers doesn't have conductivity modulation, nor does it have long reverse recovery times. So that's good news and bad news also. Schottky diodes are limited for silicon devices to low voltage applications, generally 100 volts and below, and they're very good at, say, 45 volts and below. They switch very fast, although they do have significant junction capacitance that can affect the circuit and cause switching loss. Recently we have Schottky diodes built with wide bandgap semiconductors such as silicon carbide or even more recently gallium nitride. These wide bandgap devices can attain high breakdown voltages of 600 or 1200 volts in a Schottky diode and still have a majority carrier device. They have larger forward drops, maybe 1.5 or 2 volts instead of something a little below 1 volt. However, they're very fast switching, and very often in a power converter you'll find that if you replace your PN diode with a Schottky barrier silicon carbide diode, even though the conduction loss is higher, the switching loss is much lower, and overall the efficiency is reduced. So these have found there are commercial devices that have found some good industry acceptance. The major problem today with them is their high cost. A silicon carbide 600 volt diode might cost 5 or 10 times as much as a comparable silicon diode, but there definitely is a measurable reduction in switching loss. Okay, let's discuss paralleling diodes. With a minority carrier or PN junction diode, classically we're not supposed to parallel diodes. So for example, suppose we needed a 10 amp diode, but all we were able to buy, or all we had in the lab, were 5 amp diodes. So you might say, well, I'll take 2 5 amp diodes and put them in parallel. And in the process, we're hoping that the 10 amps will divide evenly between the 2 diodes, so we get 5 amps through each diode. Generally, this doesn't work. And the reason for this is the temperature dependence of the equilibrium IV characteristic of the diode. Basically, when a diode gets hotter, its voltage goes down for the same current, or conversely, for the same voltage, the current will go up. And this is in a minority carrier, say PN junction diode. So here's what happens. You put the two diodes in parallel, we apply 10 amps. There's some small difference between the diodes which makes one of the diodes take a little more current than the other, and it gets a little hotter. And so say that this diode 1 is hotter, runs a little hotter than diode 2. That makes it take more current. So instead of 5 amps, it might take 6 amps, and diode 2 then will take 4 amps. Okay, that makes the first diode get hotter yet, the second diode get cooler, and even more of the current goes through the first diode and less through the second. And so we have thermal instability, where one diode hogs all the current. And what will happen is that diode will hog the current, it'll overheat, and it'll in fact exceed its rating, and so it will fail. And once it fails, if it fails as an open circuit, then that makes all 10 amps go through the other diode, and it fails also. So in general, with minority carrier devices, we aren't able to parallel. With majority carrier devices, the forward drop goes up as the temperature goes up, and it may be possible to parallel. So if you want to get minority carrier diodes to share current, we have to do what I would consider heroic measures. So we can sort devices and select matched devices. We can package them on a common thermal substrate so they run at the same temperature. And in fact, if you want to build a high current module of diodes, that's exactly what's done. Or we can try to build some external circuitry that forces the currents to balance. Usually that circuitry takes a lot of work to make work, and generally what we would rather do is find a large enough diode and just use one. One last short topic. We've talked about how diode reverse recovery induces switching loss in the MOSFET in say a buck converter. Sometimes we have circuits where the diode is not directly connected to a transistor. And here's an example of one. This often happens in transformer isolated converters or in some other converter circuits that have effectively an inductor that provides current to the diode. So in this example, I'm going to model the rest of the converter circuit with some switched voltage source that's shown here. It's initially a positive voltage, and then at some time it switches to a negative voltage. And what's shown here is an inductor, and then a diode with its junction capacitance, here C, that's shown explicitly. This is the capacitance of the depletion region. So initially we have positive voltage applied. That positive voltage makes positive current flow through the inductor, and that current flows through the diode, turning the diode on. Okay, so the diode is on, and basically this positive input voltage V1 appears across the inductor, and the inductor current increases with a slope given by the voltage divided by the inductance, and rises to some positive current. And at this time where we switch the input, this voltage negative, at this point, so we have negative voltage applied across the inductor. The inductor current is still positive initially, so this positive current continues to flow through the diode, which keeps it on, and so the input voltage appears across the inductor. And the inductor current then ramps down from the negative applied voltage, like this. Eventually it reaches 0. And what happens then? Well, just because the inductor current is 0 doesn't mean the diode turns off. We have to first remove its stored charge, and that takes some time. So during the reverse recovery time of the diode stays on. It maintains its same forward voltage drop, and so we have the same negative voltage across the inductor, which continues to charge the inductor current negative. Okay, so we get some negative current in the inductor. And then at some point right here, Finally, the diode turns off because its stored charge has been removed by the negative current. And at that point, the diode switches off, and what happens to the inductor current? We've built up some negative current in the inductor. We're storing energy in the inductor, 1/2 Li squared, and the inductor current has to go somewhere. Well, the only place it can go is through the capacitance now. So the junction capacitance of the reverse bias diode will form a resonant circuit in connection with the inductor. That resonant circuit has some initial condition on current, and so we get the inductor and capacitor forming a resonant circuit that rings like this, and we get diode voltage that rings as well. Well, eventually that ringing decays to zero by parasitic losses in the circuit. So we have resistance of the inductor winding, we have core loss and other losses around the circuit, and something damps out the ringing and makes it decay to zero. Whatever that is, whatever damps it, dissipates the power, and so it will get hot. And this is in fact a form of switching loss. The diode induces energy storage in the inductor, which is then lost after the diode turns off. Okay? However much energy loss that is, I'm going to call it W off right now, is the energy loss during the diode turn off or stored in the energy during the diode turn off transition and then lost. That energy multiplied by the switching frequency is another form of switching loss. And so in our power converters, when we see ringing like this that decays, that ringing is an additional component of switching loss. In this particular case, we can actually calculate how much energy there is. The recovered charge, which is the area under the curve, is defined as the integral of the current during this time, as usual. So, and the recovered charge is something that is a property of the diode. We can also calculate the energy stored in the inductor during this interval. And basically, if we integrate the voltage on the inductor, this negative voltage, times the inductor current, that's the integral of the power, which is the total energy stored in the inductor from here to here. Okay, well, the voltage is this voltage minus V2, and the current is this current waveform. But we can plug V2 into here, and since V2 is a constant, the integral of the power is actually just the constant V2 times the integral of the current, and the integral of the current is the recovered charge of the diode. So what we get is that during the diode reverse recovery time, energy is stored in the inductor equal to the applied voltage V2 times the diode stored charge or recovered charge. Okay, that energy becomes stored in the inductor, so it's equal to 1/2 Li squared at this point right here at the peak of the current. And that energy then rings between the inductor and capacitor during these oscillations and eventually gets dissipated by whatever damps the ringing. So this is the amount of energy we lose every time this diode switches off. We multiply it by the switching frequency to get the switching loss. And so the diode can induce switching loss in things besides a MOSFET. And this reverse recovery will induce ringing that is another form of switching loss. For the next two lectures, we're going to cover the power MOSFET. In this lecture, I'm going to introduce what the power MOSFET is, how it's constructed, and some of its basic characteristics. And then in the next lecture, we'll talk about MOSFET gate drive circuits and some practical considerations. Here's a cross-sectional view of a power MOSFET. So if you take a silicon wafer and cut it and look at from the side what it looks like, generally you see something like this. So we have vertical current flow through the MOSFET and really through just about every power device. So for example, the drain here connects to the bottom of the silicon wafer, and the source and the gate are put on the top side. What I've shown here, the cross-hatched regions represent metal contacts. So we have metal contacts to the drain and to the source. This shaded area here around the gate is the oxide layer, that's silicon dioxide or glass that insulates the gate from the rest of the MOSFET. The clear area inside that is the gate, that is usually a polysilicon material, but it's a conductor that it forms the gate. And then here we have the doped silicon. This is an in-channel MOSFET. The source is connected right here. The drain comes from the bottom at this in region, but there's lightly doped in material, and the drain actually is right there. And so we have a MOSFET that connects to the drain and source like that. The P material is called the substrate, and in the practical power MOSFET, the substrate is shorted to the source. This particular structure shown here is called the DMOS structure, in which the gate and the source are built laterally on the top surface of the MOSFET. We also have other variants, grooved structures such as VMOS or UMOS, or sometimes known by a trade name such as trench MOS, are devices where grooves are cut into the top of the side of the silicon, and the gate is actually built vertically along the side of the groove. We also have the SuperMOS structure, which is a relatively recent improvement that reduces the on resistance of high voltage devices. And so we have some very good 600 volt MOSFETs built with the SuperMOS structure. Okay, the power MOSFET is a highly interdigitated device, meaning that we replicate the MOSFET many times on the top side of a chip and connect all of these little MOSFETs in parallel to get one large high current MOSFET. So here you can see there's a channel right here of a MOSFET, there's another one there, there's another one over here, another one over here, and so on. And so we pack these MOSFETs as tightly as we can together to fill the surface of a silicon wafer and build a high current device. Okay, so then current will, when the MOSFET is turned on, current will flow in the drain and then through the channel and out the source. That's for positive current flow. Actually, a better way to say it perhaps is that we have electrons coming in from the source to the in material. They form when the gate is forward biased, they form an inversion layer or channel here that effectively is more in region that connects the source to the drain, and then the electrons flow this way and out the drain. In the off state, where the MOSFET is, the gate is turned off, positive voltage is put on the drain with respect to the source, then we have a depletion region formed that blocks the voltage, and really this is the same as in the p-in diode. And in fact, if you look at the substrate P material and this region right here, this actually looks like a p-in diode, as we talked about in the previous lectures for the diode. We have lightly doped in region in the drain that gives the device the breakdown voltage that it requires. And so in the reverse state, we have an electric field really across here that has the voltage drop from drain to source. Okay. To obtain a high voltage breakdown rating, as in any semiconductor device, we require lightly doped, high resistivity material. In the on state, again, current flows this way, as I mentioned before. A key distinguishing feature here, though, is that the current has to flow through this in-minus region. And much of the on resistance of the device appears across that region. And since it is lightly doped, it has a high resistance. And this is the on resistance primarily of the MOSFET. You do have to put that in series with the resistance of the channel and the resistance of the contacts and the leads and the package. But in general, this N- region dominates the on resistance. And in the MOSFET, we have a majority carrier device where there are no minority carriers to cause conductivity modulation the way there is in the diode. So this accounts for why MOSFETs tend to have a relatively high on resistance, especially at high voltage levels. And so a high voltage rated device will have to have an especially high resistance N- region, and the on resistance goes up quickly with voltage. So we have very good MOSFETs at low voltage, but at high voltage we start to prefer minority carrier devices that can give lower forward voltage drops. Okay, the MOSFET has this body diode, which I mentioned last week. The body diode actually comes from this p-n junction between the substrate P material and the drain. And you can see there is a p-n junction there, and it's a real diode. So effectively we have our MOSFET represented by the channel, and it's in parallel with the body diode. Okay, so this is a real diode. It has reverse recovery. It can conduct current if it's forward biased, and that happens if we put plus on the source and minus on the drain. Then this diode can become forward biased and current can flow this way. The diode can conduct the full rated current of the MOSFET. After all, it is the same device. However, the caveat is that the diode is not necessarily optimized for fast switching speed, and it depends on the diode. Some MOSFETs are designed to have on purpose a fast recovery diode, and others are not. Here are the static IV characteristics of the MOSFET. This is drawn in a little different way than you might be used to seeing, and it's drawn to emphasize how to control the MOSFET. So the vertical axis is the drain current. The horizontal axis here is the gate to source voltage, and we have characteristics or lines of constant drain voltage. So basically, if the gate voltage is below a voltage known as the threshold voltage, then the MOSFET is off. And the gate driver has to bring the gate voltage or gate to source voltage higher than the threshold to turn the MOSFET on. So here, as you can see, as we raise the voltage above the threshold, for the first few volts the MOSFET starts to turn on, and when we're up here at maybe 10 or 15 volts, the MOSFET is all the way on. And then we have, for a given drain current, we have a low drain to source voltage. So we generally will operate the MOSFET turned on over here, where we have a low voltage, and in this case the drain to source voltage is approximately proportional to the drain current, and we approximate this as saying the drain voltage is the drain current multiplied by the on resistance of the MOSFET. Okay. In majority carrier devices like this, we typically have a positive temperature coefficient of the on resistance, which means as the device gets hot, the on resistance goes up. So first of all, this makes it easier to parallel MOSFETs. They don't have this mechanism, this positive feedback mechanism that will make one device hog all the current. On the other hand, the on resistance is highest at high temperature, and when we choose an on resistance, we have to be cognizant of that and think about, what, in the worst case, what is the hottest the MOSFET will run and what is the on resistance under those conditions. Here's an equivalent circuit of the MOSFET to first order, showing the capacitances. So the MOSFET has capacitance from each terminal to each other terminal, and we'll talk about what each of these is one at a time. So first of all, the gate to source capacitance is this ideal capacitor of the MOSFET between the gate terminal and the channel, and it's drawn here with respect to the source. So this is the capacitance across here from gate to channel. And we charge up this gate to source capacitance to put charge in the channel and turn the MOSFET on. In addition to that, you can see that there's overlap between the gate contact and the drain. And this forms what's called the gate to drain capacitance. Okay, we do what we can to make that capacitance small, but in fact, charging it up does help put additional charge in the drain region and somewhat reduce the on resistance. Typically, the gate to drain capacitance is small compared to the gate to source capacitance. So it's a lot fewer picofarads of capacitance. However, it has a lot of voltage across it. The gate to source capacitance might get charged up to 10 or 15 volts, whereas the gate to drain capacitance gets charged up to basically the full drain voltage. And so although the capacitance is small, the voltage across it is large, and the amount of charge in this capacitance can be large. In fact, in some devices it's larger than the charge in the gate to source capacitance. This has some impact on and considerations on how we design the gate driver circuit, and we're going to talk about that in the next lecture. The third capacitance is the drain to source capacitance across here. And this is basically the capacitance of the body diode. It's really capacitance from here to here. And this is the same capacitance that this p-n junction diode would have. And it behaves a lot like a diode capacitance. It's nonlinear. We didn't talk about this with respect to the p-n junction diode, but it's actually a similar kind of function. Here's a classic formula for a depletion capacitance, and it's a nonlinear device where the capacitance varies roughly as the inverse square root of the voltage. So as the voltage goes up, the capacitance goes down, the incremental capacitance, and we get this inverse square root formula. Okay, these output capacitances of devices, such as the drain to source capacitance of the MOSFET and the junction capacitance of the diode, are another mechanism that can lead to switching loss. Basically, these capacitances get charged up with energy when there's voltage across them. So, for example, when the MOSFET is off, we have VG across here. There's no voltage across the diode junction capacitance, but as far as AC signals go, the junction capacitance is effectively in parallel with CDS, and the two add together. When we turn the MOSFET on, we short out these capacitances, and any energy stored in them gets dumped into the channel of the MOSFET during the turn-on transition. So if this is a linear capacitance, we can say that these capacitances store energy equal to 1/2 CV squared, where here C is the effective capacitance if these were linear capacitances of the output capacitances of the devices, and VG is the voltage at the input to the converter. So we lose this much energy every time we turn the MOSFET on and short the capacitances out. Okay, so this would cause a switching loss that is equal to this energy stored in these capacitances multiplied by the number of times per second that we short out the capacitances, or multiplied by the switching frequency. So this is another mechanism for switching loss. If we want to account for the fact that the capacitances are nonlinear, we can integrate the power that charges up the capacitances to see how much energy the nonlinear capacitors store. So we can integrate the power, which is voltage times the current, and plug in the expression for I is C dV dt for this capacitor. And when we integrate the square root function, we find that the energy that is lost is equal to this. And it has a 2/3 factor instead of a 1/2 factor, and we evaluate the capacitance at the off state condition of the MOSFET. So that makes us actually lose a little more energy. Instead of 1/2 CV squared, we actually have 4/3 times as much, or 2/3 CV squared. Okay, conclusion. So the MOSFET is a majority carrier device. That's good news because it has very fast switching speed. We don't have all the time that it takes to remove all of this stored charge that was causing conductivity modulation in the diode. And so MOSFETs can switch much faster. And in a MOSFET that is, it's typical to get switching times of a few tens of nanoseconds, and in low voltage devices even faster. So typical switching frequencies, tens and hundreds of kilohertz are easy, and we have low voltage computer type power supplies that run in the megahertz of switching frequency range because of the high speed of these devices. The bad news though is that on resistance increases rapidly with the rated voltage because these are majority carrier devices and don't have conductivity modulation. So we have good superjunction MOSFETs at 600 volts, but we can't go much higher than that before the on resistance has increased too much to where it's just not economical to use the device. They're very easy to drive. We simply switch the gate to source voltage between 0 and 10 or 15 volts, and very easy to control then when they're on and off. We also have logic level MOSFETs that are designed to operate with a 5 volt gate voltage instead of 10 or 15. Okay, one other thing, these devices generally are loss limited. When we design a power converter, we generally don't select the MOSFET based on the current rating, which is a peak current rating of the device. Instead, usually we select them on the basis of on resistance and conduction loss. So often we will choose a device with a peak current rating much higher than we intend to use, and instead we choose the MOSFET size to get a given low on resistance as needed in our application. So as a result, these are very rugged devices as well that have quite a bit of margin when it comes to current. In this lecture, we'll discuss some practical circuits for driving power MOSFETs and some of their basic considerations. So what I've shown here as an example is a synchronous buck converter. In other words, it's a DC to DC buck converter that has a main power transistor realized by a MOSFET, and the rectifier or diode is replaced with a synchronous rectifier with MOSFET Q2. This configuration of two MOSFETs actually is found in many different applications and circuits besides this one. It's found in quite a few different DC-DC converters, and this is often called a half-bridge circuit. It's also found in many different DC to AC inverter circuits. And the fundamentals of driving the switches really is the same in all of those circuits. But here, to keep things simple, we'll discuss the DC to DC synchronous buck converter. So we have two transistors that we have to drive. So the main switch Q1 and the synchronous rectifier Q2 each are turned on and off by their control terminals or gates, and the voltage of the gate must be referenced to the voltage at the source of the same transistor. So to turn Q2 on and off, let's see, its source is connected to ground, so its gate voltage must be switched with respect to ground. And that's relatively easy. On the other hand, with Q1, the source of Q1 is connected to the switch node, which is switching high and low. When Q2 is on, the switch node is at ground, and when Q1 is on, the switch node is at VG. So to control Q1, we must drive the gate voltage with respect to this switch node and drive the gate voltage must be high, say 12 volts above the switch node when we want to turn Q1 on. and it must be essentially equal to the switch node voltage when we want to turn Q1 off. So we need to build circuitry that is connected to the two gates here to drive the transistors in that manner. Here's a common way to do it. This is called a half-bridge gate driver, and we can buy commercial half-bridge gate drivers that are implemented in high-voltage integrated circuits that do this. So the half-bridge gate driver really comprises all of these things inside the box. The half-bridge gate driver contains a low-side driver that drives the low-side MOSFET Q2 with respect to ground, and it contains a high-side driver that drives the high-side MOSFET Q1 and its gate with respect to its source, which is the switch node. Each of these triangles represents really a buffer or a circuit that can produce the high currents needed to switch the gates, charge the gate capacitances quickly at the proper voltage, in this example 12 volts. The high side driver additionally has what's called a bootstrap power supply. This buffer or gate driver circuitry has to be powered, and its effective ground is connected to the switch node, and so the power supply to this driver circuitry must be 12 volts with respect to the switch node. And so this diode and capacitor comprise what is called a bootstrap power supply. When the low side MOSFET Q2 is turned on, then the switch node here is at ground, and what happens is this bootstrap diode turns on, and this capacitor is charged to 12 volts through this path. So we get 12 volts here. Okay. Then when Q2 turns off and Q1 turns on, when this gate driver turns Q1 on, the switch node goes high up to the input voltage, and the capacitor voltage flies up with it, so that the gate drive circuit for Q1 is still powered from the 12 volt supply held on this capacitor. At this point, this diode is off, and the high side driver is powered from the bootstrap capacitor. So the bootstrap capacitor gets charged to 12 volts every time the low side transistor turns on. Something about bootstrap power supplies is they don't work unless you switch the low side transistor. You have to turn it on every so often to charge up this bootstrap capacitor, or it will run out of charge. The gate drive circuitry generally includes what's called undervoltage lockout protection, in which if the power supply of the driver circuitry is too low, then the circuitry will turn off, and it will actually protect the power stage by shorting the gate to the source and keeping the transistors turned off. So if you ever let this bootstrap capacitor voltage get below the undervoltage lockout of this gate driver circuit, then it will just turn off and the circuit won't work. So we have to keep switching Q2 occasionally to make sure we charge this up. Now under normal operation, we're switching Q1 and Q2 on and off at the switching frequency, and that's no problem. Okay, some more things we need in this circuit. This logic input is a control signal that goes high and low, and it commands Q1 and Q2 to turn on and off. So when the logic signal is high, typically we'll turn Q1 on and we'll turn Q2 off. So there's a block here and here that perform that function of providing the correct signals going into these buffer amplifiers to make them turn on and off in this way. Likewise, when the logic input is low, we want Q1 off and Q2 on. Okay, this logic signal typically is referred to this ground, and so it'll go high and low with respect to ground. And this upper block must also then perform the function of level shifting. It has to level shift this signal up to this node voltage to provide the proper signals at the input of this buffer. Something else we have to do is we have to make sure that we never turn both Q1 and Q2 on at the same time. If we ever do that, then they'll short out our input voltage, what we've been calling VG. And even if they're on for a few nanoseconds at the same time, during those few nanoseconds we can get a large current spike that flows through the two transistors that can be many, many amps. And that current spike can damage the transistors and make the circuit fail, or at the very least it will cause a large amount of power loss. So what we do is this logic circuitry, these boxes, also implement what is called break before make operation, or non-overlapping conduction circuitry, which makes sure that first you turn the on or conducting transistor off, we wait some amount of time called a dead time, and then we turn the other opposite device on. So both devices are off for some short amount of time that is long enough to make sure that when we account for switching times and driver delays and things, we never have the case where both transistors can be on at the same time. Okay, let's consider what happens. Let's suppose we had Q2 on, and we want to turn it off. So our logic signal will start out low, Q2 is on, then we go to switch the logic signal high, there is some dead time, and then we turn Q1 on. So one question is, what happens during the dead time? Which device conducts, if any? Okay, well the answer is during the dead time the inductor current continues to flow and we can't interrupt the inductor current. Let's assume here that the inductor current is positive and flowing to the output. If we have a positive input and positive output voltage, then the inductor current will flow in this direction. If both transistors are off, the inductor current has to flow somewhere. Well, the only place it can flow then is through D2, through this body diode. The inductor current will forward bias the body diode, and it will conduct during the dead time, and the switch node voltage, Vs, will remain low with D2 conducting. Then right here, where we turn Q1 on, the upper gate driver will turn Q1 on, and what it does then is we have current flowing this way that will both make D2 go through a reverse recovery and cause switching loss, and also it will supply the inductor current. After the reverse recovery of D2 is done, D2 will be off, and then Q1 will conduct and supply the inductor current. So we have switching loss that happens even with synchronous rectifiers. Because of the need to have dead times, we get switching loss caused by the body diodes. Let's consider some further details about the switching times and exactly how these devices switch. If you recall from the last lecture, we discussed the capacitances of the MOSFET, and we drew this circuit here where we explicitly showed the MOSFET with its body diode and with the three capacitances, the gate to drain and gate to source capacitance, and the output or drain to source capacitance. To understand what happens during the switching times, we also need to model the driver and understand how the driver circuit interacts to charge and discharge these capacitances. So here's our driver symbol, and what I'm going to do is represent the driver output terminals here with a simple Thevenin equivalent model here, in which we model the output terminals with some Thevenin equivalent voltage source and some Thevenin equivalent resistance. Okay, we know the Thevenin equivalent voltage is simply the open circuit output voltage, which is something that will switch between 0 and, in this case, 12 volts. And R Thevenin is the Thevenin equivalent output resistance of the driver. Now, real drivers are more complicated than this, but this is actually a reasonably good first order model that explains all of the things we want to talk about today. And in a typical driver, we can think of this Thevenin equivalent resistance as being the on resistance of the MOSFETs that are inside the driver, that are driving the output terminal of the chip. It's traditional to rate drivers according to the peak current that they can produce at their output. And so if we buy a driver that's rated at 12 volts and 1 amp, for example, then the Thevenin equivalent resistance would be 12 volts divided by the 1 amp, or 12 ohms. Okay, so our actual circuit then drives the gate to source of the MOSFET with this Thevenin equivalent. So what I've done here is to insert the gate driver Thevenin equivalent model in place of the low side driver, and I've replaced the MOSFET with an equivalent circuit model that contains the capacitances, the body diode, and here we have a dependent current source that models how the drain current depends on the gate voltage. Let's consider the transient in which we turn off the lower MOSFET, wait for some dead time, and then turn on the upper MOSFET. So we're going to draw some waveforms. Here's our Thevenin equivalent driver voltage that will start out high so that the lower MOSFET Q2 is on. So it's 12 volts. And under these conditions, the gate to source voltage of Q2, this voltage here, is high also and is equal to 12 volts. Okay, the switch node voltage Vs of t is equal to ground because the lower MOSFET is on. And at this point, what we'll do is we'll make our driver switch low. So the Thevenin voltage goes low. We have an RC circuit where the Thevenin resistance is connected across VGS, and it will pull current out of this gate and discharge these capacitors. So there'll be some kind of RC type decay and the voltage will go low. Okay, when the lower MOSFET is off, recall the body diode is still on to conduct the inductor current, and that will keep this Vs switch node voltage low. Okay, and it will stay low for the dead time. So here is the dead time. Or perhaps even we should call this whole time here the dead time. Okay, at this point, the upper gate driver turns Q1 on. So what happens when it turns Q1 on is the upper MOSFET will try to pull this node high. Now, as we just mentioned a few minutes ago, this makes the body diode of Q2 undergo a reverse recovery, and so it takes some time for that reverse recovery to happen before this voltage at this node can start to rise. But eventually it does rise. I'm sorry, that's VGS. It's Vs that eventually rises. Okay, now when Vs is rising, what happens to the charge on this gate capacitance, CGD? you can see that this node here is all of a sudden going high. We're trying to hold VGS low. Okay, so that means the voltage across this capacitance has to increase along with the drain voltage. Okay, so if the voltage on this CGD increases, it means current must flow through CGD, according to I is C dV dt for this capacitor, to charge the capacitor. So we have current flowing in this direction through CGD. Now the big question is, once that current gets to the node here at the gate, where does it go from there? It has to complete the loop and keep flowing someplace. Okay, now where can it flow? Can it flow this way? Well, we hope it does. We hope the gate driver keeps pulling this node down the ground and keeps this MOSFET off. But the trouble is, the voltage here is 0, so we have 0 volts here, and we have 0 volts here coming out of this the driver, or V Thevenin is 0. You can see right there. So there's no voltage across R Thevenin, and if there's no voltage across this resistor, then by Ohm's law there's no current through the resistor. So we have 0 amps of current flowing through the resistor. What that means is that the only place that this current can go is this way, through CGS. And because of that, CGS will start to charge also, and we'll see VGS rise. Well, that's not good. If VGS rises above the threshold voltage of the gate, call it VTHR, then this transistor will start to turn on again. And when it turns on again, then it tries to pull this node back down, and what happens is we get oscillations, where this transistor will turn on and off many times, and we get all kinds of switching loss in the process. So the gate to drain capacitance causes problems, and it's a common problem that we have to battle when we're designing these kind of circuits. It's typical for the total charge in the gate to drain capacitance can be equal or even greater than the total charge in CGS. So there's a lot of charge here, and it's easy for that charge, if it all flows this way, to start charging up CGS. Well, the hope here is that when this voltage rises a couple of volts, then we do start to get current flowing through the Thevenin resistance and through the gate driver. And if the Thevenin resistance is low enough, we hope the gate driver can hold this node voltage low enough that the Q1 or Q2 doesn't turn back on. Another thing we can do to help the situation is to slow down the speed at which Q1 turns on. And so we can put a resistor in the gate of Q1 that makes it turn on more slowly and makes the voltage at this node rise more slowly. So dV dt is lower, and since I is C dV dt in this capacitor, we get less current here, and it's easier for the gate driver to pull that current out of the gate and keep the transistor turned off. So you'll often see little resistors of a few tens of ohms put in series with the gate. We often will put a diode in that direction so that the resistor slows down how fast the Q1 turns on, but the diode lets the driver turn Q1 off very quickly. Okay, so that was the switching transition where Q2 turns off, and then we have D2 conducting during the dead time, and then Q1 turns on. And during this time, we saw that we get switching loss. Caused by the reverse recovery of the body diode D2, as well as by shorting out the output capacitances of the devices, and possibly, but hopefully not, also from oscillations and spurious switching caused by the CGD problems. Let's now examine the other transition, where we turn Q1 off and Q2 on. So here we have Q1 initially conducting, which makes the switch node high and equal to the input voltage VG. When we turn Q1 off, what happens? Who conducts then? Well, again, we have positive current flowing in the inductor. Both transistors are off, and this positive inductor current has to flow somewhere, and it will flow out of D2. The body diode D2 is the only remaining diode or only remaining semiconductor device that can conduct current in that direction. So we get Q1 turning off, then D2 turns on, and Q2 turns on. What happens to the charge on the output capacitances of the MOSFETs? When we turn Q1 off, what happens is the inductor current can discharge these capacitors. And that inductor current will actually discharge this node down to ground. So we turn Q1 off here. And let's assume we have a nice big gate driver that can turn Q1 off quickly. And in fact, let's assume that the gate, if we get a big enough gate driver, we can turn Q1 off before the inductor current has a chance to discharge the voltage at this node by very much. So Q1 gets turned off right away while there's still very little voltage across Q1. The voltage is held close to zero by its capacitance. And so then the inductor discharges this node down to ground, discharging the energy in these capacitors. When we get down to ground, then the diode D2 will turn on. And then at some point later, after the dead time is over, our Q2 gate driver will turn on and turn Q2 on. What I've just described here actually doesn't have any mechanism for switching loss. Q1 turns off quickly. The capacitance, if nothing else, the output capacitance CDS holds the voltage across Q1 to be close to zero during the turn-off switching time of Q1. And then the inductor actually recovers the energy that was stored in these capacitors, and that energy flows to the load. There is no reverse recovery of a diode. We have D2 turning on, but no diode turning off. So there is no switching loss at this transition. And this switching transition of Q2, I'm sorry, of this one, Q1, D2, Q2, is what we call a zero voltage switching transition. So zero voltage switching can happen in a situation like this where the voltage across the MOSFET is held close to zero during its switching transition, and we have no mechanism for switching loss. Now, the other transition in the other direction was what we call hard switched, and it has switching loss from diode reverse recovery and the other things we talked about. So this converter here is what we would call a hard switched converter. There are converter circuits that get zero voltage switching at both transitions, and those are called soft switching or zero voltage switching converters. And they can have considerably higher efficiency because most of the mechanisms of switching loss have been eliminated. Circuits that achieve zero voltage switching at both switching transitions are more complicated than the one we're talking about here, and they're beyond the scope of this course. They're actually the subject of an entire different course that we teach at Colorado. However, it's interesting that even in the basic hard-switched buck converter with MOSFETs and good gate drivers, one of the transitions is essentially lossless, and it's only the other transition where we have substantial switching loss. In this lecture, we will discuss the bipolar junction transistor, or BJT, and its modern successor, the insulated gate bipolar transistor, or IGBT. Here's a sketch of the bipolar junction transistor. It's an NPN device, and we have a lightly doped N region or intrinsic region in the collector, so that this base collector junction, PN junction, really has the same structure as the classic power diode that we've already discussed. So under reverse bias conditions, where the collector voltage is positive, the base is more negative than the collector, and so is the emitter. And in fact, to turn this device off, the NP or PN junction between the base and emitter is reverse biased and turned off. So under these conditions, the device is off, and the electric field is in the N- region that is able to block the collector voltage. This is a vertical device, and again, this is a cross-sectional area of the transistor or of the chip, like the cross-sectional areas we've been drawing previously for the MOSFET. So to turn this device on, what we do is we have a driver circuit connected to the base and emitter that will forward bias the base emitter junction. So apply a positive voltage at the base with respect to the emitter to forward bias this junction, and when we do that, electrons from the emitter are able to diffuse across this junction into the base, where they become minority carriers. Because the collector is more positive voltage, these electrons can easily continue to flow, and they'll actually flow into the collector region. So by forward biasing the base emitter junction, we get the minority carriers into the base and into the N- region that are needed to conduct the collector to emitter current. In the process, you can see that these minority carrier electrons can go into the N- region and cause conductivity modulation that effectively reduces its on resistance. And so, like in the diode, this conductivity modulation gives us the best of both worlds as far as high voltage breakdown plus low on resistance. But the price we pay is that we have a lot of stored minority charge in the N- region that has to be removed if we want to turn the transistor off. Okay, so to turn the transistor off when we're in this situation, we have two choices. One is we can simply reverse bias the PN base emitter junction with zero base current and wait for these charges to recombine, and eventually they will. And once they do, then the transistor will turn off. But the other thing we could do is actively remove the electrons through the base terminal. Actually, we would pull the electrons backwards with a negative base emitter current that will remove the stored charge in the base and N- region. So So here's a sketch of what the typical waveforms look like. Here we have a base drive circuit that I'm representing with some Thevenin equivalent voltage source and resistance. Here is the voltage of that base driver voltage source. It starts out negative, which reverse biases the base emitter junction and turns the transistor off. At this point, our driver voltage goes high to turn on the base emitter junction, and you find the base emitter voltage then of the base emitter diode goes forward and goes to plus 0.7 volts, and then the transistor turns on, so it has low collector to emitter voltage and high collector current, and it's in the on state. To turn the transistor off actively, what we do is we make our driver actually go to a negative voltage, and with that negative voltage we actively remove the stored charge out of the base. Okay, and so the base current that we get, base current waveform, will go negative, and actually look a lot like the reverse recovery current of a diode. It's very similar in shape. So we get a large negative current to actively remove the stored charge. During this time, the base emitter voltage is high for at least part of the reverse recovery time. Eventually, the voltage will go low, and at that point, we'll see the transistor fully turn off. So in order to switch the transistor off quickly, we need this large negative current. And so an ideal base current waveform then looks like this. We have a large positive current initially to supply the charge to the base and turn it on. Then we have a small maintenance current to supply recombination in the base of the minority carriers, maintain the minority carriers in the base and the collector in minus region. And then to turn the transistor off, we have a large negative current coming out of the base to remove the stored charge quickly. Finally, once the transistor's off, we have no base current. Okay, one thing you might ask is, well, why can't we just build a big base current driver that can pull all this stored charge out very quickly and turn the transistor off just as fast as a MOSFET? Well, first of all, it takes a lot more current than a MOSFET, but second, there are limits to how large the base current can be. Very large negative base currents during the turn-off switching time lead to a failure mechanism that is traditionally called a second breakdown mechanism that comes from current crowding. So here's an example or a sketch of what happens. So we have a lot of stored charge in the N- region and in the base P region, and we're going to pull current out of the base and pull that stored charge out. So you can see the way the base and emitter contacts are built. A big negative current requires that we have lateral current flowing through the base region and really through the N- region also. This lateral current causes a voltage drop in the resistance of the silicon. So the silicon material has some resistance, and so from the direction of the current you can see that the voltage in the base will be more positive in the center than it will be at the edge. And what that does is it makes the base emitter junction be more positive in the middle than it is at the edge. And so during this time, the collector current will tend to want to flow there in the center. So we get what's called current crowding. And that current crowding heats up the center part of the base emitter junction more than it heats up the edges. And we get this phenomenon where the center part of the base emitter diode junction will hog the current. It can even go into thermal runaway, as we've discussed previously with the case of trying to parallel diodes. Effectively, you can think of this as like a distributed diode, and we want the current to flow uniformly across the whole region, but in fact here we're making it crowd in the center. And so this part will run hotter than the rest, and it will tend to hog all of the current, and this can make the transistor fail. So this is called current crowding. If you have a transistor that fails, you can actually cut it open and look at it under a microscope and see that it failed in the middle of the emitter, and then the engineer gets told that their negative base current at turn-off is too large. You can do a similar thing at turn-on, where the current's going the other direction, and in that case it can make the current all crowd at the edges of the emitter, and you can see that with a microscope also. So this is called the second breakdown mechanism that causes BJTs to fail, and the effect is that it limits how fast we can switch the practical BJT. Another different characteristic of the BJT relative to the MOSFET is that at high current, the BJT runs out of gain. And we're not going to go into the various reasons for this, but they're well understood. And so this is a plot of base current versus collector current for an actual BJT, power BJT that is rated 10 amps and 600 volts. And so if the BJT operates with a constant current gain beta, then you would expect the base current versus collector current to be a straight line with a slope equal to that current gain. But you can see that at high values of collector current, the slope becomes low and the transistor runs out of current gain. And this is classic for any BJT. For this particular device, it's rated 10 amps, and you can see that you can barely get 10 amps out of this transistor at all. That's really the limit. And so the current rating is determined really by this gain characteristic of the transistor. With a MOSFET, this doesn't happen. A 10 amp rated MOSFET will have curves like this that extend up to 20 and 30 and much higher currents. And the MOSFET then is actually thermally limited. So you can run a 10 amp MOSFET at 20 amps for very short times as long as the average is low enough and you don't overheat the device. So this loss of current gain provides another mechanism that limits the power that we can get through the BJT. The Darlington connected BJT is one of the classic kind of early approaches to improve the gain of high current or high voltage BJTs. And at high voltage, it's difficult to get high current gain at the same time. So a 1000 volt BJT might have a current gain of only a few. And the Darlington connected BJT gives us 2 transistors worth of gain, and the total gain from the input base current of the first transistor to the collector current of the combination now is the product of the 2 betas. So this is one of the traditional ways to build a high current or high voltage BJT. The one problem with driving this Darlington connection comes at the turn off. So if we have say another base driver, we connect here, and we do the same thing with it that we did with a single BJT a couple of slides ago, where to turn this device off we pull a big negative current out of the base. If we just had Q1 and Q2 with no diode, what happens is that our base driver will turn Q1 off quickly, and then once Q1 is off, there's nothing to actively remove the stored charge in Q2. So we have to wait for the minority charge in Q2 to recombine, and its switching time can be long. So we have a lot of switching loss and we have slow switching times. So this diode D1 is added to fix that, so that when our base driver turns off Q1 quickly, we still have a path to remove the stored charge from Q2 through D1, and our base driver is able to turn off Q2 quickly as well. Okay, so the BJT is one of the classic power transistors. Back when I was a graduate student, the BJT was the workhorse of the power electronics business, and then it was replaced by the MOSFET, which became commercially significant in the 1980s. And so in low voltage applications, say 600 volts and below, the MOSFET really is the device of choice today. Then at higher voltage applications, the BJT, it's not just it has been replaced by the IGBT for voltages above 600 volts. And so we're going to talk about the IGBT next. Compared to the MOSFET, the BJT is slower switching because it's a minority carrier device, but its on resistance for the same chip size is a lot lower than that of a comparable voltage MOSFET. Okay, here is the IGBT. Really, this is a combination MOSFET and BJT. And here's a sketch or a cross-sectional drawing of it. And this actually looks exactly like the drawing for the MOSFET. There's only one small difference, that this region right here is P instead of N. So there is in fact an extra P-N junction in series with what we call the drain of the MOSFET, that now is traditionally called the collector. So the insulated gate bipolar transistor has a gate just like a MOSFET, The source of the MOSFET is called the emitter in the IGBT, and the drain now is called a collector, and we have this extra p-n junction. Okay, what the p-n junction does is, under normal conditions where the device is turned on, we have current flowing this way across the p-n junction, and we have holes from the p material that diffuse across the p-n junction and go into the N- region and cause conductivity modulation. And so these holes, when the device is turned on, give us minority carriers that reduce the on resistance of the device. So we get a much lower on resistance in the N- region than we had in the comparable MOSFET, although we do have an extra p-n junction in series that has its forward drop. But what this lets us do in practice is to design IGBTs with very high voltages and have much lower on resistances than the MOSFET would have. So above 600 volts, the on resistance of the MOSFET goes up very quickly, but by doing this trick to get minority carrier injection, we can control that on resistance. And so we have 1200 volt and 1700 volt devices today that are very good and very significant commercially, and we have much larger voltage devices also for high power applications with breakdown voltages of in the 2000 and 3000 and even higher range. Okay, so effectively the IGBT looks like this. We have a MOSFET channel in the usual place, the same place as in the MOSFET, and then we have this p-n junction, and to first order you might say, well, we have a diode in series with our MOSFET. But what actually happens is a little more complicated than that. If you look at the structure, the substrate P material that is shorted to the what we're calling the emitter now actually gives us a PNP transistor. And so a more accurate equivalent circuit for the IGBT is this. It has a MOSFET, and then the MOSFET is connected to a PNP transistor. And we can actually get two different components of current flow. They're called I1 and I2 here. So we can have current flow this way through the channel of the MOSFET and out. That's called I1. Or we can have current flow this way, just through the PNP transistor and bypassing the MOSFET channel. And that's called I2. And effectively, the MOSFET drain current supplies the base current to the PNP transistor. Okay, so the effect of this on the switching, in fact the turn-off switching performance, is this. Our gate driver can turn the MOSFET off quickly, which makes I1 go to 0. But we still have minority charge in the N- region that will allow the PNP to continue to conduct. And so I2 continues to conduct. And in fact, there's no way to actively remove that stored charge from the N- region. So all we can do is sit around and wait for the minority charge to recombine. And once it does, then finally the PNP will turn off. So the IGBT has this fairly slow turn-off mechanism as a result. And that turn-off mechanism is traditionally called current tailing in the IGBT. So the turn-off current waveform looks like this. Originally when the device is on, the total current flowing this way is some combination of I1 and I2. And when we turn the device off, we turn off the MOSFET quickly, and so I1 goes away quickly, and you see the current decrease by the switching off of the MOSFET to this point. But after that, I2 continues to flow, and the fraction of the collector current that was I2 slowly decays while the minority carriers decay, and eventually the device turns off. And so this long time it takes the I2 component to decay is called the current tail. Okay, so the turn-off switching transition of the IGBT can be significant. It depends on the size and the rating of the IGBT, but it may be several microseconds, or in a good IGBT it may be, say, several hundreds of nanoseconds. So if we multiply the collector to emitter voltage by the collector current, we get the power loss in the transistor during this turn-off transition, and it has some area that is the energy loss during this turn-off transition, and we get switching loss then equal to the energy loss during the turn-off tail times the switching frequency. And in fact, there is some energy loss during the turn-on transition too, so we really ought to add the turn-on energy loss also. On data sheets, they will actually usually specify values of these turn-on and turn-off energy losses. There are some things we can do to control this current tail. One thing we could do is, in fact, by designing the circuit, we can actually control the current gain of this bipolar transistor, and we can control how much of this current flows in the I2 path versus the I1 path. So this is a design variable that the device designer has to play with. So if we make most of the current flow through the MOSFET and very little flow through the BJT, then what that does is it makes this the I1 portion be large and the I2 portion be small, and the current tail is smaller. So we'll get less energy lost during the turn-off transition. And so the designers can make a faster IGBT that way. But the price they pay is that the forward voltage drop is larger because more of the current is flowing in the MOSFET direction and less in the collector direction. So another thing that is often done is to make the opposite choice, which gives us more minority charge, stored charge. It makes the device switch off slower, but it gives us a smaller forward drop. And often many manufacturers even offer two versions of their devices, one that is optimized for forward drop and the other that is optimized for fast switching times. And so you have to decide which one will give you more efficiency in your application. Okay, so the IGBT really is the modern device of choice, really at voltages above 600 volts. And we have very large IGBT modules. These modules are composed of multiple individual chips, where the individual chip might be rated 50 amps or 100 amps. Multiple chips like that are packaged together on a common thermal substrate to make them run at the same temperature and share the current. And so then we have a module of many of these chips. That module might be rated at hundreds of amps or even 1,000 amps, and at high voltages, possibly several thousand volts. So these are very good high power devices. They can be controlled simply by switching their gate voltage from 0 to 15 volts and back, and so you can control a lot of power with a simple MOSFET-like gate. The forward voltage drop of these devices is a diode in series with an on resistance. So it's the on resistance of the N- region in series with the base emitter, or not base emitter, but the PN junction voltage drop that is in the collector of the device. The temperature coefficient of these devices is a combination of MOSFET and BJT behavior. At low current, the forward voltage has a negative temperature coefficient, but at high current, the MOSFET on resistance dominates, and we have a positive temperature coefficient, which means that the devices tend to share as you get close to the rated current of the device. The devices are slower than a MOSFET but they can be faster than a Darlington or an SCR or gate turn-off thyristor. You'll see switching frequencies for the low forward drop devices might be a kilohertz or several kilohertz, and for the fast devices, sometimes they're run at tens of kilohertz, and there are some lower voltage, very fast devices that can even be run at 100 kilohertz or more. Here's one last brief note about switching loss and its effect on switching frequency and efficiency. So we've talked about different mechanisms now for switching loss from the different devices and other mechanisms around the converter, where we found that we got energy loss every time we switch. And so we have different mechanisms where we could calculate the total loss during the switching transition, which might come from the reverse recovery, or from the switching times, or from ringing and energy stored in parasitic capacitors and inductors in the converter. And in each case, we could find some total amount of energy that was lost during the switching transition. So what we can do now for whatever our converter is we can add up all of those losses and get a total amount of energy that is lost due to the different switching mechanisms during each switching period. So then the total switching loss will be that total energy loss multiplied by the switching frequency. Okay, so this is what this loss scales linearly with frequency, and as we turn up the switching frequency, we turn up the switching loss. Now, what is the effect of this on the overall efficiency? Well, we have loss mechanisms that come from different sources. Back in Chapter 3, we talked about conduction losses and how to model those. Those losses depend on, say, the output current, but they don't depend on the switching frequency. So if we, say, are interested in the efficiency and the total loss maybe at full load or at some critical load power or operating point, we can calculate the conduction loss at that point, and it's a given value. We also have what are called fixed losses that don't depend on switching frequency, they don't depend on load power, they're just a fixed loss that we're stuck with. An example of that is the power that it takes to run the controller circuitry for our power converter. And then finally we have the switching loss that again scales linearly with switching frequency. So the total loss then is a sum of all of these three things. Okay, now given this, we can calculate the efficiency. So the efficiency will be the output power over the input power, or the output power divided by the output power plus this loss, and we can plot that versus switching frequency. And what we find is that the efficiency goes down, of course, as the frequency goes up. Here I've plotted the efficiency for some typical values, and I have switching frequency varied on a logarithmic scale on the horizontal axis. And so what happens is at low switching frequency, we find that the conduction loss and the fixed loss dominate, and the switching frequency is relatively low. Now, if we're in this situation, we may as well raise the switching frequency. It's true that that will make the efficiency go down a little, but not by very much, because the total loss is dominated by other things. And the size of our reactive components, such as our inductors and capacitor, filters in the converter, and if we have a transformer in our converter, the power transformer also, these things depend on the frequency. If you raise the frequency, the reactive elements get smaller. So if we're down at this point, we may as well raise the frequency because it makes our reactive elements get a lot smaller, so we have a smaller and less expensive converter. And there's very little penalty in efficiency when we do that. On the other hand, if we're at high frequency, the switching loss term dominates the other terms, and then our total loss is very sensitive to switching frequency. So we probably don't want to raise the frequency too much, or our switching loss will become large and our efficiency will really suffer. So there's some good sweet spot of switching frequencies in the middle where the switching loss is starting to hurt, but not too much yet. And that's then represents a compromise between the switching loss and its effect on efficiency and the reactive element size. So then here you can even solve this formula for the critical frequency where the switching loss is equal to the other losses. At that point, the total loss is twice the loss you would get at zero switching frequency. And that gives an estimate for a given technology of what kind of frequencies we can run at. You may choose to run at a little higher or a little lower frequency depending on the details of the application, but we'll probably run somewhere in this range. Okay, so we have a fundamental trade-off then between efficiency and switching loss versus the reactive element size. And the engineer has to choose the switching frequency accordingly. So it depends on the application. At high powers and high voltages, we tend to run at low frequencies, 10 kilohertz or 1 kilohertz, depending on the voltage of the IGBT. At high frequency, low voltage applications with MOSFETs supplying, say, 1 volt computer processor chips might run at several megahertz, and this F-crit may be way up here, at a much higher frequency. In recent years, we've seen the introduction of new power semiconductor devices using wide bandgap semiconductor materials. Instead of silicon, they use silicon carbide or gallium nitride. These materials allow significant improvements in the trade-off between breakdown voltage, forward voltage drop, and switching speed. So in this brief lecture, I'm going to describe or summarize why that is so, and then we'll talk about several of the commercially available devices, specifically silicon carbide Schottky diodes, silicon carbide MOSFETs, and gallium nitride HIMT devices. Here is a formula that you see often quoted in the literature for the specific resistance, in other words, the on resistance multiplied by the active chip area, for a majority carrier device such as a MOSFET. The on resistance is a function of the breakdown voltage, V sub B, as well as the material mobility, mu, the material permittivity, epsilon, and the critical electric field at the onset of avalanche breakdown, E sub C. So if you want to increase the blocking voltage of your MOSFET, for example, the on resistance will increase as the breakdown voltage squared. So high voltage MOSFETs have much higher on resistances. But the interesting thing here is the other terms, these denominator terms, that are a function of the semiconductor material. And so it turns out that these wide bandgap materials, such as silicon carbide and gallium nitride, have much higher critical fields, E sub C, that allow a significant improvement in this trade-off. Here's a comparison of the parameters for these basic materials. So silicon has a band gap of 1.12 electron volts. Silicon carbide and gallium nitride have much higher band gaps, and the result of this is that the critical fields are much higher. So with this significant increase in critical field, then we can design the device to have a much lower on resistance at a given breakdown voltage. The electron mobilities are also changed. In fact, it turns out that silicon carbide has lower electron mobility, which is bad. That means more on resistance. And gallium nitride, for reasons we'll discuss in a minute, has higher electron mobility through what are called hot carriers. that exist in the two-dimensional electron gas in the device. Because of the lower mobility of silicon carbide, it actually is inferior at low breakdown voltages, and silicon is better. But when you get above 600 volts, then silicon carbide begins to exhibit significant advantages. And so we see good silicon carbide MOSFETs at voltages starting at 600 volts and going commercially now to 10,000 volts. GaN doesn't have that issue, and in fact GaN is highly competitive with silicon as MOSFETs at low voltage, or at least as controlled transistors at lower voltages. So we see both sub 100 volt GaN devices and we see 600 volt GaN devices that are very good. We can also make Schottky diodes with these devices, and so we see high voltage Schottky diodes made especially out of silicon carbide, and there are majority carrier devices that have no significant reverse recovery, and we get silicon carbide Schottkys at 600 and 1200 volts and higher. In silicon carbide we can build MOS gates. Silicon carbide can have an oxide layer that is similar to the oxide layer in silicon, and we can build MOSFETs with it. This is not true in other materials, and in particular it's not true in GaN, so we aren't able to build MOSFETs with GaN, and the devices that we have are junction FETs instead. Silicon carbide MOSFETs then can be built with a vertical structure that's very similar to the vertical MOSFET structure seen in a silicon MOSFET. And it has all the same structure. It has a body diode and so on. In GaN this is not the case. GaN is a thin film material that is deposited on top of a substrate, and so we have lateral GaN devices. Because GaN devices are lateral, it's somewhat more difficult to scale to higher voltages and currents, although we're seeing that being done commercially. The thermal coefficient of expansion of the thin film GaN device must be matched somehow to the substrate that it's deposited on, and there are issues there as well that affect the structure of the GaN devices. So as I mentioned, we have silicon carbide Schottky diodes. These were the first wide bandgap power devices to become commercially important. We see them available at 600, 1200 volts and higher. Because the Schottky diode is a majority carrier device, there's no significant reverse recovery. They do have a higher forward voltage drop, typically 1.5 to 2 volts. But they have much lower switching loss because they're a majority carrier device. What we find then is higher conduction loss, lower switching loss, and in most switch mode applications at say 600 volts, you see a significant gain in overall system efficiency. They also cost more than silicon, so there's a trade-off. In the area of MOSFETs, we have silicon MOSFETs at voltages up to 600 or 700 volts. If you want to go to a higher voltage, then generally we use a silicon IGBT. In the case of silicon carbide, we have silicon carbide MOSFETs starting at 600 volts and commercial devices available at up to even 10,000 volts. And these are real MOSFETs that are very similar to the silicon MOSFETs, but with good properties at high voltage. So they have much lower on resistance than a silicon MOSFET. They do have a PN body diode, just like the silicon MOSFET has. In the case of silicon carbide, the body diode has a forward drop of 3 to 4 volts, so it's higher. The body diodes generally are built with good reverse recovery times below 50 nanoseconds. And so we can switch these devices at a much higher frequency than we could operate an IGBT. So where the IGBT might run at 5 or 10 kilohertz, these MOSFETs can run at much higher frequencies. Here are some sample commercial devices that you can buy today. I've listed some from 650 volts up to 1700 volts with nice on resistances that are tens of milliohms. In GaN, we're not able to build an oxide layer, and so we can't build a MOS gate, and what we see for GaN transistors is what is basically a junction field effect transistor, where there's a source and a drain with semiconductor material between them, and a gate that is built as a diode junction on top of that material. So when we negatively bias the gate, we can turn off the channel. When we forward bias the device with a positive gate voltage, there is current that can flow between the source and the drain. The traditional junction FET is a depletion mode device, so at zero gate voltage it's forward biased or turned on, and to turn it off you have to apply a negative voltage to the gate. Early GaN transistors were in fact depletion mode devices, and we have cascode type circuits that combine a silicon MOSFET with a depletion mode GaN device to build what is effectively an enhancement mode transistor. There is another twist here in the GaN devices. These are what are called high electron mobility transistors, or HEMTs. They are also characterized as having a heterojunction, which means that we have two different materials having different band gaps. And in the GaN device today we have aluminum gallium nitride, which is a low band gap semiconductor material, and then below it is GaN, which is a high band gap or wide band gap material, and there is a junction between them. When we place materials having different band gaps in contact at this heterojunction, it can form what is called a two-dimensional electron gas, which is shown here. And this two-dimensional electron gas has carriers having high energies that are able to conduct or jump very easily from atom to atom and effectively have very low on resistance or high mobility. And this is one of the keys to the GaN device of why it can achieve very low on resistance. To turn this device off, we negatively bias the gate, which will extend its depletion region below the gate and disrupt the 2D electron gas so that the source and drain have no conducting channel. So this device can have a high breakdown field because it's a wide band gap material, and at the same time it can have very low on resistance from this two-dimensional electron gas. The GaN device is a junction field effect transistor that traditionally is a depletion mode device. More recent GaN power transistors actually have their gate threshold voltages shifted positively so that they become effectively enhancement mode devices. So with zero gate to source voltage, the device becomes turned off, and we apply a positive voltage greater than the threshold to turn the device on. However, you can't apply too positive of a voltage, or you will forward bias the gate to source diode, and then you'll get significant positive current flowing into the gate, which actually can damage the device. So we have to limit the gate current and must apply a gate voltage that is not too high. Often then we'll drive these devices with a 0 to 5 volt gate drive signal to switch the power GaN FET. So in the on state, the device is on with a low on resistance. This is with the gate to source voltage greater than the threshold of maybe 3 or 3.5 volts. In the off state, we'll generally apply 0 volts between gate and source to turn the device off. The device does not have a built-in body diode the way the MOSFET structure has. But having said that, it's still possible to get the device to conduct if you apply reverse current or voltage through it. Let's suppose we have the gate shorted to the source, and then we apply negative drain voltage. In this case, with reverse operation, the drain can actually become the source, and the source the drain. So if you apply a negative enough voltage to the drain, we'll have positive voltage at the gate with respect to the drain, and if that positive voltage is more than the threshold, the device can turn on. So in that case, the device will conduct, and it will conduct current in this direction with a forward voltage drop between source and drain equal to the threshold or a little bit greater. So it's possible to have a reverse conducting device without actually having a physical body diode. So this behavior is similar to the MOSFET that has a body diode, except that there's no reverse recovery because there's no real diode. Also, the forward drop is fairly large. It's greater than or equal to the threshold voltage of the gate. So you see, GaN devices are actually current bidirectional devices with very fast switching times. So here's a comparison of 600 volt transistors, both a silicon MOSFET and an equivalent GaN transistor. And here it's assumed that they're sized to have the same on resistance. Of course, to achieve this on resistance, the GaN has a much smaller area, and as a result, it has much lower gate charge. So because it's a smaller device, the charges are smaller and it can switch much faster. So we see lower gate charge, lower output capacitance. The only negative thing, perhaps, is the voltage drop when reverse conducting. But then again, it has negligible reverse recovery. So wide bandgap semiconductors have become commercially important. While they cost more, they can operate at higher voltages with higher switching speeds and with lower forward voltage drops. Currently, the important devices are the silicon carbide Schottky diode, the silicon carbide MOSFET, and the GaN HIMT device. Homework assignment 2 is concerned with simulation of a buck converter that steps 12 volts down to 1 volt at 20 amps to supply a microprocessor. You will add a synchronous rectifier to a buck converter to improve its efficiency. In this lecture, I'm going to illustrate how to use the schematic capture capabilities of LT-Spice, and I'm going to work an example in which I will add a synchronous rectifier and the associated circuitry in a boost converter example. Here's the circuit that we'll start with. This is a boost power stage having input voltage VG, an inductor L1 with a MOSFET and diode, and then the output R and C. This converter is intended to step 12 volts up to 24 volts, and it operates at a duty cycle of a half. Here we have a voltage source to set the duty cycle to 0.5. This voltage goes into a pulse width modulator that then generates the switched waveform going to the driver, which then turns the MOSFET on and off. To insert a synchronous rectifier in the circuit, what we need to do is to take the diode and replace it with a MOSFET. We need to drive it with a gate driver circuit. The gate driver needs a power supply to supply the gate driver, and we're going to derive that power supply from the 12 volts at the input. We need to generate complementary drive signals for the two transistors, so we're going to add what's called a dead time generator that takes the pulse width modulator logic output signal and generates a second complementary signal to drive the synchronous rectifier FET. The switching converter library that accompanies these LT-Spice files for this course includes what's called a dead time generator block, which is shown right here. This dead time generator takes the control input signal coming from the pulse width modulator, C, which is shown here in green, and it generates two drive signals, C1 and C2. So C1 is intended to drive the main power FET of the converter, and C2 is intended to drive the synchronous rectifier FET. So these are complementary signals. When one is high, the other is low, and vice versa, so that they switch at opposite times. This dead time generator also generates what's called a dead time, and here you can see the output. This is the C1 output in red and the C2 output in purple, and there are dead times here produced by the dead time generator block that can be set as a parameter for the block. In this case, it's set to 100 nanoseconds. So the object here is to turn off one FET, wait for the dead time, and then turn on the other FET. So this is called break before make operation. We want to make sure that both FETs are not on at the same time. And the dead time here set to 100 nanoseconds is supposed to be large enough to make sure that the switching transition of the first device being turned off can complete before the second device is told to turn on. Here is the LT-Spice boost converter. To remove the diode, we use the scissors tool. So I click on that tool and then I can just cut away the diode. On the Macintosh, it doesn't have the toolbar like this. Instead, you have to right click with the mouse to bring up menus that include all of these functions. Okay, we'll insert a device here. So I click on that one, and let's find the MOSFETs. Okay, so I will insert an NMOS transistor right here. Okay, and then to stop this, we'll hit escape. I want to change this transistor into a specific device, so I right click on it and I can pick a new MOSFET. So here's a library of parts that are built into the LT-Spice libraries. These transistors, their models are optimized so that the LT-Spice simulation will run quickly, and I strongly suggest you choose one from this list. Okay, so I'm going to choose this IRF-Z44N that is a 55 volt rated transistor with an on resistance of 14 milliohms. Next thing I'm going to do is add the dead time driver from our library. So we go here to the component list, and I need to go to the directory that has the downloaded files from the course website, and here is the block called dead time that we can insert. So I'll put it right there, and then we get the little pencil to draw some wires to connect this up. So connect its input up to C. I take the C1 output and we'll connect that to the driver input of the main transistor. Now we need the driver for the synchronous rectifier. I can either insert a driver from the library or I can copy the one we already have. Let's take the duplicate or copy function, copy this driver, and I'll just move or place one up here. Lastly, we need to add the bootstrap power supply for the high side driver. So we derive this from the 12 volt input. What we'll do is add a diode, and I think I'll just use another one of these Schottky diodes for that purpose. So I'll copy that and place it over here. Okay, we need to add a capacitor for this bootstrap power supply. That I'll place right about there. And we need to connect these components up. Okay, let's see, we need to set the value of the capacitor. I'm going to make it be 10 microfarads. Alright, I think we're ready to go. Let's press the run button and see how it works. Here I've zoomed in on the switching transition. So this upper waveform is the switch node voltage right at the switch node between the two FETs. It's high, so the synchronous rectifier is on here. The gate driver turns the synchronous rectifier off right there, and you can see the voltage increase a little bit. What's happening is the body diode of the synchronous rectifier is being forward biased by the inductor current, and it's turning on. So we get a higher forward voltage drop during this short time during the dead time. Here you can see the gate drive, or the gate voltage of the synchronous FET is going low right there, which coincides with the jump in the switch node voltage. The synchronous FET is fully turned off here, and the green waveform is the gate voltage of the main FET, this M1 FET in green. So the gate driver starts turning it on right here, and there's some rise time on the gate voltage. At this point here, the switch node voltage falls, and we have a low voltage after that. Here's a magnified view of the current in the output capacitor at the time when we're turning off the synchronous rectifier, so that same switch transition. And what happens, as we just saw, was that the body diode of the synchronous rectifier is turned on during the dead time, and then when we turn on the lower MOSFET, the body diode of the upper FET goes through a reverse recovery. And that reverse recovery comes out of the capacitor and goes through the two MOSFETs, so it goes around this loop. The green waveform is that capacitor current, so it's near zero here, and it goes down to a very large negative value. What is that? About minus 55 amps. The area of this current spike is the charge that is pulled out of the capacitor and flows through the two MOSFETs. So this current is caused primarily by the reverse recovery of the body diode of the synchronous FET. Also, some of this charge represents the change in charge on the output capacitances of the two MOSFETs. Okay, so if we define this area as Q, you can estimate what Q is. It's the area of this triangle, so if we find the switching time and this amplitude, we can work out what Q is. We could also, if we're clever, figure out how to get LT Spice to tell us the area of this triangle. But in any event, its area we can define as some charge Q, and we get this charge drawn out of the capacitor once per switching period. So it represents an average current that is the charge divided by the switching period. We get that much average current flowing out of the capacitor as a result of this, and this then represents a power loss, or at least a power flowing out of the capacitor of this current multiplied by the output voltage. So Q over TS times the output voltage. And this average power essentially is switching loss. It's the switching loss induced by the reverse recovery of the body diode primarily, as well as some power loss induced by charging or discharging the output capacitances of the MOSFETs. A little bit of that capacitive power actually is not lost, but this primarily is from the reverse recovery. So on the homework, you will work out or estimate this power loss predicted by LT Spice due to the diode reverse recovery, and compare that to the total loss in your circuit. So the homework assignment is to start with a basic buck converter. So this circuit is given on the course website. It has a main FET and a diode with the output filter and the output load. Again, we want, in this microprocessor, we want to supply 1 volt at 20 amps. So we'll have to adjust the duty cycle so that we get 1 volt with high accuracy. And you can measure the efficiency of this circuit, including both the input power, the gate driver power, and the output power in your calculation. And then, as we just did in this boost example, what we'll want to do is, in the buck, replace this diode with a MOSFET as a synchronous rectifier like this, along with its gate driver, and we'll want to add a bootstrap power supply to the upper driver, and then work out the efficiency in this case, and look at things like the current spike from the reverse recovery. There's also some discussion questions at the end of the assignment, which are optional, but if you wish, you may want to further investigate how to improve the efficiency of this circuit. If you look here, we have 2 different MOSFETs. In the power electronics field, we figured out that synchronous rectifier power supplies like this can be better optimized if the MOSFETs are different, so you might consider how this was optimized, and in fact look at whether you can find other MOSFETs in the LT Spice library that would further optimize it. We can also optimize the dead time and the gate driver resistors to get some improvements in efficiency as well. And it's worth looking at that and trying it in LT-Spice if you have the time. Having discussed how to realize switches using semiconductor devices and to implement things such as single quadrant or two quadrant switches in a switching converter, we're now in a position to discuss what is known as the discontinuous conduction mode. And Chapter 5 covers first the origin of the discontinuous conduction mode, and then how to solve it, and we'll do some examples of solving buck and boost converters that operate in this discontinuous conduction mode. The converters that we've discussed so far in this course operate in what is called the continuous conduction mode, by contrast to the mode of operation we're going to discuss now. The discontinuous conduction mode occurs because there is a ripple in the current or voltage waveform that is applied to one or more of the switches inside the converter, and this ripple is larger than the DC component. And as a result, the current or the voltage attempts to reverse through the switch. Now, if we realize the switch to be a unidirectional switch, and we try then to reverse the polarity, the switch doesn't behave in the way that it was intended. And so it will switch on or off at a time that does not coincide with the driver signal switching. And so we get additional intervals or subintervals within the switching period as a result. And this completely changes the characteristics of the converter. The most traditional discontinuous mode operation occurs because the inductor current ripple is greater than the DC component of current, and this causes the current through the switches to try to reverse direction. The diode won't allow it. The diode will turn off instead, and we get a third period during the switching period, and this changes the characteristics of the converter substantially. So when the discontinuous mode happens, what we're going to find is that the output voltage now becomes load dependent. In continuous mode, say for a buck converter, the output voltage is the duty cycle times the input voltage. Any dependence on load is small and only comes from the effects of losses in the converters. In the discontinuous mode, though, we have a first order dependence of the output voltage on the load current. So the properties of the converter change drastically. We then all of a sudden we have a high output impedance. We're going to find it turns out that the dynamics of the converter that we're going to discuss in several weeks, those dynamics change very substantially, and in fact they're simpler in discontinuous mode. We also find that when you remove the load, the discontinuous mode causes the output voltage to not be controllable, and it can do bad things, so we have to account for that. Some converters are designed on purpose to always work in discontinuous mode. One of the good things about it is that the current goes to zero before the end of the switching period, the diode turns off, and then there's no reverse recovery when the MOSFET is next turned on. So there can be less switching loss. But on the other hand, there are higher peak currents, and so we can get more conduction loss, and there's a trade-off then. Even if we don't intentionally design a converter to work in this mode, many converters will operate in the discontinuous mode at low output power, and so we have to be able to analyze and know what's going to happen then at those operating points. So what we're going to do in this lecture is discuss the origins of the mode and find the mode boundaries, the conditions under which we operate in continuous or discontinuous mode. And then in the next several lectures we will analyze converters to find their output voltages and other things when they operate in the discontinuous mode. So here's an example. We have a basic buck converter, and we've realized the switches with conventional single quadrant switches of a transistor and a diode. Here is what the inductor current waveform looks like in the continuous mode, and it's the waveform we've been drawing all along this in this class. So it has a DC component that we're labeling capital I, plus it has some switching ripple that has a peak magnitude of delta I. Okay, we previously analyzed this circuit and we know how to calculate capital I and delta I now. Here are the expressions. So the DC component, capital I, is the load current, V over R. And delta I, the peak to average ripple, is the slope times the time, which we can write in terms of VG like this. And the ripple depends on the duty cycle, VG, the inductance, and the switching period. Okay, the interesting thing about this is that the DC component depends on the load resistance, or on the current that the load decides to draw, but the ripple doesn't. The ripple depends on all kinds of things, but the one thing it doesn't depend on is the load resistance or the load current. So what happens if we, say, increase the value of R, or our load all of a sudden decides it doesn't need as much current? Well, that will make the DC component, capital I, go down, but it won't change the ripple. Now, what's important here is actually the effect of that on the diode. So when the diode is on, it conducts the inductor current, and the diode current waveform looks like this. So when the diode is on, it has the same capital I plus the ripple, and the minimum diode current happens right there at the end of the switching period. And that minimum value is the DC component of current minus the ripple. Okay, so the diode current has to stay positive for the diode to work. And when we account for the ripple, the minimum diode current is actually less than capital I. So let's consider increasing the value of R to the point where the ripple equals capital I. Actually, we reduce capital I so it's equal to the ripple. Then the inductor current looks like this, and the diode current follows the inductor current for the second half of the period. So you can see that the diode's current starts out at capital I plus delta I, and it ends at capital I minus delta I, which for this particular load current is equal to 0. Okay, what happens if we increase the load resistance even more? Well, here is that case. DC component of load current and inductor current, capital I, is now less than delta I. So even though the average current and the load current are positive, they're less than delta I, and so the diode current and inductor current go to 0 before the end of the switching period. Okay, once that happens, the diode will turn off, and it will not allow the inductor current to continue in the same direction and go negative. So we get a third interval now. From the point the diode turns off until the end of the switching period, where the diode and the MOSFET are off and the inductor current just sits at 0 current. So now our switching period is divided into 3 intervals. There's the D1 interval, the first interval, which we're also going to call DTS. It's the D is the MOSFET duty cycle, and D1 is the duty cycle of the first interval, and they're the same here. We have a D2 interval now when the diode conducts, and we have a D3 interval when nobody conducts. So this is the discontinuous mode of operation, and this extra interval changes all the equations of the converter. So first of all, we need to be able to write the equations of the mode boundary, and we have a way to do that. That the mode boundary happens when delta I is equal to the DC component capital I. Okay, and in fact the conditions then are that we're in DCM, or discontinuous mode, when capital I is less than delta I. Now at the boundary, the continuous mode equations are still valid, So we can plug the continuous mode equations that we had for capital I and delta I into these equations to find the boundary. So here's the expression for capital I in terms of Vg. Here's the expression for the delta I. And so we can plug them into this, and we can solve. So what? The Vg's cancel out. We can move the 2L and TS over to the left-hand side and cancel the D's, it looks like, and we'll get this expression. So this is the expression or the condition for operation in the discontinuous mode. Okay, the quantity on the left-hand side is a function of element values in the switching period. It's traditional to call this quantity K, and so in the power electronics business we generally call capital K is 2L over RTS. And this 2L over RTS factor keeps coming up in many of our equations over and over from here on. The right-hand side is the critical value of K at the boundary between modes, so we call that K crit. So the right-hand side is a function of duty cycle. It will vary with duty cycle. But when K is equal to K crit, then we're at the mode boundary, and if K is less than K crit, then we operate in the discontinuous conduction mode. For the buck converter, we find here that K crit is equal to D prime. For different converters, they'll have K crit will be a different function of duty cycle, but in general we can write this expression for the mode boundary in some equation of the form K less than K crit of D for discontinuous mode. So here's a plot of that. K crit for the buck converter is 1 minus D, or D prime. So here's a plot of K crit versus D. So K crit is 1 at D of 0, K crit is 0 at D of 1, and it looks like that. Okay, so we compare that to K. So suppose K is less than 1. The maximum value of K crit is 1, so if K is less than 1, say some value like here, then we'll be in discontinuous mode over this range, where K is less than K crit. And then at higher duty cycles over this range, we'll be in continuous mode. On the right side here is another example where K is bigger than 1, and in that case K is always greater than K crit, so we're always in continuous mode then. For the different converters, buck boost and buck boost, with their K crit expressions labeled. So K crit for the buck is D prime. We're going to show in an upcoming lecture that K crit for the boost is D times D prime squared. And on the homework, you're going to work out for the buck boost that K crit is D prime squared. For the buck, the maximum value of K crit for any D between 0 and 1 is 1. So if K is greater than 1, then we're always in continuous mode. But if K is less than 1, then we have to worry about discontinuous mode. For the boost, this maximum value turns out to be 4/27. We'll discuss that. It's an interesting number that comes out of nature here. The boost is less likely to run in discontinuous mode, but if K is smaller than 4/27, then it can. For the buck boost, the maximum value of K crit is 1, so again, with K less than 1, we may run in discontinuous mode. Okay, so that's the mode boundary. In the next lecture, we're going to solve for the output voltage. In this lecture, we will discuss how to solve for the output voltage of a converter operating in discontinuous conduction mode. And I'm going to explain it for the example of a buck converter. What we need to do is to extend the ideas developed in Chapter 2 to apply to this case where we have inductor current ripple that is large. So here's what we talked about back in Chapter 2 at the beginning of the course. We had this technique of inductor volt-second balance, which said that in steady state the average voltage applied to an inductor is 0. And that's true in any circuit, and it doesn't matter if it's a continuous mode or discontinuous power converter or something else. So it still applies. And same thing with charge balance. On capacitors, in steady state, the average current through a capacitor is also 0, and we can apply this to solve our discontinuous mode converter as well. But where we have to be careful is the small ripple approximation. So really, by definition here, in discontinuous mode, we have an element where the ripple is large. And we're talking in these lectures about the common example where the inductor current ripple is large compared to the DC component. So we can't approximate away the inductor current ripple now in solving our discontinuous mode converter. And we're going to have to use some other arguments in order to handle the inductor current and include its ripple. On the other hand, we still want the output capacitor voltage to have small ripple. And generally we're going to put a capacitor on our output that will be big enough to filter out the ripple and have small voltage ripple at our output. So we can apply the small ripple approximation to the capacitor voltage but not to the inductor current. Okay, so let's do this example of the buck converter in discontinuous mode and apply these arguments to solve for the output voltage. Here's our buck converter then, and we now have 3 subintervals. First interval where the MOSFET is on gives us this circuit. For the second interval, the MOSFET is turned off and the diode is on, so we get this circuit with the left side of the inductor connected to ground. And then we now have a new third interval where both transistor and diode are off. The inductor current has gone to 0, then the diode is turned off, and the left side of the inductor now is left hanging in space, not connected anywhere, with 0 current flowing through the inductor. So as usual, we will write the circuit equations for each interval. So here we have, for the first interval with a MOSFET on, as usual, we can write the inductor voltage is VG minus V, like this. And the capacitor current would be, from the node equation, it would be the inductor current minus the load current V over R. So we get that the capacitor current is IL minus V over R. Next, we apply the small ripple approximation. So the output capacitor voltage V has small ripple, and we can replace V in these two equations with capital V to ignore the ripple in the output. So that gives us these terms. But the inductor current has large ripple, and we can't approximate IL of t by its DC component. So we're going to just leave IL of t alone for now, and we're going to have to handle the ripple in IL with some additional arguments in a couple of minutes. For subinterval 2, the diode conducts. The inductor current is positive, and we have this circuit with the left side of the inductor connected to ground. We can write that the inductor voltage is minus the output voltage, like this. The capacitor current is, again, the inductor current minus the load current, like that. And we can replace V of t by the DC component capital V using the small ripple approximation to get these equations. And again, the inductor current is left as IL of t. For subinterval 3, the inductor current has gone to 0, the diode is turned off, so the right-hand side of the inductor is connected, or not connected, it's hanging in space. What is the inductor voltage during this interval? Well, the inductor voltage is the derivative of the current. We know what VL of t is L times DIL dt. IL is 0, so the derivative of IL is 0, so we get that the inductor voltage is 0 during this interval. So VL is 0, we can simply write that. IL is also 0. The capacitor current is the inductor current minus the load current, although the inductor current is 0. So really all we need to say is the capacitor current is minus capital V over R, where we apply the small ripple again to V of t. So here's the inductor voltage waveform. It's a positive voltage during the first interval, a negative voltage during the second, and it's 0 during the third interval. We can apply volt-second balance to this waveform in the usual way. We have a third interval. The inductor voltage can be written as D1 times the voltage during the first interval plus D2 times the voltage during the second interval, which is minus V, plus D3 times the voltage during the third interval, which is 0. And by volt-second balance, this is equal to 0. So we get this equation. You can solve it for the output voltage, and we get this expression for the output voltage. Now in continuous conduction mode, without losses, this equation told us what the output voltage of the buck in continuous mode was. But here we have an unknown. The duty cycle D2 is not known. D2 really depends on when the inductor current goes to 0 and the diode turns off, and we have to do further analysis to find D2. So at this point we have an equation with two unknowns, V and D2, and we need to get more equations. So let's keep going. Let's apply charge balance next. Here's our node where the capacitor is connected at the output terminals of the converter. We can write the node equation at that point, which for the buck converter, the inductor is connected there. So we can write that the inductor current is equal to the capacitor current plus the load current, like this. And what we want to do is apply charge balance to the capacitor. So the hard way to apply charge balance is to take the inductor current waveform that we already drew and subtract the load current to draw the capacitor current waveform and find its average. But a little bit easier way to do it is to look at the original node equation at this node and compute the DC components of each term. So we can say that the DC current flowing out of the inductor into this node equals the DC component of the capacitor current plus the DC component of the load current. And the capacitor current by charge balance has no DC, it's 0. So we get that the average inductor current, or DC component of inductor current, equals the load current. So all we really have to do is take the inductor current waveform that we've already drawn, find its average value, and equate that to the load current. I should caution you at this point, this expression of finding the average inductor current and equating it to the load is really only true in the buck converter, and it's because the inductor is what's connected to the output node where the capacitor is. We'll do another example next time with a boost converter where it's the diode that's connected to the output node instead of the inductor, and in that case we have to draw the diode current waveform and find its DC component. Okay, so here's the inductor current waveform. We'll find its DC component and equate it to the load. Here's the calculation for that. The DC component of inductor current is found, as usual, by averaging the inductor current over one period. So the average is the integral divided by the period, and the integral is the area under the curve. So we need to find this area. Okay, the area, and for this waveform we have the area of a triangle, so we have to use the triangle formula, which would be 1/2 the base, and what the base is D1 plus D2 times TS, times the height. I've labeled this peak current I peak. Okay, so that's the area, or the integral. If you divide by TS, we get the average value. Okay, and so here it is divided by TS. And the other thing I've done here is substitute in an expression for I peak. Here's how we find I peak. The inductor current starts the period at 0. It starts at 0 because we're in discontinuous mode, and we ended at 0 in the last period. We go up during the first interval with a slope given by the applied voltage over L. So Vg minus V over L is the slope of the inductor current during the first interval. Here, multiply that by the length of the first interval to get the change in current, and that's I peak. So we can plug that expression for I peak into here, and finally we get this expression for the average inductor current, and then lastly we equate the average inductor current to the load current, and we get this expression that comes from charge balance on the capacitor. So we have two equations. The first one was from volt-second balance. The second one is from capacitor charge balance. We have two unknowns, the output voltage and D2. So we can solve. So I'm not going to go through the algebra in this lecture. I'll actually illustrate the algebra in the next example of the next lecture. But basically you solve one of these equations for D2, plug it into the other equation, you then get a quadratic expression that we have to find the roots of, and finally from doing that we can solve and get this equation for the conversion ratio V over Vg of the buck converter in discontinuous mode. This equation is a function of D1, the duty cycle of the first interval. It's also a function of K, which is the same 2L over RTS that came out of the mode boundary equation in the last lecture. Here's a plot. So this is M, which is V over Vg, versus duty cycle. And we have now two choices for M. If we're in continuous mode, when K is greater than K crit, then M is equal to D. Whereas if we're in discontinuous mode with K less than K crit, M is given by the expression from the last slide. So we can plot this for different values of load resistance or different values of K, and here are some different choices. So for example, for K equals 0.1, to plot this we first have to plot our K versus K crit formula. Remember, K crit for the buck converter was D prime, so it looked like this. And if, say, we do the K equals 0.1 curve, so here's 0.1 for K. K is less than K crit for D from 0 all the way up to 0.9 right there. So we use the discontinuous formula for D between 0 and 0.9, and then for D between 0.9 and 1 we're in continuous mode and we have to use the continuous formula. So here's a plot, a computer drawn plot of the discontinuous formula going all the way up to D is 0.9, and after that we follow the continuous formula of M equals D. And that's what happens over the whole range of from 0 to 1 in duty cycle for the case when K is equal to 0.1. One easy way to plot this is to recognize that discontinuous mode makes the voltage rise. So you can actually just plot both of these expressions and then take the largest and you'll get the right answer. Another thing I should point out is that what happens when you disconnect the load, which is, say, let R go to infinity. Okay, so K is 2L over RTS. So here with no load power, or R is an open circuit or infinity, if R goes to infinity, K goes to 0. And what this curve does in that case is it actually just rises all the way to 1. Basically, you get the output voltage equal to the input voltage regardless of the duty cycle. It's actually, the solution goes to 1 except right at the axis where it actually turns into a squared off function here. So if, say, the customer disconnects the load, we'll lose control of our output voltage. And we have to do something about that. Generally, we build a feedback loop that stops switching, turns the converter off to keep the output voltage from rising beyond the value that we want so that we could maintain control of the output. Generally, this is a problem. In discontinuous mode, when K goes to 0, we tend to lose control of the output. Let's work an example and go through the analysis of a boost converter in discontinuous conduction mode. Here is our boost converter. We know from the discussions of the previous lectures that the mode boundary between continuous and discontinuous mode occurs when the DC component of inductor current equals the ripple. Since the diode in this converter conducts the inductor current when it's on, that is in fact the condition for whether the diode is turned off by the ripple. We can use our continuous mode solutions for the inductor current and its ripple from previous analyses. Here's what we had before, that the DC component of the inductor current was Vg over d prime squared r, and the ripple was given by this expression. So we can plug these two into here to get the expression for the mode boundary. So here it is again. This is the DC component, and this is the ripple. So for continuous mode, the DC component is greater than the ripple. We can simplify this expression. Let's see, the VGs cancel out. We can put the terms that depend on duty cycle on the right side of the equation and the other terms on the left-hand side, and we get this expression. We recognize that this is our usual K, 2L over RTS, and this is the critical value at the boundary, K crit of D. So this is what comes out of the equations for the boost converter. K crit is equal to D times D prime squared. Here's a plot of that function. The function d times d prime squared has a root at d equals 0 right here, and it actually has two roots at d prime equals 0 or d equals 1 right there, so it looks parabolic about d of 1. And so k crit is 0 at both d of 0 and d of 1, and in between it rises to a maximum. This is qualitatively different than what happened in the buck, and actually it's different than what happens in many other converters as well. In the buck, K crit was maximum at D of 0, so the converter was most likely to run in discontinuous mode at low duty cycle. That's not the case here. Here K crit goes to 0 at both extremes of duty cycle. For high duty cycle, most converters will go continuous. And the reason for that is that as the duty cycle approaches 1, the ripple goes to 0, while the DC component does not. So the converters generally run in continuous mode at high duty cycle. Here the boost is going continuous also at low duty cycle. Why is that? Well, let's look back at the original boost converter. At low duty cycle, for example in the extreme as D goes to 0, we still have a path for current to flow this way through the converter. If we never turn the MOSFET on, current will still flow out of VG through the inductor and through the load. At D of 0, the load voltage is VG. We have load current equal to VG over R, so there's substantial current flowing through our inductor. However, if we don't switch the MOSFET, then there's no ripple. So the current ripple goes to 0, but the DC current does not, and we find that the converter must run in continuous conduction mode. So the boost tends to not want to run discontinuous. But certainly if k is small enough, it can. And one can work out the maximum of this k crit function. It turns out to be at d of 1/3, where the value is 4/27, and that's roughly 0.015. So if we have k less than 0.015, then the converter will run in discontinuous mode over some intermediate range of duty cycles. So here's an example with k just less than 0.1, and we run in discontinuous mode from here to here. Okay, that's the analysis of the mode boundary. Now let's work out the output voltage. So as usual, here we will draw what the circuit reduces to with the switches in the different positions. So for subinterval 1, the MOSFET is on and the right side of the inductor is connected to ground. In position 2, the diode conducts, and in position 3, the diode and MOSFET are both off and the inductor current is 0. So we will go through volt-second balance and charge balance for the two reactive elements. So in subinterval 1, the inductor voltage is Vg, and the load current, or the capacitor current, is minus the load current. We make the small ripple approximation for the output voltage as usual and replace V of t with capital V. In position 2, the inductor is connected to the output. So the inductor voltage is Vg minus V. We can again make the small ripple approximation and replace V of t with capital V. The capacitor current in this interval is equal to the inductor current minus the load current. We do not make the small ripple approximation on I because the ripple is large in the inductor current, but we can make the small ripple approximation in the voltage. For the third interval, the inductor current is 0, and the capacitor current is minus the load current. We'll make the small ripple approximation in the load current as well. So we apply volt-second balance. Here are the inductor voltages we found for the three intervals, so that we can draw the VL of t waveform. To apply volt-second balance, we find the average inductor voltage, which will be d times the d1 times the value in the first interval, Vg, plus d2 times the value in the second interval, Vg minus V, plus d3 times 0. And in steady state, the average inductor voltage is 0. We can solve this equation for the output voltage. If we do, this is what we get. The output voltage is a function of d1, d2, and Vg. d2 is an unknown still at this point, so we need another equation to solve for d2. So to get the second equation, we apply capacitor charge balance. In the case of the boost converter, the elements connected to the capacitor node, besides the capacitor, are the load and the diode. So to work out capacitor charge balance, we should write the node equation. So at this node, the diode current is equal to the capacitor current plus the load current, like this. Capacitor charge balance tells us that the DC component of capacitor current is 0. So we find the DC components of these currents. Capacitor current has 0 average, and therefore the average diode current is equal to the DC load current. So for the boost converter, to apply charge balance, we need to work out the average diode current. Here is our inductor current waveform that looks like the usual discontinuous mode inductor current. The diode current equals the inductor current when the diode conducts, and it's 0 the rest of the time. So this is the diode current waveform. To find the DC component of this current, we should integrate over one period and divide by the period. The integral of the diode current then would be the area of this triangle. And that area is 1/2 the base of the triangle, which is, for this example, d2ts, times the height, which is this peak current we'll call I peak. We can find I peak knowing the slopes. So during the first interval, the inductor current increases with a slope of Vg over L, and I peak then would be that slope Vg over L times the length of the first interval, d1ts. So we can take that I peak and plug it into here. Okay, so here is the area times 1 over Ts to get the average. We plug in our expression for I peak, and we get this. And so if we equate the average diode current to the load current, finally this is the equation that results from capacitor charge balance. So we have two equations and two unknowns. First equation came from volt-second balance. The second equation came from capacitor charge balance. And the two unknowns are the output voltage V and the duty cycle D2. So we can take these two equations now, eliminate D2, and solve for the output voltage. The steps in that analysis are outlined here. So what we're going to do is take the first equation and solve it for D2. So the little algebra, this is what you get. We'll then plug that expression for D2 into the second equation, and then if we rearrange terms to try to solve for V, we get this. Okay, so it turns out that this gives us a quadratic equation in the output voltage that we need to solve. Here is the same equation repeated. So we apply the quadratic formula to solve for V, and this is the answer. As usual with the quadratic equation, we get two roots. So which root is correct? Well, if you look at the discriminant, or the quantity inside the radical, that quantity is greater than 1. So 1 plus the square root of the discriminant gives us a number bigger than 2. Dividing by 2 gives us a number bigger than 1. And the conversion ratio is bigger than 1, which is actually what we expect for the boost converter. On the other hand, the other root, if we take the minus sign, gives us 1 minus a number bigger than 1, so we get a negative answer. Well, we know the boost converter gives a positive voltage, but even if we didn't, we could go back and look at our volt-second balance equation and see that if Vg is positive, then V has to be positive because the duty cycles have to be positive. So a negative V is actually happening because our solution is giving a negative D2, which is a non-physical answer. So we select the positive sign, and then this is our answer for the conversion ratio of the boost in discontinuous mode. And it's valid again when K is less than K crit. Here's a plot of what the function looks like. So we have that M, the conversion ratio, is 1 over d prime in continuous mode, and it's the function with the radical in the discontinuous mode. So for example, for K equals a number bigger than 4/27, we'll always be in continuous mode, and we have this function. Whereas if K is, say, 0.1, then we'll be in discontinuous mode over some intermediate range of duty cycles, and we'll follow the continuous mode result outside that range. So here's a plot for that example. Okay, actually for large K, the discontinuous mode equation can be approximated. 4d squared over K turns out to be much greater than 1. You can ignore the 1, take the radical, and you get that M is equal to 1/2 plus d over root K. So it's actually approximately a linear function of duty cycle for small k. So for example, if k is 0.01, we get this function where it's nearly always in discontinuous mode with a small k, and it's approximately linear function of duty cycle with a slope of 1 over root k, which would be 10. Okay, here's a handy table of the answers for the basic converters. So here's what K crit is. Here's the discontinuous mode M of D. Here's the completing the solution for D2. And then the last column is the continuous mode result. So for all the basic converters, you can just simply go to the table and plug in the results. Finally, here's a plot of the discontinuous mode functions, the M of D functions for discontinuous mode, for the basic three converters. So the boost was this function that approached a linear function with a slope of 1 over root k. It turns out that the buck boost converter exactly has a slope of 1 over root k, and it is exactly linear. So that's plotted here. The buck boost is inverting, and so the inversion is not included in this plot. And then the buck its function turns out to be asymptotic to the buck boost line and to 1. And so it's this function that's below those asymptotes, while the boost function is above those asymptotes. Okay, so for the boost and the buck boost, we actually get functions that are almost linear in discontinuous mode. One last point I would make here is for both the boost and the buck boost formulas, what happens to the output voltage, in this case, when you remove the load? Well, if we remove the load, this is the case where R goes to infinity, and that makes K go to 0. So what happens here, our slope is 1 over root K. If K goes to 0, our slope goes to infinity, and the output voltage goes to infinity. This is a real problem, and it really happens. If you remove the load from your boost or buck boost converters, its output voltage tends to infinity. So physically, why is that? Let's go back and look at the converter circuit. Can you explain why the output voltage of the boost converter would tend to infinity if you remove the load? Well, the answer is, if we look at just how the circuit works, when the MOSFET turns on, the inductor current charges up to some current, and some energy from VG is stored in the inductor. When we turn the MOSFET off, that inductor current and its stored energy flows through the diode to the output, and it charges up the capacitor. So when that energy is transferred to the capacitor voltage increases and its stored energy increases. Now, there is no mechanism for discharging the capacitor if you remove the load. So the only thing that can happen is every time we switch, every switching period, the capacitor is charged with a little more energy, and its voltage rises more and more every time or during every switching period. And with no mechanism for discharging the load or discharging this capacitor through the load, the voltage can build up to an arbitrarily large number. So it is something to watch out for. We have to be careful and limit the output voltage, or if our feedback loop senses this happening, it needs to stop switching or turn down its duty cycle to keep this from happening. But if you run an open loop converter and you say your load wire falls out, then the converter will make a very large voltage. It will probably exceed the voltage ratings of some of the components, and the converter will fail. So we've seen that the discontinuous conduction mode is a consequence of using single quadrant switches or unidirectional switches in an application where the applied switch waveforms become bidirectional. This causes the switches to change their conducting state at times that don't coincide with the drive signal, and it adds additional intervals to the converter which change the properties of the converter. We found how to find the mode boundaries by equating the DC component of the inductor current to the ripple. There are some sample problems that have multiple inductors, and then this gets a little more complicated. But in the case with multiple inductors, we have to carefully draw the diode current waveform and find under which conditions it goes to zero. But in general, we can find an equation of the form k is less than k crit for discontinuous mode operation. We also found how to solve for a steady state in the converters. We apply volt-second balance and charge balance as usual to get a set of equations, but we have to be careful with the small ripple approximation, and in those cases where the ripple is large, we have to use additional arguments. This week we're going to discuss converter circuits. First, we're going to talk about where all these converters come from and what are the relationships between them. So I have just brought up, kind of out of the blue, introduced some different converters such as the boost or the buck boost or some others that we've done in problems. So I want to talk just a little bit about what the relationships are between these and how you can derive one from the other. Then second, we're going to talk about transformer isolated converters, which so far in the course have not been covered. So we will talk about the important topic of how to introduce a physical magnetic isolation transformer into a power converter and discuss some of the well-known and widely used isolated converter circuits. So we'll begin with section 6.1 called Circuit Manipulations, and what we're going to discuss here is how to take a converter we already know and manipulate it to generate a new one and to perform some new function that we want. So what we're going to do is start with a buck converter as the the original rudimentary converter. And at the beginning of the course, I introduced this converter from first principles, that we have a switch network that changes the DC component of the voltage, and then this is followed by a filter that removes the switching harmonics and passes this changed DC component to the load. And we know now from all of the analysis and basic arguments we've given that the conversion ratio of the buck converter, M, is equal to the duty cycle, where this conversion ratio is the ratio of the output to the input voltages. Okay, now something that we can do to a converter is first we can consider changing the positions of the power source and the load. So here I've drawn kind of a box around the buck converter where we have input terminals labeled voltage V1, where there is a source of power connected, and we have output terminals that are labeled V2 here, where we've connected a load with a filter capacitor. So power flows from the source to the load, and we know, since this is a buck converter, that V2 is equal to the duty cycle times V1. Now, one thing that we could do is connect our power source to port 2 and our load to port 1. And here's an example of that. So here I've connected the power source here as V2, the load is V1, but the relationship between V1 and V2 is the same. In fact, if you apply volt-second balance to this inductor, you find you get exactly the same relationship, that V2 is still dV1, but now V2 is the power source and V1 is the load. So if we solve for V1, we find that V1 is equal to V2 divided by the duty cycle. And since the duty cycle is less than 1, the load voltage V1 is greater than the source voltage V2. So this performs the function actually of boosting the voltage. And in fact, if you look at this carefully, you might recognize that this looks like a boost converter, just drawn from right to left instead of from left to right. By interchanging the source and the load, what we've done is reverse the direction of power flow. So this actually makes current flow the other direction through the inductor. And as a result, we have to look carefully at how we realize the switches. So back in Chapter 4, we introduced a formal way to realize the switches. And if we apply that process here, what we find is that we have to put a transistor from the switching node to ground, and we have to put a diode from the switching node to port 1, which is quite different than what we had to do in the buck converter when current flowed the other direction. And something that this does is that it actually changes the definition of the duty cycle. We can define the duty cycle as being the fraction of the time the switch is in position 1, or we could define it as the fraction of time the switch is in position 2. It's really just semantics. We typically define the duty cycle according to the transistor duty cycle, and here when this transistor is on, the switch now is in position 2, not 1. In fact, we can just define switch position 1 as when the transistor's on, and if we do that, we have to interchange d and d prime. So V1 we then write as 1 over d prime times V2 instead of 1 over d. And this then is in fact the traditional equation for the boost converter, that the output voltage, which is now V1, is 1 over d prime times the input voltage. So the d prime comes simply because the power is flowing in the opposite direction and we have to realize the switches in a different way. So the boost literally is simply a buck converter connected backwards. Okay, a second thing we can do is we can connect converters in cascade. So take your favorite converter and call it converter number 1. And we know, if we know its conversion ratio, so the output voltage of converter 1, V1, is equal to this conversion ratio M1 of D times the input voltage VG. And we can take that voltage V1 and use it as the input voltage of a second converter. So take, say, your second most favorite converter and put it there as converter number 2. And its output voltage, that here we will apply to the load, is the conversion ratio M2 for the second converter times V1. Okay, so the overall conversion ratio of this cascade connection then is V is equal to M1 times M2 times VG. So we get a conversion ratio of M1 times M2. Okay, well that's fine, but let's try it. So I think a straightforward thing to do might be to take a buck converter and put it as converter 1, and let's put a boost converter as converter 2. So this combination is capable of making an output voltage that is either less than or greater than VG, depending on the duty cycles of the individual buck and boost converters. Okay, and so in fact if we drive the switches of the two converters with the same duty cycle, then what we get for the cascade connection is D over 1 minus D, which sounds like a buck boost type conversion ratio. And here literally is the circuit then. Here's our buck converter with its switch and LC filter. The output of the buck becomes the input to the boost converter that has its switch and its L and C driving the load. Okay, well that's all fine. However, I would say that there are some things we can do to simplify this circuit. And for one thing, if you look at this inner part of this circuit, we have a 3-pole low-pass filter. So there's an inductor, then a capacitor, and then another inductor that are filtering the ripple. Now you can do this if you want, but we don't really have to. We can reduce the order of this low-pass filter, and the basic DC waveforms will be unchanged. Changing the order of the filter merely changes how it filters the ripple. So for example, we could remove C1 if we like. And once we've done that, we have 2 inductors in series, and we can combine the series connection of inductors into one inductor. So here's that. We have the 2 inductors in series. We combine them into a single effective inductor. That's the sum of the 2 inductances. and we get this circuit. Okay, this is called the non-inverting buck-boost converter, and it's actually a popular converter. It's widely used in applications such as mobile computing and cell phones, where we need an output voltage that is either greater than or less than the input voltage. And we actually don't have to control the two switch networks with the same duty cycle. You can switch, for example, just one and not the other if you want, and that turns out to be a good way to control them. So if you want to boost, we make the buck switches just always connected in position 1, and we operate the boost switches with some duty cycle to control the boost ratio. And conversely, if we want to buck, we just leave the boost switches in position 2, and we control the buck switches with some duty cycle to control the buck ratio of the converter. This is a very efficient converter, and especially if the output voltage is near the input voltage, we have a low switching loss and low conduction loss in this converter, and it can operate with very high efficiency. Okay, there's something else we can do to this non-inverting buck-boost converter. If we just look at what the circuit is with a switch in the two different positions, and let's assume now that we operate both switch networks with the same duty cycle, then with the switches in position 1, the inductor is connected to VG, and I put a dot here to follow the polarity at which the inductor is connected. So the dot is connected to VG, and the non-dot side of the inductor is connected to ground. So we have this circuit for subinterval 1. In subinterval 2, we have the dot side of the inductor connected to ground and the non-dot side connected to the output like this. Okay, so this is what I just described, and this is this non-inverting buck-boost converter. Now, one simple thing that we can do is change the polarity of the inductor during one of the intervals. So for example, during subinterval 2, if we just reverse the direction of the inductor and connect the dot side to the output voltage instead of to ground, like this, then that will change the polarity of the output voltage. Our inductor current, instead of flowing in this way to the output, will flow the other direction and cause a negative output voltage. Otherwise, this is the same circuit as before. So this is called the inverting buck-boost converter, and it turns out to reduce the number of switches necessary. Because if you look at this, the non-dot side of the inductor now is always connected to ground, and all you have to do is connect the dot side either to VGE in position 1 or to the output voltage in position 2. Okay, so here are the two subintervals, and we can connect a switch like this, as I just mentioned, and what we get then is the inverting buck-boost converter, which is what we have talked about previously in this course. So the inverting buck-boost converter can be derived from the cascade connection of a buck converter and a boost converter, and then by reversing the polarity of the inductor during one of the intervals, we simplify the number of switches needed, and we get a minus sign so that it's an inverting converter. Okay, so cascade connections of converters then can actually lead to new converters as well. We cascade two converters and then simplify the result, and we can generate a new converter with properties that combine the properties of the two individual original converters. If you construct the equivalent circuit model of the buck-boost converter, what you find is that you actually get two DC transformer models in it. There's a buck transformer, and later there's a boost transformer in the equivalent circuit model. And this actually reflects the origins of the buck-boost converter, that it is in fact a cascade of a buck followed by a boost. There are other cascade connections possible. I just took one arbitrary one. Another well-known cascade connection starts with a boost and is followed by a buck. So we have boost first, then buck, instead of buck followed by boost. And if we do that connection and follow the same arguments that I applied to the buck-boost converter, what we get in this case is a Chook converter, which is named after its inventor. And he actually derived this converter by cascading a boost followed by a buck. Now you can plug other converters in and follow them. We're not going to do that, but as an exercise, it's an interesting thing to try to do and see what other kinds of converter circuits you can generate. We saw in the last lecture how to apply transformations such as inversion of source and load or a cascade connection of converters to take a DC-DC converter and generate a new DC-DC converter that has different, possibly desirable properties. The approaches that were considered in that lecture will not generate an inverter. So suppose we have DC-DC converters, but we want to make a DC to AC or AC to DC type converter. We need to be able to change the polarity of the voltage, and so far in the previous lecture, none of those approaches would accomplish that. So in this lecture, we'll talk briefly about one of the widely used ways to produce AC. And it's called the differential connection of the load. So if we have two DC-DC converters, what we can do is connect the load differentially between their outputs. So for example, suppose these converters are buck converters. Okay, so the first buck produces an output voltage that is the duty cycle times Vg, and it's a DC voltage. The second buck produces an output voltage that is its duty cycle times the input voltage, which is also DC. But we connect the load differentially between the outputs so that the voltage across the load is voltage 1 minus voltage 2. Now if both buck converters produce the same output voltage, then we will get 0 volts differentially across the load. But if we make one of the converters produce a higher voltage than the other, then we can get either positive or negative voltage across the load, depending on which buck converter makes the higher voltage. And in fact, if we control the duty cycles of the two buck converters in a skillful way, then we could make, for example, a sinusoidal voltage that appears differentially across the load. So here we'll draw out the circuit. Here's buck converter number 1 with its switch and LC filter. Here's buck converter number 2 with its switch and LC filter. And what we're going to do is drive buck converter number 2 with the complement of the duty cycle of converter 1. So if we drive the transistor of buck converter 1 with, say, the duty cycle D, then buck converter 2 will have its transistor driven with D prime. Okay, so then the voltage across the load will be V1 minus V2, or dVg minus d prime Vg, and we can combine the d and d prime together to get this. 2d minus 1 is actually d minus d prime, or d minus the quantity 1 minus d. So we get 2d minus 1. Okay. Here's a plot of that conversion ratio, 2d minus 1 versus d. At d of a half, the conversion ratio is 0, and when d is greater than a half, we get a positive voltage, and when d is less than a half, we get a negative voltage. Now, this circuit can be considerably simplified. We have a lot of LC filters, and we can, again, like in the last lecture, simplify this filtering. And the first thing we might want to do is, if you look at this, you see we have capacitors that are connected from the individual outputs to ground, where what we might really want to do instead is directly put a capacitor across our load and filter the load voltage. So here what I've done is remove these two capacitors and replace them with a single capacitor across the load. Once we do that, you can see that now effectively we have our two inductors in series. So we could take those two inductors and combine them into a single inductor like this, whose value would be the sum of the two individual inductor values. And now you can see we have simply an LC low-pass filter that's taking the differential voltage coming out of the two switch networks and putting that through a two-pole low-pass filter to provide the load voltage. Okay, this is the way we most often build this circuit, and on the right side here is this exactly same circuit. It's just redrawn in the way it's normally drawn, where we have our two switch networks and the load and LC low-pass filters connected differentially across the outputs. This is often called the H-bridge or full bridge circuit or a bridge inverter circuit. It's very commonly used in single-phase inverter applications where we have a DC input VG and we want to produce a sinusoidal output across the load V. It's also used in DC applications, for example in DC motor drives or servo amplifiers in control systems, where we want to drive a DC motor in either direction. So to drive the motor in one direction, we apply a positive voltage that's DC. To drive it in the opposite direction, we apply a negative DC voltage. And so we can do that with a circuit like this as well. We might, in that case, actually replace the whole RLC network simply with a DC motor connected differentially between these terminals. The self-inductance of the motor winding takes the place of this inductor, and the inertia of the shaft replaces the capacitor. If we want to make three-phase AC, we can do the same trick with three converters. So here we might have three different buck converters, one for each phase. Each buck converter produces an output voltage that is its duty cycle times the DC input voltage VG. And we connect our three-phase load differentially across the outputs of the three converters. Okay, so the line-to-line voltage from phase A to phase B will be V1 minus V2. The line-to-line voltage from phase B to phase C will be V2 minus V3, and so on, like this. So what we do then is we control the duty cycles of the three converters to make the three individual AC output voltages be the desired sinusoids with no offset or no DC bias. So here is that circuit. Here again we have three buck converters with their individual filters. As before, we can change the filtering, and again, instead of filtering the voltage from one phase to ground, we might instead want to filter the AC voltage. So we can move these capacitors across the AC load. Here the circuit is drawn with the capacitors omitted altogether, and we simply have the three inductors of the three buck converters and the three switch networks, one for each phase. If desired, we can put three-phase capacitor filters as well. For example, we could connect them in what's called a delta connection and make them filter each line-to-line voltage. Or in some applications, we might omit those capacitors. If we want to build a motor drive, we might replace this whole network with, say, a three-phase induction motor. The inductors become the inductances of the windings, and there will be also filtering from the inertia of the load. But effectively, we have a three-phase AC load that is connected differentially across the outputs of three buck converters. Here's another similar kind of circuit that has a boost type characteristic. There's a single inductor on the input, there are switches for each of the three phases, and we have capacitive filters on the output. And this is the current source inverter. It has a boost type conversion characteristic, but it has a similar three-phase bridge in it. In each of these circuits, I've drawn ideal switches, but of course we have to realize the switches carefully according to the procedures we discussed in Chapter 4. So for this circuit with the buck converters, our buck switches need to be current bidirectional switches because they conduct the AC output currents. And in the current source inverter, we need voltage bidirectional switches because they block the output voltages. But we've now already discussed how to do this, and we know how. Okay, so we've seen that the differential connections of DC-DC converters can lead to inverter-type characteristics and give us a way to really synthesize and understand where some of these inverter circuits come from. Now, there are other ways to do it as well, but this differential connection is, in fact, the most widely used approach. We previously discussed some circuit manipulations to expose the relationships between the different converters and to derive some new ones. There's another way to do this. We can actually derive all possible converters that have a given set of constraints, such as having, say, 2 switching intervals and 1 inductor. I'm not going to derive all the possible converters. It turns out that there are an infinite number of them, and they do some pretty interesting and diverse things. But I do want to briefly summarize some of the basic results. So what's shown here is, I think, the most rudimentary class of converters where we have one inductor that is switched between the input source VG and the output load V in 2 different ways. One way during interval 1 and another way during interval 2. Now, there's only a limited number of possible ways to connect an inductor between 2 voltages, and pick one for the first interval and one for the second, and we can write down all the possible ways to do that and see what converters occur. And the answer is right here. There are 8 converters that are interesting, in addition to a few degenerate or redundant cases that don't add anything new. And we can group these converters actually into 3 different groups. The first group are converters that I would call DC-DC, namely that if you have a positive input voltage, then the output voltage is always of the same polarity regardless of the duty cycle. There's also 2 converters where when you vary the duty cycle from 0 to 1, the output voltage changes polarity in such a way that these are useful as DC to AC type inverters. And then the last 2 are the inversion of the inverters. So they're more suitable for AC to DC type applications or rectifiers. So here they are. The first 2 are the buck and the boost, which we already know about. The next 2 we've also discussed. We have the buck boost and the non-inverting buck boost. So these are the 4 converters in this class. They're all you can make with a single inductor and 2 intervals that are DC-DC type converters. Okay, converters 5 and 6 are ones that you might say are suitable as inverters. And we've already discussed the H-bridge in the last lecture. This is converter number 5. Converter number 6 is a pretty strange one. It was invented, actually the transformer isolated version of this was invented at the Watkins-Johnson Company, and we call this the Watkins-Johnson converter. It has this conversion ratio 2D minus 1 divided by D. It looks like this. But it passes through 0 at D of a half, and it can make either positive or negative output voltages, although the M of D function is a nonlinear one. And then the last 2 in this class are the inverse of numbers 5 and 6. So converter number 7 is what you get if you swap the source and the load of the H-bridge. And this one is sometimes called the current fed bridge. So its conversion ratio is 1 over 2d minus 1. And at d of a half, the ideal conversion ratio goes to infinity. So here's a plot of its conversion ratio. This is a pretty strange conversion ratio, but in fact, if the input is a sinusoid and you want the output to be DC, this is the conversion ratio that you need to perform this rectification function. So when the sinusoid at the input passes through 0 and the output voltage is non-zero, then the ratio, or the conversion ratio, goes to infinity. But in fact, we're not making infinite output voltage, we're just holding up the output voltage when the input is going through 0. So if you vary the duty cycle sinusoidally about a half, then you can convert an AC input voltage to a DC output. And then the last one is what we get from inversion of source and load with the Watkins-Johnson converter, and its conversion ratio is the inverse, which also goes to infinity at d of a half. So those are all the converters that are possible if you only have one inductor and you have two switching intervals. We can think of other classes of converters, and the next most logical class might be the class of two-inductor type converters. So we have two inductors and we switch them in one way between the source and load for the first interval and a different way for the second interval. There are many more than 8 members of this class of converters, and they can do some pretty interesting different things. Here's just a couple of them. The Chuk converter we've previously mentioned, and derived this by cascade of a boost followed by a buck converter. It's an inverting buck-boost type converter. The SEPIC is another converter in this class. The transformer isolated version of the SEPIC was invented at Bell Labs in the 1970s, and they called it a single-ended primary inductance converter, whose initials are SEPIC. This turns out to be a non-inverting buck-boost converter, and it's interesting, actually finds quite a few applications. It's interesting for one because its transistor has its source connected to ground. We realize the switches with transistor and diode like this. So it's easy to drive this transistor with a low side driver and get this non-inverting buck-boost type characteristic. Here's another converter, is the inverse of the SEPIC. It's also a non-inverting buck-boost type converter. Some people call this the Zeta converter. Then there's a lot of other very different converters. So some of them have what we call quadratic conversion ratios that are functions of the duty cycle squared. Here's one of those that was in an earlier homework assignment that has a conversion ratio equal to d squared. And it's interesting that you can get such a conversion ratio in a converter that has 3 diodes and only 1 transistor. We can get quadratic conversion ratios that have other functions also, like buck-boost squared or other types of conversion ratios by some of the members of this class. So there are some very interesting and exotic conversion ratios that are possible. In general, if you have an arbitrary number of inductors and switches, we can build, there are an infinite number of converters that are possible, and in this universe of converters, there are many different and unusual functions of duty cycle, and some of these can have practical applications. So far in the course, we have talked about converters containing only inductors, capacitors, and switches. We've ignored one of the other primary elements used in switching converters, namely the magnetic transformer. So for the next several lectures, we're going to discuss converters with transformers, what the basic circuits are, and how to model them and extend what we already know to understand the operation of transformer-isolated converters. There are a number of reasons to incorporate a transformer into a converter. One of the major ones is when safety requirements require that we have transformer isolation from the power line. Now, one way to do this is to put a 60-cycle transformer at the input of our system, but 60-cycle or 50-cycle transformers elsewhere in the world, these transformers are very heavy and large, and nowadays we generally try to avoid them whenever we can. The size of the transformer scales more or less inversely with frequency. So if we can build a transformer that operates at the converter switching frequency, say 100 kilohertz, instead of 60 or 50 hertz, the size of the transformer and its weight can be reduced by a very large margin. Here's an example of an iPhone charger that plugs into the 120 volt 60 cycle wall and produces a 5 volt output to drive USB connected devices and power them. Inside this charger unit is a flyback converter, which is a transformer isolated version of the buck boost converter, and it contains a high frequency transformer that operates at the switching frequency. Another reason to use a transformer is when we have a large step up or step down of voltage. Suppose we had 100 volts and we wanted to make 1 volt. We could build a buck converter and operate it at a duty cycle of 1%, but such a small duty cycle may mean that the conduction time of the transistor is equal to the switching times of the transistors, and we find then that the efficiency is very low. Most of the time we're switching instead of conducting. So instead we could build a converter that includes a transformer that has a turns ratio and use the turns ratio to do most of the work of stepping down the voltage, and that converter then operates at a much higher duty cycle where the efficiency is better. Yet another reason is we sometimes build multiple output converters that supply multiple voltages, and these are simply additional secondary windings on the transformer inside the converter, and the voltages approximately scale by the turns ratios of the windings. Here's a diagram of a transformer that is a physical magnetic transformer. It has multiple windings, each with some number of turns. So winding 1 has N1 turns, winding 2 has N2 turns, and so on. And we've labeled the voltages and currents of each winding. Here the convention used with polarity marks on the windings is we're defining, for now, all the currents as flowing into the respective polarity mark or dot, and we're defining the voltages as plus with respect to the dots. To understand how a converter works that contains a transformer like this, we need to first model the transformer and to write a set of equations that describe its behavior. What we're going to do is to employ this equivalent circuit model for the transformer. And so the physical transformer on the left is replaced with this equivalent circuit model on the right, where everything inside my dashed lines here is internal to the model and is modeling things that are going on inside the transformer. So we replace our physical transformer with this equivalent circuit model, and this equivalent circuit model has elements that we can solve using standard circuit analysis. So the equivalent circuit model we will use most of the time is this simple first order model that contains an ideal transformer inside these dotted lines, and then in parallel with one of the windings of the ideal transformer is an inductor that is called the magnetizing inductance of the transformer. Okay, so there isn't actually a physical extra inductor put on our transformer. This is built into the transformer, and everything inside this dashed line is an equivalent circuit that is modeling correctly the terminal equations between the voltages and currents of the windings. Okay, the defining equations of the ideal transformer we've seen before. The voltage of each winding divided by its turns is equal for all of the windings. So V1 over N1 equals V2 over N2, and so on. and this makes the voltages scale according to the turns ratios of the ideal transformer. The equations of the currents going into the windings of the ideal transformer is this one, and this is, again, we've seen before also. The sum of the amp turns flowing into the dots of the ideal transformer is 0. Now, in addition to the ideal transformer, we're adding one more element. This L sub m is called the magnetizing inductance, and its current, I sub m, is called the magnetizing current. The magnetizing inductance is actually real, and the way to see that is to do the thought experiment of suppose we connect something up to our transformer, like some AC voltage, connect it up to our primary winding, and suppose we disconnect all the other windings. So they're winding 2 and winding 3 here are simply open circuited. What do we expect this to do? Well, this is a real physical magnetic device. It has some number of turns of wire on an iron core or ferrite core. And if you have simply some turns of wire on one winding that is on a core, we would expect that to behave like an inductor. And the magnetizing inductance then actually models that inductance. So the magnetizing inductance referred to the first winding, where it's drawn here, is the inductance that you would get if you simply put N1 turns of wire on the core. The magnetizing inductance does behave as a real inductor. It obeys the voltage is L di dt, or in this case, V1 is Lm di m dt. And it has to obey volt-second balance. The average value of the voltage applied to this inductor must be 0. So we can apply volt-second balance to find the steady-state behavior of the of circuits containing physical magnetic transformers. The magnetizing inductance also explains why you can't put DC through a transformer. So we can't, for example, apply a DC voltage, Vg, to our transformer, because at DC, the magnetizing inductance, being an inductor, has 0 impedance. Its impedance goes to a short circuit at DC, and it shorts out our DC voltage. And if we apply a DC voltage, volt-seconds won't balance on Lm. The magnetizing inductance is a physical inductor in that sense. It models magnetization of the transformer core. The transformer core has a BH characteristic. If you apply too many volt-seconds to the transformer core, it will saturate and the transformer will turn into a short circuit, which generally is bad in most of our converters. So if the applied volt-seconds on the winding is too large, what happens when you apply voltage is we integrate. So by Faraday's law, the flux in the core is given or proportional to the integral of the applied voltage. As we apply voltage, we integrate up the BH loop. When we get into saturation, then the current in the windings in the magnetizing inductance becomes very large, and the magnetizing inductance essentially turns into a short circuit, which is called saturation of the transformer, and it's generally something we want to avoid. So then, we apply volt-second balance to transformers when we analyze converters that contain them. So the procedure here is that we replace the physical transformer with this equivalent circuit model that contains an ideal transformer plus a magnetizing inductance in parallel with one of the windings. And then we apply volt-second balance to this magnetizing inductance just like we do to any other inductor in the converter, and as we've been doing in the past. And understanding how the volt-seconds balance then is part of the analysis of the converter. Okay, we sometimes use the terminology transformer reset. And transformer reset is the mechanism by which the converter circuit makes the volt-seconds balance on the transformer. In many converter circuits, it's not easy to add a transformer. We have to add additional circuitry to make the transformer reset and get the volt-second balance to happen. So we're going to discuss that with respect to a transformer isolated version of the buck converter known as the forward converter to understand how the transformer gets reset and how we can get the volt-seconds to balance. One last point, this equivalent circuit model is a simple first-order model that is adequate for most things we're going to do in analysis of converters, but if desired we can further refine this model to model other things. So for example, if we want to model the resistance of the windings, like we've done in previous exercises for modeling losses in inductors, we can model resistance of the windings of the transformer by putting resistors in series with each of these windings. And in our equivalent circuit model then, these resistors appear basically at the terminals of the model. So in these places. Sometimes we model what's called core loss in the transformer, and we can do that by putting a resistor in parallel with a magnetizing inductance, the traditional way to do that. And sometimes we model what are called leakage inductances that are effectively series inductances in series with these windings. Okay, we're not going to model those in this course, but they do exist. They're a higher order effect in the transformer, but there are times where we need to include them. So in the upcoming lectures, we're going to use this transformer model to understand how some of the basic transformer isolated converter circuits work. We're going to look at transformer isolated versions of the buck converter and the buck boost converter. We will apply this model and understand the transformer reset, generalizing our ideas of volt-second balance and charge balance to include volt-second balance on the magnetizing inductance. I'll also briefly list some of the other common transformer isolated converters. Last time we talked about how to model a transformer and the first order model that included an ideal transformer with a magnetizing inductance in parallel with one of the windings. The magnetizing inductance models magnetization of the core, and it operates like a real inductor in that we have to have volt-second balance on this magnetizing inductance. So today we're going to talk about how to put a transformer into a buck converter, and one of the common, well-known, and commercially important transformer isolated versions of the buck converter that is called the forward converter. Now, putting an isolation transformer into a buck converter and getting the volt-seconds to balance on the magnetizing inductance is not so easy to do. Here's a buck converter. I've just drawn one, and let's think about, where could we perhaps break the circuit and insert an actual isolation transformer. So we want to put a transformer somewhere in this circuit. So perhaps we could break these wires and put the transformer here. Or we might try putting it over here, perhaps, breaking the wires right there. Or perhaps we could try breaking the wires right here. And the question is, do any of these work? And could you put the transformer in any of these points and get the volt-seconds to balance? Okay, well, if we put the transformer in position 1, we're connecting the primary of the transformer straight up to VG, which is DC. So we would be applying a DC voltage to the primary winding of the transformer, and the volt-seconds won't balance. So that's no good. Likewise, at position 2, we would be connecting the secondary of our transformer up to the output voltage, V, which is DC if the converter works. And so we're putting DC on our secondary. And so that also applies a DC voltage across the transformer. The volt-seconds won't balance, and that's no good. Okay, how about position 3, or this point 3? Well, that's a little trickier, but that doesn't work either. Because in fact, if volt-seconds balance on this inductor, then the average voltage across this filter inductor is 0. And so the DC at this point, at point 3, is the same as the DC at point 2. And in fact, the voltage, the switch voltage at this point switches from 0 to VG and back, but it never goes negative. So the average is positive, and the volt-seconds don't balance there either. So none of these places work, and it's just not so easy to do. So we have to go to more work, and we actually have to add extra circuitry to make the volt-seconds balance and reset the transformer in any of these buck-derived transformer-isolated converters. And so there are quite a few different schemes and different ways to do that. What we're going to talk about now is one of the more popular ways that is called the forward converter. Here's a schematic of the forward converter. We have the transformer placed in series with Q1, and its output or secondary winding, which is actually winding 3 in this diagram, goes through some diodes to the output terminals. And the voltage right here is the same voltage driving the LC output filter that we have in the regular non-isolated buck converter. So Vs of t actually switches high and low with some duty cycle. It turns out to switch high to N3 over N1 VG with a transistor on, and it's 0 with a transistor off. And so we get a voltage that has a DC average that depends on the duty cycle that gets filtered to produce the output voltage. That is very similar to the original non-isolated buck converter. But then we have an extra winding here, and there's some extra means for resetting the transformer and applying negative voltage across the magnetizing inductance during the D prime interval to get the average value of the transformer voltage to be 0 and get the volt-seconds to balance on the magnetizing inductance. So we need to talk about how that works in order to understand this converter. And there's actually different versions of the forward converter that have different circuits to reset the transformer. This is one of the classic ones that has a winding, this N2 winding, is here only for resetting the transformer, but the power actually flows through the first and third windings. So to approach the analysis of a transformer isolated converter, the first thing we do is replace the transformer with the equivalent circuit model. So here is the equivalent circuit model we discussed in the last lecture that contains an ideal transformer with 3 windings in this case. And in parallel with the first winding, we're going to put the magnetizing inductance, the value Lm, and it has a magnetizing current Im. Okay, having that model in the circuit, now we can proceed and analyze the circuit in the usual way. So we will work out the voltage on the inductor, we'll work out the voltage on the magnetizing inductance, and we'll apply volt-second balance separately to each of these. We also will work out the capacitor current and apply charge balance, and in general we will also work out the input current, Ig, and find its average value as well. Okay, here are the waveforms, and it turns out that with this version of the forward converter, the magnetizing current operates in the discontinuous conduction mode. And it has a discontinuous mode type waveform that starts at 0, rises to a peak value while the transistor is on. When the transistor is off, the magnetizing current decreases down to 0 and then remains at 0 for the rest of the switching period. And in the process of going back to 0, we say that the transformer has been reset and its magnetizing current has gone back to the starting point. And the voltages that are applied to the magnetizing inductance that make this happen will then have volt-second balance. Okay, so for this version of the converter, the magnetizing inductance must operate in discontinuous mode. The output filter inductor, on the other hand, can operate either in continuous or discontinuous mode, just like any other buck filter inductor. So we need to write the circuit for the different switching intervals and work out the waveforms. Okay, so let's take our equivalent circuit for the transformer and the converter and look at what happens during each interval. So this is a circuit with 3 diodes. Whenever we have a lot of diodes, it can be tricky to figure out which diodes conduct when. So here's the explanation. During the first interval, the D interval, we turn the MOSFET on. Okay, so Q1 is on, and that makes VG appear across the primary winding. Okay, so here's the dot of the winding is at the plus of VG, so the windings are positive with respect to the dot. We'll have VG times the turns ratio appear across this in2 winding that's plus at the dot, and you can see then that the voltage across this diode D1 will be VG plus this positive winding 2 voltage, which is a positive voltage, and it reverse biases D1. So D1 is off and blocking voltage. On the third winding, we have VG times the turns ratio that is plus at the dot. So there's positive voltage coming out the dot, which will turn on D2. And then we'll get positive voltage after D2. And that positive voltage will turn D3 off. So that's the situation during the first interval with Q1 on, D2 on, and the other 2 diodes are off. Here's the circuit then. D1 is an open circuit, D3 is an open circuit, Q1 and D2 are short circuits. Okay, what happens during this interval? Okay, first of all we have the output inductor current, which I'm going to call I, and it'll be approximately capital I if we have small ripple. That current flows out of the dot of the winding 3 of the transformer. There's no current in winding 2 because D1 is off, and so this output current, which follows the equations of the ideal transformer, if we have current coming out of the dot on the third winding, we must have current going into the dot on the first winding. Okay, recall that the sum of the currents flowing into the dots times their respective turns adds up to 0 in a transformer. So N1 I1 prime is this current flowing into the dot, plus N2 I2, which is 0, and then I3 times N3 is flowing into the dot, but the inductor current is flowing the other direction, so we could subtract N3I is the current flowing into the dot of the third winding. Those add up to 0, and so that tells us that I1 prime, the current flowing into the ideal transformer dot primary winding, is equal to N3 over N1I. So basically this is the reflected output inductor filter current is flowing this way. Okay, the current IG during this interval is that current in that ideal transformer primary winding, N3 over N1I, plus the magnetizing current. One other thing I'll say is for forward converters, we generally design the transformer with no air gap, and the magnetizing inductance is very large and the magnetizing current is very small. So in a typical forward converter, the magnetizing current Im is much smaller than the reflected load current capital I, and this Ig is approximately just N3 over N1 times I. Okay, what happens during the next interval? In the second interval, we turn Q2 off. Okay, what happens when Q2 is off? Well, the magnetizing current has built up to some positive current, and even though it's small, it's not zero. It's more, it's positive, and it has to flow somewhere. Before it was flowing through the MOSFET, but with the MOSFET turned off, it has to actually flow out of one of the other windings. And what our model here predicts is that Im will flow this way, and it will flow through the ideal transformer part of our primary winding model and flow out of the dot. So if we have positive current flowing out of the dot on the primary, then there must be current flowing into the dot of one of the other windings. Well, it can't flow into the dot of the third winding because that would flow backwards through D2. So in fact, D2 gets reverse biased and it is turned off. It won't allow reverse current. So the only other place it can flow is into the dot on the secondary winding, and so it flows like this. And it forward biases D1. The output inductor current has to flow somewhere also. If D2 is off, the output inductor current will flow through D3. So we have D3 on. So for the second interval, here's the circuit. We have Q1 off, D2 off, D1 and D3 are on. Okay. What happens to the transformer during this interval is that with D1 turning on, the input voltage VG is placed across the second winding like this, and it is negative at the dot instead of positive. So the voltage that we get across the magnetizing inductance referred to the primary is of opposite polarity, negative at the dot, and the value will be Vg times the turns ratio. So here's what we have so far for the magnetizing inductance. We have a positive voltage Vg applied during the first interval by the MOSFET turning on. When D1 turns on, we have a negative voltage Vg times the turns ratio in 1 over N2. And with this voltage, the magnetizing current will increase during the first interval up to some peak value, and then the negative voltage during the second interval will make it decrease. Finally, when the magnetizing current gets to 0, D1 turns off because it won't allow current to flow negative through it, and so we have a third interval where D1 is off. Then here is the schematic during the third interval. D3 is still on, conducting the output inductor current, but D1 now has turned off, and the magnetizing current remains at 0 for the rest of the switching period. Okay, so transformer reset. Again, this is the mechanism by which the volt-seconds balance, and we can analyze transformer reset by writing the equations of volt-second balance on the transformer. So then here again was our voltage waveform. The average primary voltage, which is the voltage across Lm, will be the duty cycle D1 times positive Vg plus the duty cycle D2 times this negative voltage minus N1 over N2 Vg plus D3 times 0 for the third interval, and this must be 0 for the converter to work. Here's that formula again. The formula is repeated here, and we can actually solve this formula to find how long D2 is. So if you just solve, you find that D2 is equal to the turns ratio N2 over N1 times D, or D1, the transistor duty cycle. The constraint that this imposes is that we have to reset the transformer before the end of the switching period. D1 can't be, or D3, the length of the last interval, can't be negative. So we can write that D3 has to be greater than or equal to 0, and D3 is equal to 1 minus D1 minus D2. So here is that equation, and if you require D3 to be greater than 0 and you plug in our solution for D2, what we find is that D1, or the transistor duty cycle, must be less than or equal to this quantity that depends on the turns ratio from N1 to N2. If we make the common, or the typical choice that N1 equals N2, then this says that the duty cycle has to be less than a half. And what's happening then is that we're applying plus VG during the first interval, we're applying minus VG during the second interval. So the second interval is the same length as the first interval, and to reset before the switching period is over, the duty cycle then has to be less than a half. If you like, though, you could choose other values of turns and make this limit come out to a different number. So what happens if we let D be greater than a half with N1 equals N2? Well, here's what it looks like. Our magnetizing current won't get back to 0 before the switching period is over. So we'll start the next switching period with some positive value of magnetizing current. And then during the next switching period, we do it again. We don't give the transformer long enough to reset back to 0, and we have some net increase in magnetizing current during the next period also. And this keeps happening. Every switching period, there's a net increase in magnetizing current. And we say the transformer walks up its BH loop, the flux in the core will increase each switching period, and eventually the transformer will saturate. Once it saturates, it turns into a short circuit, and the next time we turn on our MOSFET with the transformer saturated, we get a very large current run out of VG that will make the converter fail. So we have to make sure to build a control circuit that doesn't let this happen. And it's typical to make N1 equal to N2 and build a control circuit that limits the maximum duty cycle to be no more than a half. Okay, we can talk about volt-second balance on the output inductor. And in fact, this is just the same analysis as in the non-isolated buck converter. We can sketch the waveform of the voltage across that inductor, and it looks like this. When the MOSFET is on, we get a voltage here equal to VG times the turns ratio from N1 to N3. That comes out here. On the right-hand side of the inductor, the output voltage is V. So then the VL voltage during the first interval will be N3 over N1 VG minus the output voltage. And for the remainder of the period when the MOSFET's off, we have 0 coming out of or across D3, and the voltage across VL is simply minus the output voltage. So this is DTS here, D prime TS is there. We can apply volt-second balance in the usual way. So D times N3 over N1 VG minus V plus D prime times minus V equals 0 by volt-second balance. And you can solve for the output voltage V, and you find that the output voltage works out to be the duty cycle times the turns ratio times VG. So this is a function that looks like a buck converter with an added turns ratio of N3 over N1. Okay, well, if the duty cycle is limited to, say, a half, then that limits how much output voltage you can get. Although we can change the turns ratio to compensate for that, and we will adjust the turns ratio to step the voltage down or whatever we're trying to do. We also have this other constraint, though, that the duty cycle is limited but to this number that depends on the turns ratio of the reset winding, or the N2 turns, as well. And so one question you might ask is, well, why don't I just make N2 be small? If I do that, that makes the maximum duty cycle be larger. So if N2 approaches a very small number, then the maximum duty cycle approaches 1, and we can get a full range of duty cycles. Well, the problem with that comes with the voltage applied to the transistor. During the subinterval 2, when we're resetting the transformer, diode D1 is on, transistor Q1 is off, and we're applying voltage VG across the second winding, where it's minus at the dot and plus at the non-dot side. And the voltage we see on the first winding then becomes minus at the dot VG times the turns ratio, N1 over N2. So the voltage that is applied to the transistor Q1 during this interval, which is the blocking voltage of the transistor, turns out to be the input voltage VG plus the voltage across this primary winding, N1 over N2 VG. So we get VG times the quantity 1 plus N1 over N2. Okay, so if we made N2 small, and made this turns ratio N1 over N2 be big, it means we're applying a much bigger voltage across our MOSFET. So a small N2 will reset the transformer quickly in a short time, but it takes a lot of voltage to do that, and that voltage gets blocked by Q1. So we end up having a very high voltage stress on Q1, and this can be a real problem. In a power supply, for example, that must operate off the rectified 240 volt power line that we see in much of the world, when you rectify 240 volts, you get a voltage of 240 root 2, that's something on the order of, or something over 300 volts. If we multiply that by 2, so N1 equals N2, then we're around 700 volts across the MOSFET, and it's hard to buy a MOSFET that's that large. We may end up, in order to get margin, we may have to use, say, a 1000 volt MOSFET, and those MOSFETs aren't very good. So in fact, we often want to go the other direction and make N2 be large, not small, to reduce the voltage on our MOSFET. But then that further limits the maximum duty cycle. So we have a trade-off, and the engineer has to decide. So for the case where N1 equals N2 and D is less than a half, then we have this factor of 2 voltage, and N1 is less than N2, then D is restricted to less than some number less than a half, but we have reduced voltage on the MOSFET. Here's another version of the forward converter that's also popular, and it reduces the voltage stress on the transistors. This is called the 2-transistor forward converter. We put a transistor on each side of the transformer, and we have clamping diodes also, as shown here, and these take the place of that second winding that did the reset. So what happens here is during the first interval, Q1 and Q2 are both on, both diodes are off, VG is applied to the transformer, and so NVG comes out the secondary. This turns on D3, D4 is off, and we have the usual first interval where the reflected VG is applied to the output filter. During this interval, magnetizing current builds up inside the transformer, just as in the previous circuit. Okay, during the second interval, what we do is we turn Q1 and Q2 off. This will turn D3 off and D4 on, as in the previous circuit. And what happens to the magnetizing current? Well, we have magnetizing current flowing that has built up, and it wants to flow this way. It can't flow out the secondary winding, because that would mean going into the dot, and that would reverse bias D3. So instead, it flows this way, and it actually flows through these two primary side diodes. So IM will flow, it'll keep flowing in this direction like this. It turns on D1 and D2 and effectively applies VG in the opposite direction across the transformer. And that resets the transformer. This is actually the same same primary voltage winding we would get during the second interval if in the previous circuit with N1 equals N2. So these diodes turn on to reset the transformer. The duty cycle is limited to be less than a half, and the circuit works fine with no extra winding. Now, a nice thing about this circuit is that these diodes also clamp the voltage across the transistors to be no more than VG. So you can see, what about, say, the drain to source voltage of Q1 is here. How large can that be? Well, the biggest it can be is if when D2 is on, which puts this node at 0 and this node at VG, and so VG is applied across Q1. Same thing happens to Q2. The highest this node can be is VG before D1 will turn on and clamp this voltage to VG. So we have VG as the maximum voltage on Q2 as well. So in the previous example with 350 volts applied at the input, we can use much lower voltage MOSFETs. In fact, if we used 600 volt MOSFETs that are very good super junction MOSFET devices that we can buy nowadays, we have plenty of voltage margin, and so we can get a good design that's very reliable. So this is a very popular circuit that is in commercial use today. So to summarize, the forward converter is a transformer isolated version of the buck converter. We say it's a buck-derived isolated converter. We have to do some extra work to get the volt seconds to balance. We saw one way to do it in which we add a second winding on the transformer that performs reset, or another way is to add these extra diodes across the primary to reset the circuit. We have 2 diodes on the output instead of 1, but with this extra circuitry then we can get the volt seconds to balance on the transformer and get a functioning converter. These are very popular and widely used converters today. In this lecture, we'll talk about the flyback converter, which is another very popular form of transformer isolated converter. The flyback converter is a transformer isolated version of the buck-boost converter. Now, it turns out that in the buck-boost converter, it is actually easy to add a transformer. Here's a diagram of the buck-boost, and we have a point in the middle of the buck-boost converter where there is already an inductor. And you could simply place a transformer at this point and the volt seconds will balance because they already balance on the inductor. And in fact what we do in the flyback is we turn the inductor into a transformer. It's actually, we often call it a flyback transformer, and it functions in fact more like a 2-winding inductor. So here is a way to think about it. Suppose we're in the lab winding an inductor with, say, some length of wire that we wind some number of turns on a magnetic core to make an inductor. And suppose instead of just winding 1 wire, we wound 2. So perhaps it's like we needed a fatter wire or thicker wire to have lower resistance, and we decided to just take 2 wires and put them together as if they were 1 and wind them together. Same number of turns. Okay, so I could draw that this way, as is shown in this lower diagram, and it actually looks like a 1-to-1 transformer. The inductor, though, what we were calling the inductor in our original buck-boost converter, we might call now as the magnetizing inductance of this transformer. So it's like we have an inductor, and then we have a 2-winding ideal transformer. Now, so far we really haven't changed anything. It looks more complicated, but it's really just functioning as an inductor with the inductor current splitting in some way between the 2 windings. What we can do, though, in this case now, is to now break this connection. This changes how the current flows through the two windings, although it doesn't change the sum of the current. So if we have current in this winding, call it I1, and a current in this winding, we call I2, the sum of those currents adds up to the original I of the buck-boost converter. But the difference is that now we have I1 flowing when Q1 is on, and I2 flows when D1 is on. So I is distributing between the two windings in a different way. Now, the way we normally draw the flyback converter is the bottom diagram, and it's nearly the same as the one above it. To get a positive output voltage, what I've done is reverse the polarity, or reverse the dots of the winding. Recall that the buck-boost converter inverts the polarity. If we want our flyback converter to make a positive voltage, then we must reverse the dots, and we reverse the diode direction also, so we get a positive output. And then the other thing we can do, if we like, is now apply a turns ratio. And the turns ratio will let us scale the voltage up and down. And this is the conventional flyback converter. There's one other small change. The order of Q1 and the primary winding are reversed here. We usually do that to put the source of the transistor at ground and make it easy to drive with just a regular ground reference driver. So the flyback converter is a buck-boost converter in which we realize the inductor using two windings that effectively give us isolation and a turns ratio. The flyback transformer then, which is this two-winding magnetic device, can be modeled in the same way as a usual transformer, with an ideal transformer and a magnetizing inductance put in parallel. But now we're using the magnetizing inductance as the actual physical inductor in our converter, and this inductor is designed to store energy. Not only that, but the winding currents look very different than the way they look in an ideal transformer. We never actually have current flowing in both windings. There's either current flowing in the primary when the MOSFET is on, or in the secondary when the diode is on, but we don't have the case that the secondary current equals the turns ratio times the primary current. So the magnetizing inductance is very significant, its current is large, and as a result we don't see what we would normally expect in an ideal transformer, far from it. We won't talk about magnetics design in this Coursera course, but I will say that the design of the flyback transformer is very different from the design of a more ideal transformer such as the one that is in the forward converter. We put an air gap in this transformer that lets our inductance store substantial energy, and its behavior, as I mentioned, is different. Okay, having said that, we can still model our converter in the usual way. We replace the transformer with our transformer model having a magnetizing inductance. We then solve the converter applying volt-second balance to the magnetizing inductance, charge balance to the capacitor, and so on, and we can get the equations of the converter. So here's what happens during subinterval 1. In subinterval 1, the MOSFET is on, the diode is off, as is usual in the buck-boost converter. And with the MOSFET turned on, then we have the magnetizing inductance connected to VG. And so we will have what VL is equal to VG. We have current flowing around this path. The capacitor current is simply minus the load current, or minus V over R. And the input current IG is equal to the magnetizing current I. We'll assume we're in continuous conduction mode here and apply the small ripple approximation to V and I and get these equations for the first interval. For the second interval, the MOSFET is off and the diode is on. We now get this circuit with the diode connecting the transformer secondary to the output. With the MOSFET on, the magnetizing current cannot flow through VG anymore. In fact, the magnetizing current or the inductor current will flow out the secondary. In our transformer equivalent circuit model, the way this works is that the inductor current or magnetizing current continues to flow, and it flows around this way, around this path. So it will flow through the ideal transformer and come out the dot on the primary side. So on the secondary side, we have current going into the dot equal to this primary current, or I, divided by the turns ratio N. So now the capacitor current for this interval is that secondary current I over N minus the load current V over R, and we get this equation. The voltage on the magnetizing inductance VL is in fact the reflected secondary voltage. With the diode on, we have voltage V applied across the secondary, and that voltage is negative at the dot of the secondary. So it will be negative at the dot on the primary, and the primary winding voltage will be V divided by the turns ratio N. So the inductor voltage is minus V over N for the first interval. With the MOSFET off, Ig is equal to 0, and so these are the equations for the second interval. We can again apply the small ripple approximation to replace V and I with their DC components, capital V and capital I. So then here are those waveforms. Here's our VL waveform, our IC waveform, and our IG waveform. So now we can apply volt-second balance to VL. So the average VL is D times this voltage plus D prime times that voltage, as is shown here. Volt-second balance says that that must be 0. We can solve this then for the output voltage. So what do we get? V would be Vg times D over D prime times the turns ratio N. Okay, so the output voltage is the input voltage times this buck boost conversion ratio D over D prime, and then also times the turns ratio N. We can apply charge balance to the capacitor. So the average capacitor current will be D times the value during the first interval plus D prime times this second interval value, which gives us this equation. We can solve that for the inductor current I, or magnetizing current, and what we find in that case is that the magnetizing current, referred to the primary side, is V over D prime R, and then times the turns ratio N. Finally, we can write the equation of Ig. The average Ig is D times the value during the first interval, I, plus D prime times 0, so we get the average Ig is D times I. So those are the equations of our DC model of the flyback. As we've done in previous chapters, we can construct equivalent circuit models to go with them. This first one from the inductor gives us this center loop equation. The second one from capacitor charge balance gives us the output side, and the third equation for the average Ig gives us the input port model. So we get this circuit, and finally we can replace the ideal sources with transformers and get an equivalent circuit for the flyback. The ideal flyback has a buck type transformer, and then it's followed by a boost type transformer, and the boost transformer additionally has a turns ratio. So in the end, this is a buck boost converter with an added turns ratio, and the flyback then has its origins, as you would expect, in the buck boost. So the flyback is a widely used and popular converter because it has a very low parts count. It's actually known to be a cheap and inexpensive way with a very small number of parts to build a converter. You can get multiple outputs for very low cost as well. All we have to do is build another output. So we could, for example, have our flyback converter with a transistor, a single magnetic device, flyback transformer, and then one diode and one capacitor for each output. and get multiple output voltages with different turns ratios, and with very low parts count, small converter, get a lot of different voltages. One problem that is known with the flyback converter is a problem called cross-regulation. If we have, say, in 2 turns on this output and in 3 turns on this output, with their respective voltages V2 and V3, we would hope that V3 would be the turns ratio in 3 over in 2 times V2. That's what we would hope, and if we have good cross-regulation, then that's what happens. It turns out with the flyback converter, second-order effects related to the leakage inductances, these small inductances of these transformers, cause the output voltages to differ substantially, and it can make the output voltages highly dependent on load current. So the cross-regulation between the 2 outputs is not very good, and we usually have to do some more work and more engineering to get a good design. So it's inexpensive, but the performance in that sense is not as good. The flyback is often operated in discontinuous conduction mode. That makes the magnetizing inductance very small, and this transformer then can be very small. And so we not only have small parts count, but we have small magnetics also. You can do an analysis of this converter in discontinuous mode, and it turns out to be to give the discontinuous mode buck-boost equations with an added turns ratio.